this way we get a one-to-one correspondence between the points of this localized scheme, namely the prime ideals of the local ring here, and the set of all points of X, which are generalizations of X. So it's a monomorphism, and the image is the set of all generalizations of X, X prime of X, it est all X prime, such that X is a specialization of X prime, maybe such that X is in the closure of the point X prime. Now, to check this point, it's evident that we can reduce to the case when X is affine, because a generalization is contained in any neighborhood of X. So we may assume X affine, and in this case, it amounts just to the statement that the prime ideals in AP are in one-to-one correspondence with the prime ideals Q in A that are contained in P, which is a well-known and more or less trivial statement in commutative algebra. Because to say that the point corresponding, let's say, to Q is a generalization of the point corresponding to P means that Q is contained in P. So all the relation is reversed. Now this, as far as the underlying sets and the underlying topologies are concerned. What about the sheaf of rings? Well, if you have a point X prime in here, this localized scheme for it Y for simplicity, then we can view it. We can look at the local ring of X prime within Y or the local ring of X prime within X. In fact, as we have a morphism of schemes, we have a homomorphism which goes from O capital XX prime to O Y X prime. A morphism between the stokes in the opposite direction. Yes?
Can the local position be identified with the intersection of all of the sets of
Yes. It can be at least. Let's see. Is it true in all cases? I would think so. Yes. Let's see. When does X belong to the closure of a point X prime? If and only if every open neighborhood of X contains X prime. Yeah. So it's just the intersection of all open neighborhoods of X. Yes. Now I look now at the homomorphism of the local rings here, and it turns out that this is an isomorphism. In other words, the sheaf of rings, the structure sheaf on Y, the localized scheme is induced, the sets would make sense by the sheaf of rings that we have on X. Now, where does this come from? This comes from the fact that if in a ring A, I again take an affine neighborhood, open neighborhood of X, in order to make everything explicit in terms of commutative algebra. This means that if you have in the commutative ring A first ideal P and the ideal Q contained in it, and if you look at A localized in P, that corresponds to this ring here, and if you look at the prime ideal in it, which corresponds to Q, namely QAP, and if you localize this local ring with respect to this prime ideal, it's the same thing as if we had localized directly A with respect to Q. It's just an evident transitivity property for localization of things. I think it's handy to describe this Y as being the intersection of the open neighborhoods. In fact, it's the inverse limit also in the scatter of schemes of all open neighborhoods of X induced with endowed with induced structure sheaf. And therefore, if we want to look at things that we are doing over X, working with schemes over X or sheaves of modules over X or whatever, if you want to look at it to what happens locally in the neighborhood of small x, in most cases, this is quite faithfully reflected by taking the base change from Y is the localization of x in x to x. And this is certainly everything that is true in every open neighborhood of small x would be true by base change on this here. And there are theorems to the effect that the converse will hold true, provided the objects we are working over x in a certain sense are finite presentation or something like this. So that we can, from something that is true when we have passed to the limit, we can deduce that it was already true at a finite layer. So that's really the meaning of these localized schemes. So in a way, the local study of x and the study of situations over x, locally over x, is reduced to studying things over a basis that is the spectrum of a local ring of x. And so we are quite naturally led to introduce the notion of a local scheme. A local scheme, by definition, that's a scheme Y, which is affine, local scheme Y, a scheme which is affine, and whose ring A is a local ring. You will see that throughout algebraic geometry, in most situations one tries to have, for rings and for the corresponding scheme for spectra, terminologies that are either identical or that are well matched together. So local rings correspond to local schemes. So we see that the local scheme is affine, and therefore it's quasi-compact, and it has a unique closed point. And the converse is true also. It means that Y is quasi-compact, and there exists a unique closed point. Why is the converse true? Because in a quasi-compact scheme, for every point, if Y is quasi-compact, then for every point Y in Y, there exists a specialization Z that is an element in the closure such that Z is closed. The closed point. This is true in every sober topological space which is quasi-compact, because every closed irreducible subset must contain a minimal closed irreducible subset by Zorn's lemma using the quasi-compacity. And in a sober space, a minimal closed irreducible subset is just reduced to a closed point. All right. Now, if there's a unique closed point, that means that all points of the quasi-compact scheme Y have a common generalization, namely this unique closed point, call it A. But that means that the morphism which goes from the localization of Y at the point A to Y is surjective. But we know it's a homeomorphism, therefore we know that it's homeomorphism into, therefore it's a homeomorphism. And we know also that the structure sheaf here is induced by the structure sheaf of Y. Therefore it must be an isomorphism of local ring spaces, which means that Y implies that Y is a local scheme. So the local schemes are essentially those which have just one closed point plus the extra restriction. I don't know if it's necessary, this extra restriction, but in our argument it is. I don't know if there are schemes that have a unique closed point and that are not local. That means that are not quasi-compact. I suspect not, because, well, never mind. I don't. Maybe you. If you take any quasi-compact neighborhood of this point, that's it. That's it. It must be. Yeah, I can prove that AY quasi-compact is not needed, because let Y be with a scheme admitting a unique closed point. And now let's look at the quasi-compact neighborhoods of A contained in Y. these UI, but what we have proved before, they must be local schemes. And as they have the same local ring at A, they must coincide. So every open subset of Y containing A is all these open sets are equal. Such open set is just the spectrum of the local ring of Y at A. But Y is, of course, that's true in any scheme. It's the union of the quasi-compact open subsets containing a given point, because it's the union of its affine subsets. So you take finite unions of subsets, finite unions of these affine open subsets. So this proves that Y is equal to these UIs. All right. So the local schemes are just those that admit a unique closed point. Maybe there are schemes that are not empty, that don't admit any closed point. I don't know. I can try to. Therefore, if you want to study things locally over a scheme X, that amounts to studying things on certain local schemes, namely the localizations of X at its various points. Now, let's determine the morphisms of a local scheme Y. Let's say the spectrum of the local ring O into an arbitrary scheme X. What are all those homomorphisms? Well, the first invariant is the image, if F is the morphism, the first invariant is the image Fa of the unique closed point of Y. Sometimes this point is called the center of the local scheme. So it's the first important invariant. We have the image of this center of Y, which is a point of X. And a second important invariant is the homomorphism between the corresponding local rings of X at this point, small x, into the local ring of Y at A, which is just O. So to a morphism from Y into X, we have associated a point of X and a homomorphism of the local ring of X at small x into O. And of course, this must be a local homomorphism because of the definition of morphisms of schemes. In other terms, it transforms the maximal ideal here into the it maps the maximal ideal here into the maximal ideal there. And now it's triple checking to see that the converse is true, that if that let's say that first of all F is determined when we know these two data, and that these two data can be chosen arbitrarily. That there is a one-to-one correspondence between morphisms of the local scheme Y into X and pairs of a point small x and capital X and the local homomorphism of the local ring of X at this point into the local ring O. So what one has to do in order to show this converse is to prove that if these things are given, then there exists a unique morphism from Y into X corresponding to these data. But of course, if there's such a morphism, the points of Y must be mapped into, because they are all generalizations of small a of the center, they must be mapped into generalization of X equals f of a. Therefore, they must be mapped into the localization of X at small x. So therefore, this must factor at least set theoretically through the localization of X at small x. In fact, all right. And this, for instance, will allow us to restrict to the case when X is affine, because then the problem is the same as if X was affine, because we can replace X by any affine neighborhood of the point small x. And in this case, it's just a problem of quantitative algebra. Namely, we have two rings O and A, O being a local ring, And we know that the homomorphisms of spectrum of A and the spectrum of A just correspond to homomorphisms of rings like this. And what we have to prove is that to give a homomorphism of an arbitrary commutative ring into a local ring is the same thing as to give first, as to give the kernel of the compositum homomorphism into the residue field of O, which is a prime kernel of this compositum, and second, to give a homomorphism of the localized ring A localized in P into O, which should be a local homomorphism. So this is a question of pure commutative algebra. I guess that without reducing to commutative algebra by just using the fact that this is a topological subspace. But I said about the sheet of things, you can do it intrinsically, but never mind whatever way you do it. It's of course, whenever you have a morphism of an arbitrary scheme y into another x, if we have a point y and its image x in x, then this morphism f induces a morphism of the localization capital Y and small y to the localization of at small x of capital X. That it induces a morphism means that we can find a diagram like this. Which is commutative. The localizations can be viewed as sub-objects instead of schemes. So this morphism induces a morphism between sub-objects. This comes from this description, for instance, of morphisms of local schemes like this one into X. Because to Y corresponds the point X, and we have a homomorphism between the local rings in the opposite direction, which defines us the morphism from this into this here. So localization of a scheme at a point is a functorial affair for variable pair capital X small comma small x of the scheme at a point fixed point. Now, what about the special case of a scheme that is a local scheme that is even the spectrum of a field? A field is a local ring. So now let's look at the case of a scheme psi equals the spectrum of a field K. How can we find morphisms of this into an arbitrary scheme X? How can we make them explicit? Well, we have said that first of all we have to define the image of the unique point. Now the spectrum of a field has just one point. We have to give the image of this unique point, that's an image small x and capital X. And then we have to give a local homomorphism from the local ring of x at small x into K. But the local homomorphism, that means now that the inverse image of the zero ideal in K is the maximal ideal here. That means also that this homomorphism in fact factors through the canonical homomorphism which goes from this local ring of capital X at small x to its residue field, to its quotient modulo its maximal ideal, and an embedding of kappa x into K. Therefore, to give a point, to give a morphism of the spectrum of a field into X, the same thing as to pick a point small x in capital X and to give a homomorphism of the field kappa x into K. In other words, to give a geometric point of X, I mean a point of X with values in the spectrum of the field, the morphism of the spectrum of the field into X, is the same thing as to pick a point of X and to give a homomorphism of kappa x into K to the opposite direction. So in a way there's a universal point, so I mean the certain sense, universal points of X which correspond to the case when we take small k equal to kappa x. If you have any point X, any element of the underlying set of X, we can take kappa of X its residue field. We can take its spectrum, and the spectrum can be viewed now as a scheme embedded in X. It's in fact a subscheme, a closed subscheme of the localization of X at small x, because kappa X is a quotient ring of the local ring of X at small x. And now what we have is that for every point of X with quotients in a field, it is for every morphism of the spectrum of the fields into X, there's a unique way of factoring it through one of these schemes over X. Factoring it through a particular point of X with quotients in some kappa X. Alright, so that much about, for the time being, about localization and local schemes. Maybe we could say a word about local schemes about schemes that are reduced to just one point. So they're necessarily, this point must necessarily be closed, and therefore this is necessarily a local scheme. But it need not be the spectrum of a field. It's just a spectrum of a local ring O, in which there exists, of course, the one maximal ideal, and where there exists no other prime ideal than this one. Now, this also means that M is a nil ideal, that every element of M is nilpotent. That means that M is reduced to the nil radical, because it means that the closed subset of the spectrum defined by M is the whole of the spectrum, which just means that the ideal is a nil ideal according to our general dictionary. Now these rings are the local rings, which we may call of dimension 0 according to general terminology that we will probably still develop. The more important case is the case when M is nilpotent. And if O is Noetherian, if O is a Noetherian local ring, or a Noetherian ring more generally, then a nil ideal in a Noetherian ring must necessarily be nilpotent, because any ideal is finitely generated, and the finitely generated nil ideal must be nilpotent. So, therefore, if O is Noetherian, then this property, its maximal ideal, the unique maximal ideal is a nil ideal, which means that the spectrum is just reduced to a point, means also that it's nilpotent. And moreover, we know that M over M squared, M being of, if O is Noetherian, then M being of finite type, as an O module, M over M squared must be of finite type as an O module, and therefore also as a K module. Where K is the residue field of O. O is Noetherian, then M and nil ideal implies these two things together, which in turn are equivalent to saying that O is of finite length as a module over itself. In fact, we get a filtration of O by the powers of the maximal ideal MR, which is a finite filtration which stops because M is nilpotent. And if we look at the corresponding graded module MR divided by MR plus 1, because M over M squared is a K module of finite type, we see easily that this here must be also a K module of finite type. A vector space of finite dimension over K, because in fact it turns out to be a quotient of the arithmetic power of M over M squared. If we have a set of generators here over K, then taking the R-fold products of these generators, we get a set of generators in here. So these two conditions together allow us to define a filtration O, where the successive quotients are vector spaces over K of finite dimension, and therefore as O is of finite length. Therefore O itself is of finite length. And the converse is pretty trivial too. So in fact, among the rings whose spectrum is reduced to just one point, we have the local rings that are arcing rings, because to say that the ring is of finite length over itself means that O, by definition, more or less, that O is an arcing ring. So let's give an example of arcing rings that are algebras over a field. We have K of T, we divide by T to the n, for instance. It's the local arcing ring of length, how much? N. Or else, to give an example of something which is not an algebra of field, let's take z over p to the nz, that's another local arcing ring. So the spectra of these two rings are reduced to a point, but they are not spectra of fields because these arcing rings are not fields. They're extensions of a field by a nilpotent ideal. So intuitively, these schemes, these arcing schemes, which are not spectra of field, they should be viewed as being something like infinitesimal neighborhoods of a point in an ambient scheme that may be a lot larger, which may be a reduced scheme, let's say, or even a non-singular scheme. So that's more or less the way they enter into the picture. As for the spectrum of a field itself, according to the context, there's a very naive way of just thinking it's just a point and nothing else. And then we have a field over this point, which is just, which is something pretty innocuous. But we may also remember that the field itself has a lot of structure in it. For instance, the field is the direct limit of subrings that are of finite type in the absolute sense. Let's say over the ring Z. And when we view things this way, we better view a field as being an algebraic variety over something like a prime field or even the integers that is irreducible, and we are identifying looking only on the inverse system of open subsets that are empty in this scheme. We look at it from the bidirectional point of view. The field is the field of rational functions intuitively, an algebraic variety. And there's a lot of structure hidden in it. So topologically in this case, but for the Zalesky topology, the spectrum is something completely trivial. But when we introduce other topologies, like État topology also, which we may speak a little about, then the topological invariance may become highly non-trivial. I will give just one example here. If you take a finite field and its spectrum, then with respect to État topology, the topology of the spectrum is a topology of a circle. And topologically, it's a circle. In fact, it's something like the classifying space up to homotopy of Z. You see, it looks like the quotient of the line by the group of integer translation operator on it. In many respects, it's just like a circle in an algebraic variety over a finite field. You should view topologically as being a fiber space over a circle. So, in the context as we are explaining it here, a field appears as something completely trivial, just a point in the field over it. But in fact, the point is nothing in the field. It's everything. The field hides a lot of extra structure. So that's just a word of caution, because we have so completely not as soon as we look at a field, but they are not. Of course, number fields are kind of hard stuff. The spectrum of a number field is just a point for the Zalesky topology. But there is other point of view, for instance, taking État topology, it has to this other topological invariant and other invariant. All right. Now let's define a certain number of properties on schemes. More properties. Here we have defined local schemes. That's a purely topological notion, in fact. Namely, there exists a unique closed point.
I have a question.
Yes.
Are we to forget about sheaves from now on? Because originally we had these schemes and we went into the trouble of putting
No, we should never forget about sheaves. Whatever way you take a schemes you see, whether you view them as local spaces with a sheaf of things on it, or whether you use them as functors, in all cases you see, you have to use a sheaf theory, I'm pretty sure.
No, I mean the sheaves we introduced, the sheaves on schemes, remember?
Yes.
The generalized sheaves.
Yes.
Those are the ones I mean.
This one. Well, in what we are doing now, I think for the time being, you won't really need it. No, I think probably yes. What we are going to do now, the point of view of schemes as being just local in spaces satisfying some extra conditions, is the most convenient one. Yeah. And certainly the absolute properties for a scheme being connected or such a thing, you see, when you want to express it on a functor, it's slightly awkward. So you better, unless you have the general notion, of a topos at your disposal, and then for any functor you have the induced topos, and you say that the topos is connected or whatever. But otherwise, I think you just stick for the time being to schemes as being a particular case of local space. So let's give, just for memory, two other topological notions for schemes that are important. A scheme may be irreducible. So that's a notion that is very often used. We don't have to redefine it. We use it a number of times, this notion. And the notion of connectedness is also important. It's a purely topological notion. Maybe also we add the property of quasi-compactness for a scheme, which has not to be defined as a purely topological notion. And of course, irreducible implies connected and non-empty. The emptiness or non-emptiness of a scheme is also an important notion, purely set theory. In the old-timeish point of view, all schemes were quasi-compact and irreducible there. But there are many important schemes that are not irreducible in fact. It's very inconvenient with respect to irreducible schemes. And there are also important schemes that are not quasi-compact. For instance, if you take the constant, take for instance any group like usual sets of a group like the group of integers or anything like this, and look at the constant group object, the constant group scheme over a field, let's say, k defines. These things, or the twisted lines of these things, you have to deal with quite frequently in algebraic geometry. And they are of course not quasi-compact because G over K, if G is an infinite set, G over K is the disjoint union of an infinite number of disjoint open subsets. That's impossible if the union was quasi-compact. For instance, if X is a very honest old-timeish variety, non-singular and projective and everything over K, it may even be projective space and a projective line, then you look at the so-called Picarsky mobile, whatever its definition, it's a certain group object over K that classifies invertible bundles on X up to isomorphism and the same after extension of the ground ring from a field to any ring, let's say. So the group scheme here, this turns out to be the extension of the constant group scheme Z by a nice quasi compact group scheme, which is an abelian variety impact. But this part, this constant part C is quite important in some cases. Let's see, it may in fact be twisted, you see. It may no longer be constant, and the fact that there is a twist is also important. And if you don't allow yourself non-quasi compact schemes, you just are very unhappy and ill at ease in order to deal with such important extensions of infinite discrete group schemes by abelian varieties. You are not in a good position in order to handle that. Therefore, this quasi compactness is really an extra condition we may put or not put on schemes. We should remember that most schemes one is handling are quasi compact, that there are a lot of important schemes that are not. So this much for topological properties. What about, to recall, we have the notion of an Noetherian scheme. One might think that as a definition that the underlying topological space is Noetherian, which would make a sense, but that would be too weak, much too weak for our purpose. So a Noetherian scheme is a scheme, I think I have not defined it as yet, which has a following property. A definition. X is quasi-compact for one thing. That means that X can be covered by a finite number of affine open subsets. Which affine open subsets just correspond to commutative rings AI. And that moreover, these rings AI are Noetherian. If you want to say, here I said it in a non-intrinsic way by using a particular covering of the quasi-compact scheme where opens affine subsets. But it's easy to see that this implies that for every open, or the equivalent therefore to say that for every open subset U and X, open and affine, the ring of U, namely gamma U or U, is a Noetherian ring. The way in which I pose it here with a particular covering implies that the ring is Noetherian if and only if its scheme, its spectrum is Noetherian. Whereas the second definition has the advantage of being intrinsic. Alright, we have also the locally Noetherian schemes. These are those for which the quasi-compactness restriction is dropped here. It just means that, by definition, for every U and X, open and affine, the ring gamma U O U is Noetherian, the ring of this affine scheme. But that also means that every quasi-compact open subset of X is Noetherian. For every U in X, U only assumed to be quasi-compact. Such a U is Noetherian. This would be definitely, for a Noetherian scheme or local Noetherian scheme, we are making assumptions stronger than just topological assumptions. We're making assumptions on the rings whose spectra allow to reconstruct the scheme. So it would be Noetherian ring. Now, for the old-timers, all schemes, of course, were Noetherian because they were of finite type over field. And therefore, the algebras that they would consider would be, in fact, integrity domains, never mind, but algebras that are finitely generated algebras over field, and because of Hilbert's theorem, these are Noetherian rings. also the most important schemes that one has to work with are either schemes that are of finite type or locally of finite type over a field, or finite type or locally of finite type over a local ring, that is Noetherian, or over the integers. So really the most important schemes one has to work with are either Noetherian or, if they're not quasi-compact, locally Noetherian. However, it would be quite unfortunate if one had to restrict scheme theory to Noetherian schemes, because when working with the formalism, in many ways, one is soon, even if one is interested to start with Noetherian schemes, even schemes of higher type over field, let's say, or over the integers, very soon one is led to go out of the camp of Noetherian schemes. So already when we define schemes by functors, I mean, it was very handy to allow functors of rings, let's say, which are not restricted to be, let's say, of finite type over a ground ring, or which are not restricted to be Noetherian. It would be this kind of condition is rather unstable under operations like tensor products for sure. Another technical reason also is that there's a standard process if we, first of all I explained if we have a scheme X, to look at the localized schemes at various points, which are just the spectra of the local rings of the scheme at various points. So if we start already with schemes of finite type over a field, these schemes are no longer finite type over a field. Because even if we have an algebra that is of finite type over a field, the localizations of this algebra with respect to prime ideals, for instance, with respect, let's say, to the zero ideals prime, which means the field, total field of fractions of the integrity domain, is no longer of finite type as an algebra. It will be a finite type as an extension field, but not as an algebra. So already we get out of the category of schemes that are finite type over the round field. And however, they are still Noetherian, these schemes here. These localized rings are still Noetherian. If you localize any Noetherian ring with respect to any set of elements, then the ring we deduce is still Noetherian. But what we have to do now quite often is to pass also to the completion of this local ring into its spectrum. Now here again, no trouble, it's still Noetherian. The completion of a local ring, of a local Noetherian ring with respect to powers of any ideal is still Noetherian. But in the sense theory now, we have to take the fiber product of the spectrum here over this with itself a certain number of times, which corresponds to taking the tensor product of this completion over this ring a certain number of times. Now these rings by no means are any more Noetherian. And now this technique of passing over the completion, taking tensor product is of very frequent use in algebraic geometry. So there are a number of very strong reasons which show us that we shouldn't, even if we're mainly interested in very special types of Noetherian schemes, we cannot, if we really want to work freely, cannot restrict to these and building up a formalism of schemes. Now, we have also the Artinian schemes. X is called Artinian. Well, there are various equivalent definitions. Let's say, for instance, if X is a spectrum is isomorphic to the spectrum of a ring, that is, X is affine, and its ring A is an Artinian ring. Now, an Artinian ring is a ring that is of finite length as a modulo over itself. Means also that it's a ring that has that satisfies the descending chain condition on ideals. Any decreasing sequence of ideals is stationary, but this implies already that the ring is of finite length. All right. Now, to say that the ring is, that the spectrum is Artinian means also that X is Noetherian and the underlying set is separated. Well, if it's separated as it's quasi compact, that implies that it's finite. And I'm sorry, it's not separated, I want to say. That wouldn't be it. And discrete, which then will imply that it's finite and discrete. So the Artinian schemes are the Lewisian schemes that are discrete, and therefore they are just a finite number of points, and each of these points is a xi, let's say, and each of these points is induced with its local ring, oxi, and that's it. On the other hand, these local rings, of course, should be Lewisian rings, and on the other hand, the spectrum should be reduced to just this point. Therefore, these should be local Artin rings, and yeah, local rings whose maximum ideal is nilpotent, such as m over m squared is 5-dimensional relative field. So the rings which we have already met before. So a Lewisian scheme, an Artinian scheme, I'm sorry, is just a bunch of local Artin rings. And the points are corresponding, the points of this Artinian scheme just correspond to different Artin rings that we are given. They are the Decking's set for the Artin rings that we are given. And of course, the global ring A is just the product of these Artin rings, because the sections of the structure sheet is just the product of the sections over these various points which make open components of the Artin scheme. In fact, I believe it's true, let's see, we think a minute, that X Artinian just is equivalent to saying that X is Noetherian and separated as a, for its topology, and separated topology. Yes. So what I want to prove it on the blackboard. If you are interested to do it, it's an exercise. Now, it is not true that a Lewisian scheme that is finite, such the underlying set is a finite set, is Artinian. Let's give an example. Let V be a discrete vibration ring. So in case you don't know what this is, take, for instance, V to be the localization of Z with respect to PZ, the localization of an at a maximum. Assume S to be affine and S prime to be affine, because first we cover S by affine open sets and reduce the situation whatever lies over this affine open set. And once we have done this, we recover S prime by affine open sets and replace X prime what lies over any such affine open set. So we can assume S and S prime are fine. But then to say that F is quasi compact means that X is the finite union of affines UI. And from this follows that X prime is a union of the X prime i's, which are just the inverse images, if you want, of the ui's in X prime, or the Xi if you want. But which can also be interpreted, each one of them, as the fiber product of Xi and S over S prime, over Xi and S prime over S. But we know that everything being affine here, X prime I and S prime being affine, this fiber product is affine, and therefore X prime can be covered by a finite number of affines. Now what about transitivity? That's trivial on the definition. We have X, Y, Z. If the inverse image by this morphism of a quasi-compact open set is quasi-compact here, and the same property holds here, then by transitivity we have the property for the composite term. What about diagonal morphisms? Are they quasi-compact? Well, they have a strong tendency to be so, but when you really make an effort, you can construct some that are not. Let's say for all practical purposes, one can say that they are. We will study a little later those morphisms for which the diagonal morphisms are scheduled, are quasi-compact. But practically it's always true that there are, one then says that G is quasi-separate. So if you make this small extra assumption on G, then it will be true that if a composite term GF is quasi-compact, then F is. So there's this very slight distinction to make mention. But for no scheme which one has really worked with so far, this is no morphism schemes, this restriction wouldn't be satisfied. All right. Now, so that's about the notion of quasi-compact morphism. Now, what about finite type morphisms? It's a little stronger than quasi-compact. So quasi-compact, I recall, is that if S is covered by affine open sets Si, and if you look at the inverse images Xi in X, these should be quasi-compact, and each of them should be a finite union of Xi alphas, which are affine each of them. Alpha varying between 1 and an integer Ni, the number of pieces maybe depend on the index here. All right. Now, these being affine, they correspond to algebras A, I, alpha if you want, over the ring AI of Si. I mean, I have cut the situation into pieces, into affine pieces, so to say. So I have reduced the situation of commutative algebra, an algebra over a ring. And I will say that the morphism F is of finite type, if not only if it's quasi-compact, but if these algebras here are algebras of finite type. Now, this at first sight seems to depend on the choice of the affine open sets in S and the affine open sets upstairs over the SIs, but it's pretty easy to see that it doesn't. If you want an intrinsic condition, you can state in this following way: for every affine open set downstairs, and for every affine open set X prime over it, which corresponds to a situation of a ring A in an algebra B, B should be an algebra of finite type over A. Thus, to be of finite type appears as being the combination of two properties, one being a global property with respect on X, although it's locally over the basis, it's quasi-compactness, and the other property is local, even above, not only below, which we will call locally of finite type. Namely, a morphism is said to be locally of finite type if for every affine open set below and every affine open set above it, the corresponding situation with a ring mapped into another turns B into an algebra of finite type over B. Now, we have locally of finite type, we have defined this notion, and we have also locally of finite presentation. It's essentially the same definition, except that you now demand that the algebra B over A should be of finite presentation and not of finite type. And it turns out that these two notions, locally of finite type and locally of finite presentation, are local on X. In other words, if X is covered by open sets Xi, then X is of finite presentation, locally of finite presentation over S, or locally of finite type over S, even only if each of the Xi's is so over S. Also, in this solid, you have the following thing: if X and S are affine themselves, So let's assume they correspond to rings B and A. B being an algebra over A. Then X is locally of finite type over S if and only if B is of finite type over A. And this analogous thing with finite presentation. X is of finite presentation over S if and only if B over A is of finite presentation. I'm sorry, locally of finite type means that the rings are of finite type here, locally of finite presentation means that the rings are of finite presentation. So those things check nicely. Of course, I'm being a little quick here. There are a few things that have to be verified. Namely, the essential fact is that if the ring B over A is finite type, let's say, then for every affine open set of spec A and every affine open set of spec B lying over it, the corresponding ring situation is also finite type in the same sign. But that's pretty easy to squeeze out. So, when S is in a certain scheme, of course, then in the algebra, then the affine rings of affine open sets of S are Nernstian, and in this case, algebras over such rings are of finite type if and only if they are finite presentation. So in this case, these two notions coincide. Same thing. These two notions are equivalent if S is Nernstian, or more generally if it is locally Nernstian. Now, all these conditions of being quasi-compact or finite type, or locally of finite type, or locally of finite presentation, they were always satisfied in the classical setup of algebraic varieties over a field, which were always supposed to be of finite type over the field, and all morphisms between these were everything together, which we have looked at so far. So in this respect, it's not really a success. Now, it's pretty clear from what we have said so far that these further notions we have introduced are stable under base change and stable under composition. So maybe in the sequel most times I want even state it and still less prove it. Most times it's never evident. Now let's speak about emergence a little bit. We will define consecutively open emergence, closed emergence, and emergence without any further qualification. So emergence of schemes X goes to Y is an open immersion if it induces an isomorphism between X and homeomorphism between X and an open subset of Y, and if the structure sheet of X can be viewed as being induced by the structure sheet on Y. So to give an open immersion into a given Y is just the same thing up to isomorphism as to an open subset of Y, and then we induce this open subset with induced topology, and we endow this open subset with induced topology and with induced structure sheet. So we have already worked with these open immersions. We have already seen, of course, it's clear that this notion is transitive. We have seen also that it's stable under base change. In fact, a base change of this situation, the X prime here, is just the inverse image of this open set, endowed with the induced scheme structure. So, no mystery about open immersions. By the way, diagonal morphisms have a strong tendency not to be open emergence. So you can say much more than these two stability conditions, A and B, let's say. Much more. What about closed emergence now? We have to define the notion. All right, in order to define it, I will we can do it in two different ways, two equivalent definitions. We can first recover Y by affine open subsets Yi. If you want to do it canonically, take all affine open subsets, but that's not needed. And let's look for every Yi as a part of X lying over Yi. I'm sorry, I mean, you have not assumed yet that X is a subset or anything like this. Let's look at the fiber product of, let's make the base change. Oh, that's it, yes, because we made the base change by an open immersion. It's just a part of X lying over Yi. It's an open subset of X. Xi. And now Yi is affine. And I say that F is a closed immersion if Xi is affine for every I, and Xi goes to Yi is a closed immersion of affine schemes. Id est, I recall, that means for the homomorphism of rings in the opposite direction, Bi goes to Ai, maybe better find that Ai goes to Bi. If I is a ring of Yi and Bi is a ring of Xi, Ai goes to Bi should be surjective. So, this condition, so then we will say that F is a closed immersion. A priori, this condition seems to depend on the choice of the affine open subsets Yi of Y, but it's easy to see that it doesn't. You can, for instance, take all affine open subsets. And the way of foreseeing this, for instance, is to show that it's equivalent with something which is more intrinsic. It is equivalent with saying that, first of all, F induces a homeomorphism between X and the closed subset of Y. So the image of X is closed, and F induces an isomorphism between X and the image, and a homeomorphism. So that's as far as the topology is concerned. F induces. And now what about the structure sheaves? We have a morphism from the sense-logical inverse image. How should I say? Yeah. Well, I can consider this morphism between the structure sheaves corresponding to the morphism of ring spaces X goes to Y as being a homomorphism which goes from OY into the direct image of OX by the closed immersion. On the other hand, because X can be identified to a closed subspace of Y, sheaves on X can be viewed as being sheaves on Y that are zero outside of X. So in fact, F star of OX, it's in a way just OX, but viewed as a sheaf on Y, zero outside of X. And here, because we have a morphism of ring spaces, I have a homomorphism of sheaves of rings of OY into this here. And the condition is that this should be a surjective homomorphism of sheaves, an epimorphism of sheaves. Which means that F star OX can be identified to the quotient of OY by the kernel of this homomorphism, which is a sheaf of ideals, J. Yes?
Does the first condition imply that F is
prime?
It does, yes. There's a little point which is slightly subtle, which one certainly, yes. Let's see. Hey, no, it's not true. No, it doesn't. It would if you assume that this remained true after any base change.
Universally.
I'm not sure it does. That's F is F, right? If F is a homeomorphism between X and image. So, all right, we may already assume then what's the whole? That the image is everything. I don't know. It's multiplied. It's not hard. But it does imply, for instance, that f star of OX is a crazy clear sheaf of modules. And therefore that the kernel J here is a crazy coherent sheaf of ideas. Therefore, closed immersion, you see from this condition that if you have a closed immersion, it's a monomorphism, because a closed immersion of affine schemes is a monomorphism. So X can be viewed as being a subobject of Y. Which subobjects of Y do we obtain in this way after isomorphism? We obtain those which can be defined in terms where we would say first a closed subset of X with induced topology, and second, well, a sheaf of ideas J on Y, which is quasi coherent, and in such a way that the support of this quotient sheaf should be just the closed set we have taken. So in fact, we need not take this closed subset, we just have to take the quasi coherent sheaf of ideas. And the quotient of OY by J will be the structure sheaf of the scheme X we are looking for. Therefore, if we speak in terms of subschemes of a given scheme, either open subschemes or closed subschemes, you see, we see that open subschemes of a given scheme, namely sub-objects that come from open immersions, are just identified with arbitrary open subsets. They are just given sets notably. As for closed subschemes, which correspond to the notion of closed immersion, they correspond in a one-to-one way to quasi-coherent sheaves of ideas, J. We are associating to every J, the scheme whose underlying topological space is the support of the quotient of OY by this quasi-coherent sheaf of ideas, and allowing it with a structure sheaf which is the quotient of OY and J, but restricted to this topological subspace. And in this way, we get a one-to-one correspondence between subschemes of Y and quasi-coherent sheaf of ideas on Y, which generalizes in the case when Y is affine, the relation between ideals of the ring, and the ring of Y, and the, how did you call them? Affine algebraic subspaces of the given affine algebraic space, Y. Now, in this picture, what about base change and transitivity? All right, if X is defined in Y by a sheaf of ideals J, in this case I will just say that X is V of J, I can also describe then X as being the spectrum of OY divided by J, viewed as being a quasi-coherent sheaf of algebras over OY. All right, now what about base change? If I have a Y prime over Y, well, X prime then, the scheme deduced over Y prime deduced from X over Y by base change, it will be, if you want, the spectrum of OY over J tensored over OY with OY prime. That's compatibility of forming spectra of sheaves of algebras with base change. But this tensor product here is just O of Y prime divided by G over phi prime. It's over phi prime divided by the sheaf of ideals, which is the inverse image of the sheaf of ideals I had on Y. And therefore we see, it's pretty clear, that this sheaf of ideals will be again quasi-coherent. And therefore we see that this is again, the spectrum of this is again a closed subscheme of Y prime. So this shows us the stability of closed emergence by base change. And what about transitivity? Well, it's pretty clear too. For instance, if we take this description here, let's say it's in the following way. If we have a quasi-coherent sheaf of ideals J and OY, which defines the subscheme X, then to give a sheaf of ideals on X is the same thing as to give a sheaf of ideals on Y, which is intermediate between J and OY itself. It's just as in the case of all linear rings. If you have an ideal in a ring, then to give it an ideal in the quotient ring is the same thing as to give an ideal intermediate between the ideal we start with and the whole ring. And it's pretty clear that K is quasi-coherent as a sheaf of modulus on Y if and only if K over J is quasi-coherent on X as a sheaf of modulus on X. So in this way we have a one-to-one correspondence between quasi-coherent sheaves of ideals on X and quasi-coherent sheaf of ideals on Y, which happen to contain J. Now what about the spectra now of the corresponding quotients? Well, we see that if you look at the subscheme Z of X, which corresponds to K over J, K being assumed to be quasi-coherent, is just the subscheme of Y, which corresponds to the quasi-coherent sheaf ideals K in OY. So that's how the picture looks like. So this gives us at the same time transitivity. If you have if Z is a closed subscheme of X and X is a closed subscheme of Y, then Z can be viewed as being a closed subscheme of Y. So closed inversions are stable under base change and under composition. So I think we have to stop now. So tomorrow we will define emergence in general as being compositor of closed and open emergence. And having defined closed and open emergence, we will be able to define specific action.
Excuse me.
Yes.
Can you come back to the definition of closed immersion?
Yes.
You gave two characterizations, right?
Yes.
In one of them, it was clearly stated that the map should be affine to begin with.
I didn't assume it will be a consequence. I think. Now, all right. Let's try. So the first was, so we have a morphism X goes to Y. We want to define that it is a closed inversion. So the first definition which I took was that covering Y, there are affine open sets Yi, looking at the inverse image of Yi and X, call it Xi.
So you assume that Xi, the Xi were affine.
So I assume that Xi is affine and Xi goes to Yi should be a closed immersion of affine schemes which we have already defined, which means that for the rings AI goes to BI, this should be a surjective homomorphism. So this implies, of course, that F goes to Y is affine. Now the other definition which I gave, but I didn't check here that it's equivalent, is the following: X goes to Y should be a homeomorphism of X onto a closed subset of Y. This, of course, is the consequence of our definition here, because this is the local condition on Y, and for closed emergence of affine schemes, we know that this is true. So that's one point. And the second point was something about the sheaf of ring, X being identified now to a closed subspace of Y. You can identify the sheaf of, I mean, this is kind of, I think, kind of handy, to identify any sheaf on X as a sheaf on Y vanishing outside of X. In the abelian sheaf, because this is the sheaf of rings on X will be a sheaf on rings on Y vanishing outside of X. And so homomorphism in the opposite direction between the sheaves, structure sheaf here and structure sheaf there, could be a homomorphism from OY to OX. And the second condition is that this should be a surjective homomorphism, an epimorphism of sheaves of sets, which means that OX should be identified to X over J. Now, in order to prove, so this is of course also a necessary condition, because we have to check it only when Y is affine by the definition here, and then we just have to notice that in the case of an affine morphism of affine schemes X and Y, the closed inversion, the direct image of the sheaf OX by the morphism F is obtained the following way. It's the sheaf B tilde, where B, the ring of X, is viewed as being, of course it's B modulo over itself, but it's now B it's a modulo over itself, but it's viewed by restriction of scalars as a modulo over A. And the homomorphism which goes from OY to F star OX is the homomorphism which goes, OY is just A tilde, is the homomorphism from A tilde to B tilde, which corresponds to the homomorphism A goes to B, which is surjective. Therefore, this is surjective homomorphism because the functor tilde is exact. Alright, so the conditions which I stated here are necessary in order for the definition, for the first definition to hold, and then we have to prove the converse. In fact, the only point here which requires a little care is to prove that the kernel of this surjective homomorphism J must necessarily be quasi-coherent. And in order to do this, we have to, what amounts to the same, we have to prove that OX is a quasi-coherent sheaf. That FOX, which I identified to the direct image of OX by equal to Y.
The point is that whether the direct image
of the quasi-coherent sheaf is quasi-coherent. Now, this is pretty easy to see in the case of a morphism, which is both quasi-compact, which is certainly true for a closed immersion. You see, the inverse image of a quasi-compact set should be quasi-compact, but the closed subset of a quasi-compact set is quasi-compact. All right, and moreover, the morphism F is of course a monomorphism in terms of this here. That is the diagonal map, because we have it's injective on the spaces, and we have a surjection here on the sheaves. So it's a monomorphism, and therefore the diagonal morphism is an isomorphism, and therefore the diagonal morphism is certainly quasi-compact. And now it's something which we will check a little later perhaps, that if you have a morphism which is quasi-compact and such a diagonal morphism is also quasi-compact, then the direct image, we call this such, if the diagonal morphism is quasi-compact, we say that the morphism is quasi-separated. Never mind the terminology. Then the direct image of a quasi-coherent sheaf is again quasi-coherent. Alright, so we define certain classes of morphisms. We have, for memory, we call that the affine morphisms. We have noticed that they are stable under composition and under base change, as all classes of morphisms that we are going to work with, that generally work with algebraic geometry. Most classes of morphisms, affine morphisms. We have spoken, I think, about monomorphisms. We have spoken about surjective morphisms. Alright, then some finiteness properties. Quasi-compact morphisms, namely the inverse image of a quasi-compact open set should be quasi-compact. Then the inverse image, I think, of any quasi-compact subset should be quasi-compact. But never mind, that's mainly important ones. The morphisms that are finite time, that means they are quasi-compact, and moreover, whenever we have an affine open set over another affine open set downstairs, the algebra to which it gives rise should be of finite type. Now, these conditions are local below only, not locally above. all conditions will be local below that we are going to investigate. But then we have also conditions locally above, like locally of finite type. That's just the last condition I stated. For every pair of an affine above and an affine below over which it lies, the algebra to which it gives rise should be of finite type. And the same thing, we have the notion of locally of finite presentation, where being of finite type is replaced by being of finite presentation. And then we have started, I guess, looking at inversions. So we have defined the closed inversions and open inversions. So open inversions are somewhat more trivial. Open inversions, they're just open inversions x go to y will be monomorphisms, so they will identify x to our sub-object of y, and these sub-objects in one-to-one corresponds with open subsets, right? Like the induced structure, both topological and the sheaf. So these are the open immersions, no mystery. Closed immersions, we have just recalled what it means, and we have obtained that, again, a closed immersion identifies x to a sub-object of y, and these sub-objects and one-to-one correspondence with the quasi-coherent sheaf of ideals J and OY. And sometimes it's handy, if J is such an ideal, to denote by V of J the closed, well, the sub-object of Y it defines, and down with the structure morphed from X into Y, which is a closed inversion. So this immediately generalizes the notation which we had adopted in the case of a ring instead of a sheaf, instead of a scheme. So when Y is affine, by denoting by V of J, J being an ideal of the ring, this subset or the subscheme, according to the cases that this defines in the spectrum, which would be therefore V of J as a scheme over Y is just the spectrum of OY over J. And this correspondence is order reversing. And now let's now use the notation of an open subscheme and a closed subscheme of X. A sub-object of Y, a sub-object X of Y, such that the inclusion morphism from X into Y is a closed immersion. It's called a closed subscheme. And if it's an open immersion, it's called an open subscheme. So closed subscheme and open subscheme. So this is in fact the terminology which is handy if we take the point of view of sub-objects of Y, rather than the point of view of morphisms. Then we see that the open subschemes of Y and one-to-one correspondence with just subsets, open subsets. The closed subschemes of Y and one-to-one correspondence with just quasi-coherent sheaves of ideas. And in terms of order relation for subschemes, the order relation between sub-objects is just the order relation between open subsets. For closed subschemes, the order relation of sub-objects is opposite to the order relation between ideas. All this is completely evident.
So is there any kind of relation between this V of J as we define here now and the old vector bundle defined by the...
Oh, no.
Except for...
So let's say the vector bundle is a fat V, let's say, and this is a non-fat V, no relation. Of course, if we have two closed inversions, x1 goes to y and x2 goes to y, then by the general properties tied up with transitivity and with base change, we know that the fiber product of these two y, which is just the intersection, must again be a closed inversion or an open inversion with these. These were open inversions. Now this intersection in the case of open inversions is just the intersection of open sets, of course. In the case of closed inversions, it should correspond to an ideal which contains both ideals J1 and J2 that define x1 and x2, and which is the smallest one having these properties. So it would just correspond to ideals j1 plus j2. In fact, in terms of tensor product, you can say that this as an affine scheme of y corresponds to the tensor product of oy over j1 times oy over j2, which is just oy divided by j1 plus j2, everything checks oy. And for the inverse image of subschemes, I mean, they correspond either to taking the inverse image of open subsets with induced topology and induced structure sheaf, or taking the inverse image of the sheaf of ideals. So that everything is very explicit, very well in hand. Now we have to define emergence shortly. We should generalize both open and closed emergence. And here again we can state the property in various equivalent ways, I guess. So I will define when f goes from x to y is an emergence by saying that it's either that it's a composition, f is an emergence, if and only if, by definition, it's a compositum, it's of, let's say, f prime f second, where f second, the first one, let's say, is a closed emergence, and the second one, which we apply, f prime, is an open emergence. So that means to have an open immersion into y, then that just means that we have an open subset of y, and that we have and that we can factor this through an open immersion just means that morphism f sets vertically factors through this open set, but the factored morphism x goes to u should be a closed immersion, which means that x should be isomorphic through this arrow to v of j, where j is a sheaf of ideals quasi-coherent not on y but on u, where j is contained in this partition of u and quasi-coherent. Now, this definition is not too intrinsic because this open set can be chosen in several ways. Of course, it's pretty clear if it works for one open set, it works for any other smaller open sets which still contains the image of x and y. By the way, x will be a closed subset of u, which is open in y, therefore x will be a locally closed subset of y. And in fact, for every open subset of y such that x viewed as a locally closed subset in y is closed in u, it's pretty clear that we can view x as being a subscheme of this u. So we don't have unicity. Of course, there's a largest open subset which does it, which would be, I don't always get it wrong, which would be the complement of the boundary, I think, of x and y, which would be the complement of x bar minus x. This is the largest open subset for which it works. So if we take this one, then the definition would be kind of intrinsic. All right. Now we can also give another more intrinsic definition by saying the following: that we want that f should be homeomorphism of x onto a locally closed subset of y, and that moreover the homomorphism which goes from f minus 1 oy, the restriction of oy to x as a sheaf of strings to x, should be surjective homomorphism of sheaves. That's pretty clear. That's a two equivalent if we choose an open set U and then we tell the story which we have said 5 minutes ago in this situation. Because once we choose an open subset U in which X is closed, then this condition is just the one which we have written down before, which can be erased. We can always state it in the following way, that locally on the image of X, F is a closed immersion. So let's give it still another way of formulating it. For every Y element of F of X, there exists a neighborhood, open neighborhood B containing Y, open neighborhood, such that X over V, the part of X lying over V, going to V, should be a closed immersion. And of course, if you don't want to remember what a closed immersion general is, if you want to give a definition of an immersion independently of the notion of open and closed immersion for general schemes, we will take V to be affine, and then we will demand that X over V, the part of X line over V, should be affine, and that the homomorphism for the rings in the opposite direction should be surjective. So locally not on Y, but locally on the image of X, around points of the image of X, we have just closed immersions. That's the definition of a general immersion. So if you don't like to take points, you can just say that there exists a family of open subsets of Y, such that their inverse, call them VI if you want. These are the V's that we have there. Such that the inverse images on X cover X, and such that what I have said here is true, that whenever that for each of these V's, the part of X line over V mapped into V should be a closed immersion. And if you want to take a V affine, then you can express it directly in terms of this here being affine and the homomorphism for the rings being surjective. So is this notion here. So what I call immersion here is what topologists or differential geometers called embeddings. Unfortunately, there is a little discrepancy. For them, immersions need not be, for differential geometers and topologists, immersions need not be homomorphisms into, they could be only locally homomorphisms in, locally on X. You see, for instance, geodesics of tori, that algebraic lens would be considered as corresponding to an immersion of the line into the torus. So here, unfortunately, the terminology is not quite coherent. When I worked out this terminology, I wasn't too much aware of the terminology that different geometers use. And then after 5 or 10 years, when I became aware of the conflict, it was really too late because the immersions had been used too much in the algebraic. I'm really not checking anymore.
An open subscheme of a closed scheme will it be an immersion? So this
Yes, so if you reverse,
yeah.
yes, it will. It's pretty clear because this open subscheme, this open subset of the closed set, you see, is induced by an open subset of the whole space. And you take this as being U. But anyhow, I will have to, we must now ascertain that immersions, in fact, that's more general still, that the composition of immersions is an immersion. And that immersions are stable under base change. All right, now, why are they stable under base change? That's pretty clear because we define them as being compositor of a closed and an open immersion, and each of these classes of morphisms is stable under base change. Compositor also. So now the question is, if you have two immersions, if you take the compositor, this is still an immersion. Well, this is pretty clear, for instance, on this here, on this condition. The surjectivity of the homomorphism for the sheaves of rings is clearly transitive affair, and the fact that we have that topologically speaking, that we have a homeomorphism with a locally closed subset is also transitive. Now what about diagonal motifs? I claim that every diagonal morphism is an immersion. So here we are really in a very nice case where you remember what this means. To say that every diagonal morphism of an x over S is an immersion means also that whenever we have an x over an S, after the base change perhaps, but you just call it x over S, in any section of this over S, then the section morphism is an immersion. Or it can also be stated by saying that whenever we have two morphisms, UV, from X into a scheme Y, and if we take the kernel of UV and the morphism of this kernel into X, this is an immersion. So all these are equivalent formulations of the property. The diagonal morphisms are immersions. Now, how can we check this? All right, take any of the ways, but let's check it with a section. Let's say we have a section of x over S here. Let's prove that this section is an immersion. So we may assume as well as the question is, of course, local over S. You see that when we look at the part of the situation lying over any open subset of S has been covered by these, then we have to check it only on each of these open subsets. So we can therefore assume that S is affine. And now the story, so let F be the structure morphism and G the section. The story is local at any point of X, let's say of the type GS. So let's take any affine open subset of X containing X. That's it. I look at the inverse image of U by G. Back to prime ideal. Let's say T or any taking any prime polynomial, irreducible polynomial P, localized with respect to this. Or take power series in one variable over field K. All these are examples of discrete valuation rings. Discrete valuation rings, among other properties, they have the following ones. They are integrity domains that have exactly one prime ideal different from the zero ideal, which therefore will be maximal ideal. So the lattice of some lattice first, let's say. The ordered set of prime ideals are just two prime ideals, one contained in the other. And therefore the topological space associated to this consists of the generic point, which corresponds to the zero ideal, and the special point, which corresponds to the maximal ideal. In this case, it would be the ideal generated by P. Here's the ideal generated by the polynomial P. Here's the prime P. And here it would be the ideal generated by T. Alright, so that's the structure of it. But it's by no means discrete, because this small point belongs to the closure of the big point here, of the generic point. So it's not an Artinian scheme. And of course, a discrete valuation ring is not an Artinian ring. It has the descending chain of ideals if T is a generator of the maximal ideal, let's say. Or let's say if you have the maximal ideal M, then the powers of the maximal ideal form a strictly decreasing sequence of ideals. Now the Artinian schemes we have a lot of way of getting Artinian schemes. For instance, if we have a point on this in a certain scheme, if we take the infinity of the neighborhoods of this point, we get, which corresponds to taking the local ring of this point and dividing it out by various powers of the maximal ideal. So the spectra of these, which are called the infinity of this here, is called the infinity of the neighborhood of order n of the point x in the scheme x. So that's an important particular case of an Artin scheme. A local Artin scheme, in fact. Another example occurred in set I, finite set, let's say, and if you look, K being a field, if you look at the constant scheme with value I defined over K by I, this is just the sum of capital I copies of the spectrum of K. Therefore, it's an Artin scheme. Another way of getting Artin schemes, if you have, for instance, a group object, a group scheme of finite type over a field K, affine or not. And if we divide this by the connected component of the neutral element, which turns out to be a subgroup object, we will deal with this in more detail. Then the quotient G over G naught is an Artinian object. It's an Artinian scheme. It's in fact finite over K. And the group G appears as an extension of the group which is finite over K. Another group which is connected. So now other types of properties that will be associated to now, which will also involve properties of the affine rings of the scheme considered. We will say that X is reduced. By definition, if the structure sheaf of X is reduced, namely, if every section of the structure sheaf over any open set that is nilpotent is 0. That's asked if F is any section of the structure sheaf over an open set, and if F is nilpotent, then F is equal to 0. There are no nilpotent sections of any open set except the 0 section, which also, because of the dictionary between properties of sheaves and properties of their stalks, first amounts to saying that the stalks of the sheaf, the local rings of X, are reduced rings. Now this property, of course, is a local property. If X is covered by open sets, then X is reduced if and only if these open sets are reduced. So X reduced, question whether X reduces to the affine case. So if X is the spectrum of the ring A, then we see immediately that X is reduced if and only if the ring A is reduced, namely doesn't have nilpotent elements except 0. The scheme is, an affine scheme is reduced depending on if its ring is reduced. So this just amounts to the problem, to the question of commutative algebra, I mean to the trivial result of commutative algebra, that a ring is reduced if and only if the localizations of this at the various times are reduced. So if A is reduced, you have first to prove that its localizations are reduced, and well, I mean you just look. And the converse is true, for instance, that the converse comes from the fact that A is contained in the product of its localizations. The product of reduced ring is reduced, and subring of reduced ring is reduced. So this is all quite trivial. What about now? We will say that the scheme is integral scheme, if it is reduced and irreducible. Now, irreducibility, of course, is no longer a local affair. You can write when X can be covered by open subsets, which are irreducible without X being irreducible. For instance, take the disjoint sum, it takes a sum of two irreducible schemes that are non-empty. And for the same reason, being integral is not a local affair. So if X is covered by open subsets xi, when is X integral in terms of the xi's? Well, X integral, of course, an open subset of X. If X is integral, an open subset is integral except if the open subset is empty. So an open subset of an irreducible set is irreducible. And the same for reduced. Irreducible, non-empty subset of an open subset that is not empty of an irreducible set is irreducible. Alright, so assume that the xi's takes a non-empty, then X is integral if and only if, first of all, the xi's are integral and mutually intersect. Of course, it's necessary that they mutually intersect also, because in a reducible space, any two non-empty open subsets must intersect. That's an equivalent definition of irreducibility. So all you have to show is a converse, that is X either integral and mutually intersect. And X is integral, of course. X will be reduced because that's a local question. So you just have to prove that if you have a topological space that is covered by open subsets that are reducible and that mutually intersect, then the topological space is reducible. That's it. Now, if X is a spectrum of a ring A, if X is affine, therefore isomorphic to the spectrum of a ring A, namely its ring of sections, the structure sheaf, then X is integral if and only if A is integral. That's the affine dictionary which we have already dealt with. In fact, to say that X is irreducible means that A divided by the nil radical of A is integral, and to say that X is reducible means that the nil radical is reduced to 0, and therefore to say that X is reduced, and therefore to say that X is integral means that both A divided by nil radical is integral, is an integral domain, and that the nil radical is reduced to 0, which means that A itself is an integral domain. Does one say that a ring is integral in order to say that it's an integral domain? Integral domain. So here we are close to having crossed first of the desert, and the absolute notions concerned with schemes. Maybe we should also say a word about normal schemes and regular schemes. So a scheme X is called a normal scheme if and only if the local rings are I was going to say are normal rings, but for rings, the slight ambiguity, let's say are integrally closed integral domains. So if you have an integral domain, let's say A, then A is embedded in field of fraction. And we say that as A is integrally closed in the absolute sense, if every element of K that is integer over A belongs to A. Or in other words, every element of K that is solution of an equation with coefficient in A and whose leading coefficient is 1 should be itself in A. That's an important notion of commutative algebra. Now, if this is satisfied for all local rings, we say that X is normal. This implies that the local rings of X are integral domains. So if X, and therefore this implies, let's say, this doesn't imply necessarily that X is integral itself, because X could be the disjoint union of integral schemes. But if, at least if X is locally indifferent, for instance, then this condition that X is normal, and in fact even only if you know that the local rings are integral domains, this implies that X is the disjoint union of integral schemes. It's easy to see. So with a little restriction of X being locally indifferent, X normal implies that X is the disjoint union of integral schemes. But they are more than integrals, because their local rings are in fact normal local rings. Now if X is a spectrum of the ring A, which is an integral domain already, if X itself is integral, namely, and affine, makes this assumption. If X already is integral and is more by affine, so we are looking at how things look locally on X by covering X with, in the general case, by open affine sets. Then we see that X is normal if and only if A is a so-called normal ring, namely A is integrally closed, by which we need its total field of fractions. So we have this notion. It's perhaps more technical than the other notions which we have seen so far. But the notions which we have described are kind of, I think, their geometric meaning is kind of clear. Except being Nusselt, it just means being Nusselt. But that's these are the schemes with which one can work and have strong fineness terms, let's say. But being Artinian, for instance, it suggests having infinitesimal neighborhoods and connectedness and irreducibility, and all these things make a rather clear geometric meaning. Being reduced means that there are more infinitesimal parts sticking out. This here is a little more subtle, you see, to get to the geometric meaning of this. So maybe I should give some comments of what these notions really mean geometrically, even if I don't give a systematic treatment of these things. It's one of the notions, but I think that I remember that I had a hard time assimilating what it really meant till I kind of understood what it meant. So really, its geometrical significance comes from the main theorem, essentially, from the Zariski's main theorem, which says something like this, assuming that X is Nusselt, for instance. So let X be a Nusselt already, and let's assume, for simplicity, although this is not essential at all, let's assume that X is integral already. Anyhow, a normal scheme eventually should be the disjoint union of integral schemes. So that X is integral is not too strong of an assumption if you want to have a geometric interpretation of what normality means. So it has, being integral, it's irreducible. It has just one generic point, let's say eta in x, and the residual field of x at eta, and that's a general definition for any integral scheme. The residual field at the generic point is called the field of rational functions. Kappa eta, or this capital K, this is a field of rational functions of x. And now we are interested in morphisms x prime go to x, which are birational in the following sense. That we assume, moreover, that f is of finite type, something like this, which just means that x was affine, that x prime can be covered by a finite number of affine sets, which correspond to algebras of finite type over the ring of x. So this is a slight tightness condition on the morphism, of course, when we have morphisms of usual algebraic varieties, I think they're all of finite type. That's not too bad. And we will say is that f is birational if x prime, we will assume x prime to be also integral. All these are simplifying conditions which are not so essential. Then we say that f is birational if the generic point eta prime of x prime lies over the generic point of x, so it's dominating, the image of x prime in x is dense, which means that the generic point is mapped into the generic point. And that moreover, zoomorphism from kappa eta to kappa eta prime, which is associated to this morphism, which is zoomorphism on the local length of x and x prime at these points. So here we have the field of functions on x, and here we have the field of function on x prime. If this is an isomorphism, so that x and x prime have the same function field. In fact, the morphism being of finite type, to say that f is birational can be interpreted in a more geometric way without speaking of the function fields by saying that there exists a non-empty open set on x. There exists u in x, open and non-empty, such that the part of x prime lying over u, when we look at the induced morphism, is isomorphic to u. It just means that provided we restrict x and forget what is outside of a certain open set, non-empty open set, provided we take this open set small enough, discarding a large enough subvariety of x lying outside of it, that then over it f becomes an isomorphism. So that's the birational point of view, that we discard what happens outside of any non-empty open set. All right. Now, to say that x is normal means exactly that whenever we have this situation, f is locally an isomorphism, that it's enabled at every point of x prime. It's just an open immersion. So to say that x is normal means that for every f birational as above, f is locally an open immersion. And in fact, we can even dispense with locally. We can even say that f is an open immersion if we assume, moreover, that f is of finite type and separated, but we have not defined as yet what it means. But this restriction is not too bad, at least for the classical mind, because all algebraic varieties classically are separated, and all morphisms between them are separated. So that's not. So normality just means that a birational morphism, I'm sorry, I had forgotten an important extra condition here, birational. Well, this would be false as I stated it, because blowing up a point, for instance, would be birational and not open immersion. I should say this following. And f with finite fibers. that has finite fibers, then F would be an open emergent. So let's give some examples and counterexamples. So there are, for any x, even x non-singular, let's say the affine plane, you can get lots of x prime over x that are Barratian over x, and which are not such that x prime goes to x are not open emergents. For instance, take in the plane, take any point and blow up this point. Then you get an x prime over x, in which the inverse image of this point is a projective line. And the projective line is associated to the tangent space to the point. So I will not give exact definitions here. I just point out the existence of such things. So this construction makes sense and will give rational morphisms which are not open emergents, which are not local isomorphisms, whenever x is, let's say, of dimension at least equal to 2, or affine plane or affine n space n at least equal to 2. This gives counterexamples. On the other hand, and in these cases x is normal, you see, but there are fibers that are not finite. There are fibers that are of dimension, strictly positive dimension. But let's give another example. Let's take this curve here. So this curve has an ordinary double point. And if you look at the normalization of it, which we obtain by separating the two branches, you get a nice curve like this, you see, which now has no singular point at all, no double point. And if you look at the natural projection of this curve onto here, the inverse image of this point consists of 2 points. Outside of this point, the homomorphism of projection is an isomorphism. So here we have a typical example of a birational morphism in which the fibers are finite and which is not an isomorphism, because in the inverse image of this point, there are 2 points here. But the local ring at this point is not normal. That's why such a thing could occur. If you take a cusp like this, you see, curve with a cuspidal singularity. And if now you look at its dissingularization, you have a curve with, which is projected to this curve here by a, in fact, by a bijective map now. The inverse image of this cusp is just reduced to a single point. So in this case, where you have a homeomorphism, the inverse image of every point is reduced to just 1 point. However, this morphism, which is birational of course, is not an isomorphism, because the local ring here is not a regular local ring, it's not a discrete valuation ring, whereas here it's a discrete valuation ring. So you have a little, you see, the fact that it's not an isomorphism is subtler than just something purely topological or set theoretical. It says that the homomorphism which goes from the local ring here to the local ring there is not an isomorphism. All right. But this again is possible only because the local ring here is not normal. And so Zariski's main theorem, which I stated here, so that's Zariski's main theorem, just says that normality means that such phenomena with finite fibers cannot exist. It's a very strong theorem in a way. Zariski proved it essentially for algebraic varieties over fields, and in EGA it's extended to the situation here, by some techniques different from Zariski's, by using the general machinery of schemes, some global tokens. But in fact, what one generally states is in this direction, but I think it's useful to notice. It's kind of trivial. That's the other direction is true too. In order to show that if birational morphisms with finite fibers are isomorphisms implies that x is normal, you just take the so-called normalization of x and apply it. The normalization x prime of x precisely is birational over x with finite fibers, and it's in a certain sense universal with respect to the property. And this is a very standard operation. And when you state that x prime goes to x as an isomorphism, you have precisely stated that x is normal. So normality essentially means, you see, that not only are there not many branches, several branches through a given point, know that one has, you see, that one has stuck together, you see. Here there are, you see, more apparent branches than here, because here there is just one. But here there is just one branch, in fact. Know that one has kind of, should I say, deep modified in some arbitrary way the local ring here by insisting that the functions at a certain point should have, for instance, certain properties on the derivatives or so. That's what normality means in such a way that now variational morphisms with finite fibers into our scheme must be open inversions. These two here. So this is the geometrical significance of normal schemes, but I don't think that in this course we are going really to use them. So it's a somewhat technical note, which is quite often useful, but it probably won't be so useful in our course, because we are doing more basic things still and for algebraic groups. And when they are reduced over, at least over an algebraic closed field, they are already regular. So the notion of a regular scheme is more important for groups than of a normal scheme. So now when is a scheme X said to be a regular scheme? By definition, this means that the local rings are regular. Regular local rings. So we have to define, now we are supposed to know, to define what a regular local ring is. Now what does this mean? I want to give a definition which should be, if possible, kind of intuitive, which should, well, I'm afraid I can, the notion is slightly technical. Let's say that intuitively it corresponds to the notion of a point on capital X which is non-singular. So we want to express properties of a local ring which expresses intuition of a point that is not singular, that is that looks as good as any of the best neighboring points can look, let's say. Something in this sense. And when we are working over an algebraically closed field with schemes of finite type, an algebraic closed field, so the affine algebras therefore are algebras of finite type over this field K, and the local rings are localization of such algebras, then it just means that the completion of this local ring with respect to powers of the maximal idea, which looks like this completion plays the part of formal Taylor expansions at the point X, then this is isomorphic to a power series ring in a certain number of variables as an algebra over K. So this is, if you have this equivalence whenever you have schemes of finite type over an algebraically closed field. Be careful, this restriction, K algebraically closed.
Is this include for perfect fields?
No, because the residual field you see of the local ring here may not be isomorphic to small k. For instance, the ring may be a field extension. Take the local ring at the general point of the scheme, at the generic point. The field extension, or the field extension you like. I mean, a field is certainly a regular ring, local ring. But even when you take closed points, you see, you may have residual field extensions that are finite extensions that are not trivial, you see, and you may not be able to lift the residual field. therefore, so I think that working over algebraically closed ground field, this criterion is good enough. Let's give, however, the general definition of a regular local ring, which comes from commutative algebra. A is a local ring. A being a local ring is called regular. If and only if first of all A is an Asterion, and second, there exists a sequence of elements x1, xn in the maximum ideal such that x1 a non-zero divisor, it's called also a regular element in A. So the multiplication by x1 should be injected. x2 is assumed to be a regular element in A divided by x1, A, etc. xn is supposed to be a regular element in A divided by x1a plus etc. plus xn minus 1a. That is, each of these elements xi should be a regular modulo the ideal generated by the previous ones. These conditions are called, are expressed by saying that x1 up to xn is a regular sequence. That makes a sense for any module. It's the notion of an M regular sequence where M is an A module. x1 injective in M, x2 injective in M modulo x1 M, etc. But that's not enough yet, and we want, moreover, that if we look at what we deduced from A by dividing by the whole sequence of xi's, A divided by sigma xia, this should be the residue field K. In other words, the xi's should generate the maximal ideal. So you want to be able to generate the maximal ideal by a regular sequence. Now the xi's should be viewed, you see, as playing the part, so A is the ring of functions on a scheme, you see, on a local scheme in fact. The xi's are just functions on the scheme that vanish at the center of the local scheme, and the xi's should be viewed as being local coordinates, as a system of n local coordinates on the scheme. And turns out that these conditions look rather weak, and it's not so clear that they are sufficiently strong to express the intuition of something with non-singular with local coordinates, etc. But it turns out that this already is sufficient. So that's what the praxis of working with these things really is. Yeah. That's an element that is a non-zero divisor. That means that's a homotopy by this element is injected. And the regular sequence is a sequence in which each element is regular modulo the ideal generated by the previous ones.
What do you think is called M sequences now? What they call M sequences now?
With M as a module, it's the same definition. X1 should be injected in M. X2 is injected modulo x1 M, etc. And it's an important technical notion in commutative algebra. It implies, for instance, that if you have an M sequence, that if you look at the Kosovo complex constructed with it, it's acyclic. And there are nice properties connected with this. But they are kind of technical. I don't want to enter into this. Let's give a few examples of regular rings. So a ring is said regular if the spectrum of this ring is regular, and if the localized rings at the various primes are regular. Now, of course, a field is regular. On the other hand, if a ring A is regular, then polynomials in one variable over it are regular on a regular ring also. And therefore, by transitivity, a polynomial ring in any number of variables over a regular ring is regular. And as a consequence, K is a field, K of T1 up to Tn is regular. You know already enough now, for instance, to know that the multiplicative group over a field, or the full linear group modularity of rank n over a field, they correspond to open subschemes of standard affine space of dimension n squared, let's say, that they are regular schemes. So here, yeah.
In your definition of regular, you require the local.
No. A scheme is said to be regular if the local rings are regular. A local ring is said to be regular if the conditions set here are true. Of course, then I redefine an arbitrary ring to be regular if and only if the localized rings are regular. Now, of course, there's a difficulty. You have to prove that if A is a regular local ring, in the sense of this definition, then when you localize it with respect to any prime ideal, it remains regular. Now, this, in fact, under this definition, is by no means trivial. And it was Serre who proved this result the first by giving a homological characterization of regular local rings. They are those for which the global homological dimension is finite. And this condition is clearly stable under localization. So we should give this here as and A over P is regular and A S minus 1, let's say, if we localize a regular ring with respect to any set of elements, we get something regular 2, let's say this here. So geologically, in fact, we first define a regular local ring, you see, right? And the maximal ideal in this definition plays an essential part. Then we remark that this notion is stable by localizing it as arbitrary prime. This allows us to define a ring, arbitrary ring to be local, to be regular, and so if all the localized rings are regular. An arbitrary ring to be regular, if all the localized rings are regular. And the local case, the two definitions obtained coincide. And the scheme is said to be regular if all the local rings of the schemes are regular. So, on the other hand, any principal ideal domain, any Dedekind ring is regular. For instance, Z is regular, not only the rings of integers of any number field are regular rings. And therefore also, if we take polynomials in any number of variables, well, these rings are regular rings. So this gives us a bunch of regular rings. We see also that if F is a local ring and Noetherian, then A is regular if and only if its completion A hat is regular. So the notion of regularity for a local ring is reduced to the complete case. And in the complete case, we can say the following. Assume that now that O is complete local ring, and that O is an algebra over field K in such a way that the homomorphism from this field K to the residual field obtained by passing quotient is an isomorphism. So in a way, we assume that the residual field of O has been lifted into a subfield of O. Then O is regular. So that would happen if O was a completion of the local ring at a certain point in an algebraic variety of finite type over an algebraically closed field. Then O is regular if and only if O is isomorphic to a power series ring K, T1, etc. Tn over K, S and K algebra. So among the other examples here for regular rings, I should say if A is Noetherian and regular, then also the power series in one variable by A is also Noetherian and regular. Alright, so that's the main, so to say, geometrical statements in the absolute setting. that one should recall about regularity.
One question.
Yes.
When you wrote down those stability properties, do you assume A is always Noetherian? Is it enough that A is locally Noetherian?
For a local ring, yeah.
No, these
Here.
properties. When you pass on from a regular ring by a polynomial construction or a power series construction, do you
Here.
need the rings to be Noetherian or to start with, or they are at
No,
each
I don't.
local stage is Noetherian?
I don't need it because except for this power series ring, that assumes that A was Noetherian, you see. But here, if you localize this at a certain prime in order to check, at any prime in order to check that this global ring is Noetherian, then it's the same thing. Let's say the following. If you have a prime P in the polynomial ring A of T, so let's look at this homomorphism here, from A into A of T. The prime P induces a prime Q. That's just, I mean, the image of P by the morphism going from spectrum here to spectrum there. All right. And now, if I look at the homomorphism, if I look at this localized ring AT at P, of course, it's an algebra of AQ now. But it's also an algebra, of course, over AQ of T polynomials in one variable. Over T. This is clear, isn't it? So then I have this indeterminate here. And it turns out that, so this is here the polynomial ring in one variable over this local ring. And it turns out that this is obtained from this one by localizing it with respect to a certain prime, the prime generated by P in this localized thing. But of course, if A was regular, then AQ was regular and local, and therefore Noetherian, so we are reduced to the Noetherian K. So maybe we stop here, and we should perhaps decide before we separate whether next course we go on with our crossing of the dessert in order to be through, or whether we change subject and do things which are more closely related to group schemes. So it's up. It's the same for me.
Let's cross the bed.
That's-
Let's cross the bed.
Taking ultra filters, you said. So they find ideas, maximum. Taking ultra filters, will define lots of maximum ideas, but I don't know if you can define prime ideas that are not maximum by some way or other.
If we divide one of the factor field from it, then doesn't it make a maximal idea? From
Oh yes, so that's not there are others, however. I mean, there are very,
yeah,
very
but
different.
are they higher?
You see, the closed ideas are all maximum. They're possibly prime. But what about the non-closed ideas? They make cover.
If you like, I'll give you a phone.
Can I ask you a question? About groups. You proved that X is a fine scheme of finite presentation over a commutative ring.
Yeah.
And G acts on the monoid, then it's a group, and you prove that you use the theorem that from a finite ring.
I'm sorry, that's not what I, no, that's not what I said.
No?
If G is a monoid scheme of finite presentation,
Yeah,
which acts like a monoid on the,
on a fine scheme of finite presentation.
no, that's not what, oh, what I said was that if you had an endomorphism,
Yeah.
that was a monomorphism.
Yeah,
Then it was an isomorphism.
Yeah, then it's isomorphism. And you use the theorem that modulo finite presentation, if it's that endomorphism is.
I didn't prove it, I gave it as an exercise.
Yeah, all right. And my question is that okay, you gave a hint that if this endomorphism is of a finite presentation is monomorphism, then it's an isomorphism.
And then there is a scheme of finite presentation over S, which is if it's an monomorphism, it's an isomorphism.
Right.
I mean, that's was a theorem
Yeah. Okay.
to be proved.
Yeah.
Which implies that if you have a monoid scheme such as the left translation transitions are monomorphisms, so with left simplification, let's say, law, for all the sets of the monoids they define, then it's a group object. But the monoid should be a finite presentation on the basis.
And the question was that I found a theorem that dual kind for module, like if there is a finitely generated module, and
when the same line?
over any commutative ring.
Yes.
Right. Then if the endomorphism of that module is epimorphism, then it's isomorphism.
The ring should be in a certain types, no?
I don't think so.
Hey.
Then I just thought of
The module should be a finite presentation then. Better be a finite presentation, I think.
no, I mean,
Any module of finite type, if you have an
Yeah.
and what is subjective?
Subjective, yeah, subjective, that's the point.
Yeah, I understand. But just a finite type is enough?
Yeah.
Module finite type. How is this proved that it's by
Kramer's rule,
Yeah?
Kramer's rule.
I understand. Need not be free?
Oh, no.
It's the assumptions and
Yeah. M should be supposed finite generated over any commutative ring A. And you have an endomorphism of M if it's subjective. And then it's injective too. It's an isomorphism actually. And the first point is to reduce the situation when the endomorphism is just translation. Homothetic. Okay, can do that.
how can you reduce to this?
Well,
Because the ring A is not
has
commutative.
to. No, the ring is commutative.
But anyhow, yeah, all right, yeah.
The ring is commutative.
Yeah, fine.
Then you.
Yes, fine.
Okay, you consider M as a ring over A of T.
Yeah.
Right, such that and you have the homotopy
Yes.
defined by Q. Right?
Yes,
So we may assume as well that F is a
Element of A.
homotopy.
Yes.
Right?
Element of A.
And then you take a set of generators, one set M and T, and you write equations. Yeah, each F times Mi can be written as sigma Aij Mj, right? Now, yeah, that's because F is subjective. Now,
You can assume that's a module that A acts faithfully on M, perhaps that might help, no?
no, I don't think we need that.
Because you
Well,
divide by the ideal that operates trivially.
well, from this, what is we get?
What
We get
is it?
Aij.
You want to move that F as invertible, perhaps? Then you better.
Alright, times matrix of M is 0, and then you multiply by the adjoint, and
What do you want to prove? F invertible element of A?
yes.
Then you better assume that A acts faithfully on M.
Oh yes.
So let's assume this.
No, but listen. No, yeah. Yeah. You multiply by the classical joint, and then you take the determinant, and you see that the determinant kills each generator, so it kills everybody in the module, right? But this determinant is of the form Fn 12. Let me see. This determinant here is J minus F, right, kills each mi, so it kills any m, right? Now expand this determinant here, where you get something of the form f to the t. Oh no, well,
So,
yes.
so the determinant is in the kills the whole module.
Yeah.
So write it's equal to 0, maybe that might help.
Mm.
Wir wollten it here.
Yeah. Okay. So that's not okay. Yeah. Am I? Okay. That's it.
No, now you can.
Yeah.
Oh, yeah.
Yes.
Yeah.
Then now I'll have a one. I have one to help me here. You see?
Oh,
Yeah. The matrix now
F is
is f times this minus delta ij. Okay, that's it. Yeah.
the
So
determinant of
the
this.
term, yeah, is 1. The term is plus or minus 1. All right.
What's plus minus 1?
The determinant is
Is 0.
no, yes, but I'm trying to expand it. It's plus or minus 1. All right. Plus f times something, isn't it? Plus f times something, and this is 0.
Yes.
So f is a unit. Huh? Yeah, operates as a unit on the
Yeah, so I,
So 1 plus.
yeah, that's still.
Oh, yes.
So
Alright, yeah.
here's the inverse of f.
That is, yeah. You got it. That's nice. Well, that sounds pretty elementary. I had a proof that in the case of an end-of-finite presentation, you see, that was inspired from what I know about endomorphism of schemes, by passing to the limit from a situation of finite type over the integers, which is really true. I mean, it's really, I recognize to indicate a proof, and it gives a less strong result than just using Cramer's formula. But I very much doubt that you can prove this result about schemes or algebras by using such a such device.
You said EP mapping where you assume subjectivity.
Yeah?
In your problem, if you EP mapping, you're not necessarily subjective.
Oh yes.
There's a huge difference.
In the case of subjectivity, it would be much easier. Let's prove, for instance, directly the following thing. If K is a ring and if A is an algebra of finite presentation over K, and if you have an endomorphism U of A, that is not an imperfect, but it is surjective, then U is an isomorphism. Let's prove this. So let's assume first, so A is a finite presentation. And I will first assume that K is Noetherian. This will help us, and then reduce to the Noetherian case. So assume K Noetherian, and therefore this implies that A is Noetherian also, because of Hilbert's theorem, that finitely generated algebras for Noetherian rings are Noetherian. Now look, I think you will get it. Look at the iterates, UN of A, the set of iterates, and look at the kernel of UN. Equals Jn. This is an ideal in A, and the sequence of these ideals is increasing. And therefore, this sequence of ideals must be stationary. But if it is stationary, it's pretty clear that U must be an isomorphism, and that's purely set one can say. So in the case when K is Noetherian, that's kind of clear. And in the non-Noetherian case, it's reduced to the general case is reduced to the Noetherian case, because A being a finite presentation over K, if K is represented as the Dieck limit of the subrings that are finite type over Z, you see, these subrings Ki being a finite type over ring Z that is Noetherian. And it's more or less trivial to see that A being a finite presentation over K, that just means that for I big enough, it comes by base change from an algebra of finite presentation over one of the Ki's. Alright, and that the endomorphism U of A also must come for I big enough from an endomorphism Ui of AI over Ki. And also that, now that's the fact that U was surjective. You see quite easily also that this means that for I big enough, for I to make a base change to a Kj here, Ui was already surjective. So this is completely standard. And now we are reduced to the certain case, Ui being surjective is bijective. Right, so this is relatively trivial. But however, if you put here instead of surjectivity, if you put an epimorphism, then I think it's a lot subtler. And then really we have to use much more than the fact that the Ki's are Noetherian. We have to use as a radial finite type over the integers. We have to kid around with Artin rings, etc. We have to use the fact that Z is a so-called Jacobson ring. That means that in any algebra of finite type over Z, any prime ideal is the intersection of the maximal ideal that contain it, and that the maximal ideal corresponds to finite residual fields and such things. I mean, one has to do some more work. Maybe we won't do it here because we want to use it. It's kind of amusing. It's rather typical of non-classical techniques in algebraic geometry. All right, so let's go on crossing that desert. So we have done making a little review of standard properties, absolute properties of schemes. So I think we have listed the most important, most widely used ones. Now we are going to look at properties of schemes over others, properties of morphisms rather. So properties of relative schemes, or what amounts to the same, properties of morphisms. And there will be a number of such notions which we have to investigate. And all of these classes of morphisms that we are going to define, or classes of relative schemes, they will have a certain number of common points, which I will list, and make some deductions from these properties in the general context. So we will define a number of classes of morphisms for any class of morphism M, let's say. For instance, we have already defined one, namely affine morphisms. For the time being, but think of M as being the class of all affine morphisms. So M will satisfy the following conditions. M is stable under base change. By which we mean the following. If we have a Cartesian diagram, XS here, base change S prime goes to S, and here an X prime that can be viewed as being the Taylor product, a Cartesian diagram. With F and F prime as vertical arrows, then if F belongs to M, we want that F prime reduced from F by base change should also belong to M. We have seen that this is true for affine morphisms, because affine morphisms correspond to spectra of quasi-coordinate sheaves of algebra. We have seen that taking quasi-coordinate sheaves of algebras commutes with base change. That's one of the ways of seeing that affine morphisms are stable under base change. Already, let's notice that this stability under base change implies that M contains all isomorphisms. Is this so? Let's see. Maybe not. Let's see. Is it clear? No, if you know, it contains the identities. Yeah. might be empty, for instance. Yeah. So, all right, therefore we better put now under transitivity, let's say. We will put that first of all it should contain the isomorphisms. Every isomorphism is an M. And second, if F and G are an M incomposable, so X, Y, Z, let's say, G here, F there, then GF is an M. So these two conditions will always be satisfied. Now, if you assume that the instead of B1 that only the identities are an M, which is just the compositum of the empty family of endomorphisms, perhaps. Yes, then it implies already that using this property here, that every isomorphism belongs to it, because every isomorphism can be interpreted in a Cartesian diagram in which the error here is an identity and the error here is a given isomorphism. Let's give already two deductions from these two conditions. Why is this condition, let's say, true for affine schemes, for affine morphisms? Well, what does it mean? So isomorphisms are affine morphisms, that's pretty clear because the inverse image of an affine is affine. And what about the compositum? What does it mean that the morphism is affine? It says that the inverse image of an affine open set is affine. Now, inverse image of an affine open set of Z in Y is affine because G is affine, and taking again its inverse image in X, it's affine again because F is affine. This shows because of transitivity of inverse images. So that's the inverse image by GF of an affine open set of Z is affine in X. So no trouble here. So for instance, affine morphisms satisfy these two conditions. Now let's look at two consequences of this. Let's assume that we have two morphisms, F1 and F2, with same target S, let's say. Or Y, same target. No, why not? No need for this. So let's rather say two morphisms, F1 from X1 into Y1 and from X2 into Y2. The whole thing lying over some ground scheme S, so there are X morphisms. And now let's take the Cartesian product over S of these two, which is a morphism of X1 times over S X2 into Y1 times over S Y2. And I claim that if F1 and F2 are an element of M, then F1 times SF2 is an element of M2. So the conditions A and B imply that M is stable under Cartesian products. So let's give the proof. Well, so let's look at this morphism here. And I claim that it can be obtained. Let's see, how can we do this? By applying twice the base change in something. So let's see. Give x1 which goes to y1, which is an m. Now let's look the projection y1 times y2, so all products are taken over S, goes into y1. And let's look at what we obtained by making the base change in f1 by this projection. Well, the private product of x1 and this here y1 is just x1 times y2. With here, the morphism here is f1 times the identity in y2. Now f1 being in M, this vertical arrow must be in M2. Now let's go on. I, however, am interested in x2 times y2, in x1 times x2. That's it, x1 times x2 mapped into y1 times y2, so I have to make what's this nonsense? How is this working? I have to introduce F2 now somehow, I don't know. So this shows that if one of the two morphisms, F1 or F2, of course means the argument is symmetric, is the identity, then what I said about F1 times F2 will be true. And what I want to say now is that F1 times F2 is equal to F1 times the identity composed with the identity times F2. Does this make a sense? It should do so, I think. Let's look at x1 times x2. This is mapped into x1 times y2 by taking the identity here, times F2. And here we have F1 times identity in y2. Alright, now F2 being an M, this by the symmetric argument of what we have done here must be an M, and therefore the compositum of these two must be an M. This here. So being an M is stable under Cartesian products. There's another theoret, another general property, which will allow us, which is again a situation analogous to the situation of transitivity, with an F here and a G here, and we assume that GF is an M, the compositum is an M. In other words, that X viewed as being a scheme over Z is an M. And we would like to deduce that then for every morphism, Z morphism of X into Y, this morphism is also an M, that X viewed over Y is an M, namely F element of M. So we would like to make such a deduction, but this will not be true under this, in this generality. We have to make another assumption. We have to assume that the diagonal morphism corresponding to G is also an M. So here the diagonal morphism comes in some essential way. What is a diagonal morphism? It's just Y goes to Y times ZY, such that the compositum of this morphism with the two projections of this product onto Y should be the identity. That's a diagonal morphism. Call it perhaps just delta lower G, the diagonal morphism. So I say that if the compositum is an M, if moreover the diagonal morphism for G is an M, and we will investigate a little more how the diagonal morphism looks like. I mean, quite often it will be in, we have the properties stated, but it has quite often the tendency to be affine, although it's not always so. Then F is an M. Let's see how we get this.
Excuse me. How about the other?
Which other?
The positive being an M and the diagonal corresponding to F being an M. We conclude that G is an M.
I don't think it works this way. The situation which we can try out a little, but I don't think there's anything reasonable in this sense. In the situation that right, is x and y are both schemes over z. X over z is supposed to be relatively m, that is the morphism, the structure morphism from x into z is m. We wonder whether any morphism from x into y, any z morphism is in m. It's quite often true, but one has to make it put in order that this be true, it's a small extra restriction, namely that the diagonal morphism for y over z should be in m. So that's about the situation. And we will see lots of examples of this. Now let's prove this little thing. So that's again a deduction from A and B. Yeah? So A and B implies this, and A and B implies this too. And A and B will always be satisfied. Now let's prove this here. So I have x, y, z. Let's rewrite the diagram. F here, G here. And I look again at x over z now by the compositum GF. And now think of z as being a point something like this, you see. We have a morphism from x to, or to be the final object over which we're working. So we have a morphism from x into y, and we can consider the graph of this morphism, which is a morphism from x into the product, x times y, the product being taken over z and all this. So let's look first at this fiber product, x times dy with the second projection here and with the first projection here. So the graph of the morphism f is a section of this here over x, gamma f, and I will define it in a minute. You see, to give such a morphism, which will be a z-morphism, we have just to define its compositum with this and with this by the universal property of the product. And its compositum with this will be the identity. That just means that we have a section of this over this. And its compositum with this here, this would be some z-morphism from x into y, and we just take f. So gamma f is just the pair, the identity on x, comma f. In this way, in fact, that's something quite general in any category. To give a z-morphism from x into y is the same thing as to give a section of x times dy over x, namely the graph. Now, of course, this correspondence is just another way of stating the universal property of the base change. All right, so now I represent f as being the compositum of gamma f here with a projection here. Now, gf was supposed to be an m. So let's put an m over the arrow. And therefore, by base change, the second projection here is an m. And therefore, all we have now to check is that gamma f is an m. And in order to prove this, we will now use the fact that the diagonal morphism for G is an m. And maybe well, let's just give the proof, and then let's emphasize a little bit on this. Let's well, I claim that this diagonal morphism here, this graph morphism, which is of course a monomorphism because its compositum with PR1 is identity as a monomorphism, is just the inverse image of the diagonal of y over z. Where here I have the diagonal morphism delta over g. We have such a diagram here. X times cy is mapped to y times y by the identity by f on x times over z, the identity on y. Here is gamma f, here is delta g, and here is f. And I claim that this diagram is Cartesian. In terms of points, it just means that an element of the graph being identified with subset of the product element of the graph, is just a pair x comma y such that can be identified to pair f comma y such that fx comma y in y times y should be in the diagonal, namely such that fx is equal to y. And that's all it means. All right. Now as delta G is an M, therefore gamma F by base change is an M2. And there we got it. Now let's emphasize a little bit on the meaning of a diagonal morphism being an M. I think that's also interesting in general terms. So let y goes to 0 to s or whatever you want, G, let's say, be a morphism. Then I claim that we have an equivalence between the following conditions. Equivalent conditions on G. A, to say that the diagonal morphism of G is an M. B, to say that for every morphism F from X into Y in SCH over S, that is for every object of SCH over Y, gamma F, which is a morphism from X into X times SY, is in M. So just what we have said before. The graphs of morphisms with values in Y should be epsilon of M. And C, let's say the following, that for every pair of morphisms, UV of X, some scheme over S into Y, so these are morphisms in SCH over S, of schemes over S, I want that the kernel of the pair UV, which is a sub-object of X, so there's a morphism of this into X. So this here, morphism, should be in it of M. I claim that these three conditions are equivalent. So they kind of show the significance for diagonal morphism to have a certain property. And now, these equivalences are again true, always assuming, we will always assume that these two conditions here, stability under base chain and stability under composition, is true for M. So let's see. So the most intrinsic way of stating things, where there is no quantificator, is just this here, taking the diagonal morphism and here. Let's show that this implies the other's end. Conversely, so we have already seen that A implies B, because gamma F is the inverse image of the diagonal morphism by a certain morphism of X times SY and to Y times Y, and it's F times the identity. So into Y times Y, that's it. I mean, X times the identity, that's it. So let's see that A implies C. Well, in a way, let's prove already the equivalence of A with B and the equivalence of A with C. So we have shown that A implies B. Let's show that B implies A. All right? Because the diagonal morphism can be viewed as being the graph of the identity map, of the identity morphism of X to of Y to itself. Therefore, not only A implies B, but B implies A trivially. Anyway, the universal case, so to say, of B would be the case when we take X equals Y and the morphism F to be the identity. Now let's look at this here, these two. What is a kernel of a pair of morphisms? It can be a pair of morphisms can be viewed as being a morphism of X into the fiber product Y times SY, U comma B. That's essentially the same thing. And the kernel is just the fiber product with the diagonal morphism here. If K is a kernel, we have this Cartesian diagram. And now we see that if the arrow here is an M, then the arrow there is an M. So therefore, certainly A implies C. And why does C imply A? Well, we can say that the diagonal morphism Y goes to Y times SY can be viewed as being the kernel of the pair of the two projections PR1 and PR2 of y times y to S. In other words, the universal situation here is obtained by taking x equals y times y, and the two projections, and expressing C in the universal situation, you get that delta G should be an M. So something which will sometimes happen is that all diagonal morphisms will be an M. And in this case, it will follow that whenever a composite on GF is an M, then also F is an M. So whenever this will happen, we will make it explicit. We'll point it out that all diagonal morphisms are an M. Won't be true for affine schemes. For affine morphisms, I want to say it's not true that any diagonal morphism is affine. Hey, there's a. I think I can give a false. I'm sorry. I spoiled the statement. I can give a false equivalent condition. So you had a y goes into S, I think, and the first condition was that delta G is an element of M. I like to give a false condition. It means that for every S prime goes to S, any base change, we now get the y prime. Well, no, it's the same effect. In disguise, it's the same as, I think, number B. So now we get the Cartesian diagram with the G here and the G prime here. If we take any section of y prime over S prime, call it sigma if you want, for every section sigma, we want that sigma should be an element of M. Well, I mean, it's just the same condition as the condition I think we called B, except that what we called X in this condition is now called S prime. If you remark that to give a section here is the same thing as to the S morphism from S prime into Y. And this here, if you make this interpretation, this morphism, a section, is then just the graph of this morphism. Therefore, to say for M, to say that all diagonal morphisms are an M, amount to saying also that all sections of a scheme over another are an M, S morphisms, but amounts to say that all graph morphisms are an M, or still it amounts to say that all kernels of pairs of morphisms are an M. Alright, so we have four different ways of stating the same property for a set of morphisms. And now we have to give a few examples. So affine schemes satisfy A and B, but they don't satisfy the condition C that all diagonal morphisms are affine. You can make easy counterexamples. For instance, take, so we'll just give a way of making an example. Take, what should I say? Take the complement of a point in the plane and take two copies of the plane that you match together by identifying the complements of the 2 points by the identity morphism. So you get something which looks like the plane except that the origin has been dedoubled. You get something which old-timers wouldn't have considered as an algebraic variety because it's non-separated, will define what it means. When you look at the diagonal morphism for this scheme, it won't be affine. Well, never mind. Now let's see some other properties for morphisms. There are two, make a list here, affine morphisms. There's a very trivial other type of morphism, which we can list. These are monomorphisms of schemes. Maybe monomorphisms in the category, that means also monomorphisms of functors. This is pretty clear that it's stable under base change, that it's stable under composition. That's true in any category. On the other hand, diagonal morphisms certainly are monomorphisms. So if GF is a monomorphism, F is a monomorphism, but no one. I mean, that's true again in any category. So, what about surjective maps? Surjective morphisms of schemes. Don't confuse surjective with epimorphisms. But when I say surjective, I just mean set surjective. Now, of course, surjective morphisms, that's stable, that's transitive if we compose two surjective morphisms, but it's a set surjective affair. So composition is surjective. What about stability under base change? Assume f is surjective, make a base change. Then I claim that f prime is surjective too. Because if you make the set surjective base change, if you take the finite product of the sets s prime and x over s, then of course, for every point here, there exists a point in x above it, a point of s prime above it. And therefore, taking the set, the pair of these points, we get a point of the set surjective finite product over S, over the given point. I'm sorry. So we want to put the surjectivity to this. So let's say if you have a point S prime in here, we look at its image in here, because this is surjective, we can find a point lying above it, let's say X, and on the other hand, we know that there exists an element in this set surjective finite product, which lies above, which is just a pair X S prime, yeah, which lies above X and S prime. On the other hand, we know that there exists a point in X prime, which lies over X and S prime, and this we have seen. That's the X prime mapped into the set surjective finite product is surjective. And therefore, lying over this pair X S prime, of course, lies over S prime. So surjective morphisms are similar to base change. Of course, diagonal morphisms are not necessarily surjective, or sections are not necessarily surjective. So we should investigate what it means for a diagonal morphism to be surjective, but perhaps a little later. So that's another case of properties of morphisms satisfying to these conditions. Now let's look at some things that are perhaps more important for us. Yes.
Example of the one that you mentioned before, or double.
Yes.
Is there an example of what you mean by happy? Does the two conditions hold for epics?
For epimorphisms. Certainly the compositum of epimorphism is an epimorphism, but I doubt very much. That certainly is false. No, it's false. It's a base change in an epimorphism. It's again epimorphism. That's not true. It would be because the notion of epimorphism is not so nice if you take it in the sense of just the category of schemes. When you take it in the category of associated sheaves, you see, of sheaves I mean, and replacing the scheme by the sheaves they define, then it's a nice notion. Otherwise, it's kind of kinky. It's not stable on a base chain. Let's look what it means if you want. If, for instance, we work with schemes that are finite over a field, namely whose algebras A are finite dimensional vector spaces over a field K. Take K algebraically closed if you prefer, by mine. So there are just a finite number of points, and then some artin rings around these points. All right. Then an epimorphism of schemes corresponds to a monomorphism of rings, and in this case, it just means that it's injective. In this case, what the error reversing business suggests is really true. It may not be true otherwise. So an epimorphism here of schemes, an epimorphism within the category of schemes just means that you have something injective here. All right. But now, let's make a base change of this. Take y prime goes to y. Let's take x prime goes to y prime. This means that we have a base change like this. A goes to a prime again finite over k. And we look to what we obtain making the base change. Now, is this here still injective? It is not, in fact, generally, because injective homomorphisms don't stay injective after base change. Take, for instance, a prime, assume that A is an arti-local ring with residual field K, and take A prime to be K to be the residual field. So let's pass to the quotient. So in this case, so that wouldn't be a convex number. But anyhow, it's pretty easy to make counterexamples here. With A prime, of course, not flat over A. So the fact that epimorphisms don't commute with base change just corresponds more or less to the fact that monomorphisms don't commute with tensor product. Yes, of course, to make a counterexample, you see, just use Nagata's cherished principle of idealization. Once you have a counterexample with modules, which is easy enough, I mean, then you have a counterexample with rings by taking just the modules as ideals of square zeros in the rings. Therefore, what you can do, start with A goes to K. You see A being an Artin ring, local Artin ring, and you take the canonical homomorphism from A into K, passage to quotient, and take a module for which take a monomorphism, like for instance M goes to A, then it's known that the corresponding homomorphism M lower K goes to A lower K equals K. It's not a monomorphism, in fact that's zero, because M lower K is just M over M squared, and the map of this into K, the zero map. So you have a homomorphism of modules. N goes into M, which is not injective, which is injective, but doesn't remain so after making the base change from A to K. And now take the direct sum of A plus either the module N or the module M, viewed as being ideal of square 0. Now you have a homomorphism of rings that is injective, and that doesn't remain injective after making the space change. Homomorphism of algebras over A is injective and doesn't stay injective by making the space change. So really, one has to be very careful, therefore, using notions as epimorphisms and related notions which have to do with direct limits, like passage to quotients, that are really in the category of schemes. They don't work so very well mostly. They work well when you work with them in the category of sheaves, rather. All right, now let's define some other notions. The notion of quasi-compact morphism. A morphism is quasi-compact, that's a purely topological notion. Maybe I can erase this now here. Let's assume we F is said to be quasi-compact if, by definition, if for every open subset U in S, subset U is quasi-compact, the inverse image is quasi-compact. So the inverse image of a quasi-compact open subset should be quasi-compact. I should have made another comment about all the notions we are going to introduce. All these notions will turn out to be local on the basis. On the one hand, they are stable under base change, so if you make a base change, S prime goes into S, and if F has a property, then X prime goes to S prime has a property. For instance, if S prime is an open subset of S, then X prime is just a part of X lying over S prime with induced structure sheaf. Then if X over S has a property, X prime over S prime has a property. But there will be a converse. If S is covered by open subsets S prime I, and if all the X prime I's over the S prime I's have the property, then it will be true that X over S has a property. So this was clear in the case of affine morphisms, in the case of monomorphisms, in the case of surjective morphisms. And this is clear also in the case of quasi-compact morphisms, because of the fact that a scheme has a basis of open sets which are quasi-compact, and these are affine open sets. And from this it follows formally that the definition here is local on the basis. In fact, we can say the following: if S is covered by open subsets Si, the Si being quasi-compact, then F is quasi-compact if and only if all of the f minus 1 of Si are, is this so? Quasi compact. Yeah, that's so. Now, we have to prove, for instance, it's necessary and sufficient that the inverse image of any affine open subset should be quasi compact. So the affine open subset is cover S. Alright, so much for the definition. Now we have to check the two properties. We have to check that this is compatible with base change. Now let's reformulate the last property in a slightly different way. If S prime is an affine open subset or a quasi-compact open subset, we want to express that S prime is quasi-compact, but this we can express by saying that X prime is covered by a finite number of affine open subsets. Because anyhow it is affine open subsets, and to say that it's quasi-compact means that it's covered by a finite number of such affine open subsets. Remember that affine. Right. Well, to start with, yeah, U is mapped to G minus 1 U, yeah? Because the composition of this and this is the identity. So if, let's see, what is this? If I have GS is in U, then is it true that, I'm sorry, what is this? Assume that we have a point in U, call it Y. It is true that f of Y is in U minus 1 U. Here. So in other words, it is true that GFY is an element of U. No, it's not here. So maybe we shouldn't care. Alrighty. So, but at least, certainly, X is mapped into S here. And therefore, if you take still an open neighborhood of affine open neighborhood of S lying in G minus 1 U, call it V if you want, then provided we replace U by the part of U lying over V, call it now U prime. We are in the situation where we have a section. Where does this nonsense? Again. What I want to do, you see, is to find an affine open set here, an affine open set there. One containing X, the other containing S, such that this affine open set here, call it U if you want, we have not constructed it yet, lies over V, and that the section is a section of U over V. And I'm getting mixed up, but I know it's kind of trivial by doing the kind of thing I have said. So far. So we started, S was already affine. Alright, we took an affine open set U containing X. We take the inverse image by G. Now maybe U is not mapped into G minus 1 U. That doesn't matter. I take the part of U lying over V, call this U prime, and now, but we don't know yet that U prime is affine. Although it would be pretty easy to prove, I guess. I think I better will make the proof with the diagonals. I think it will come out more easily because you don't have. You won't get mixed up in the various choices of open sets. So we have x over s, and we look at the diagonal morphism x goes to x times sx, and we want to prove that this is an immersion. Now let's cover x by, we can already assume of course that s is affine because the story is, the question is local over s, so assume s affine now. And x is covered by affine open sets, each xi affine. That's it. And therefore x times x is covered by the fiber products xi times xj over s. And now what is the inverse, so which can be viewed as being open subsets of x times x, namely the intersection of the inverse image of xi and of xj by the first and second projection respectively. Alright, and now by this description, what is the inverse image of this open set in x? That's just xi intersects xj. So what I have to prove is that xi intersects xj mapped into this fiber product is an open immersion. Is an immersion, I'm sorry. Because the property for morphism to be an immersion is local on the target. So I have to prove it over every one of these open sets. Now we can view xi intersects xj, call this what you all know, call this z for the time being, I and j now are fixed. Alright. Now z is mapped first into z times sc, and then because z is mapped into each xi and xj, it's mapped into here. But this second morphism is an open immersion. Because z is both open in xi and this z is open in xj. And therefore all we have to prove is that this here is an open immersion. So now we are reduced to the case when S is affine and Z perhaps is not affine because we don't know that's the intersection of two affine open sets of X are affine, but Z at least is contained in an affine. Alright. Namely in XA or XJ. Now I cover, so let's now forget about the XIJs. We now just assume that X is contained in some affine. X prime over S. And now I cover X by affine open sets, Xi as before, but with the benefit that now I know that the intersection of affine open sets, X being affine open sets of X prime, are affine. If I don't want to admit this fact, which we will see a little later with this generality and even more, let's say that we can take as affines in X open sets of the type X prime lower f, where f are elements of the rings of X prime. Because these open sets make a basis for the topology of X prime, and therefore those which are contained in X make a basis for the topology of X. And the intersection of two such open sets, X prime F and X prime G, is again of the same type. Alright, therefore I have affines now in X, such the intersection of two such affines is again affine. And now, if I make the same reduction as before, in this situation I see that I'm reduced to proving that if Z is an affine open set of X, it would be the intersection of an XF with an XG, X prime F with an X prime G. Then the morphism which goes from the diagonal morphism which goes from Z into Z times SZ is an immersion. In fact, in this case, it will be a closed immersion. Because now we can make everything explicit in terms of commutative algebra. S corresponds to a ring A, Z corresponds to an algebra B over A, and the diagonal morphism corresponds to the homomorphism of rings. B tensor B goes into B, which makes X tensor Y into XY. So there was a slight trickiness in order to the case of affines. In all these statements, of course, we always have to get back to the affine situation, our models. as a consequence of this, as of what we have said, the diagonal morphisms are inversions. We see the following thing, that if GF is an inversion, I mean that's just an equivalent statement again, GF an inversion implies that G is an inversion. I hope that I stated this as an equivalent condition to the condition that diagonal morphisms should be in our class of morphisms. It's also the same to saying that if GF is in the class, then F is in the class. First one is in the class. To check that F, a given morphism, is an inversion, you can follow it by another morphism. Look at the convolution. If the convolution is an inversion, then F already was one. No, I understand. I didn't state this general effect. I didn't. At least I think we have seen it as that it implies this, and the converse is true, because look at the diagonal morphism x goes to x times sx. If I follow it with one of the projections, I get the identity, which is an m. And therefore, this must be an m. So I mean, it works in the two ways. The property that the diagonal morphisms are in the class is equivalent, not only implies that gf in the class implies f in the class.
Could you quickly, just since we've got listing here, go through and just remind which is which? We've got immersions are closed on the composition, base change, and diagonal morphism. The immersions are closed on the composition, base change, and diagonal morphism.
Yes.
Could we just list these through which of all of these classes are satisfy one or more of those properties?
Well, all classes that we are working with are stable on the composition and base state.
Okay, every single one.
And they are local on the basis always. So this one's are local. We won't study any class that didn't have these properties. The base change really is the most important thing, but the classes we are studying at present are also stable under composition. All right. Then for some of these things here, it is true that all diagonal morphisms have the property. This is true, but here there are not so many yet. It's true for monomorphisms, it's not true for affine, it's not true for Grothendieck, it's not for quasi compact. Almost true for all useful things that we are working with. It will be true. Finite type is not true, same reason. Locally of finite type neither. Locally of finite type, yes, but it's kind of trivial, you see, because a quotient algebra is a finite type over the quotient of the ring by an ideal is a finite type over the ring. Alright, so locally of finite presentation is not true because the diagonal ideal may not be a finite type. For open immersions it's not true, for closed immersions neither. It would be true only for separated morphisms, and for immersions it's true. So the extra property is satisfied for the time being for these here. Maybe we should see under which conditions an immersion is locally of finite presentation. We have already remarked that they are always locally of finite type. All right. So if we have an immersion x goes into y, it can be viewed, as we have said, as being a closed immersion in some open set. And therefore it's defined x as v of j, where j is a quasi-coherent sheaf of ideals on y. On U, I'm sorry. Now, the morphism F is locally of finite presentation. always locally of finite type, but it's locally of finite presentation if and only if this sheaf of ideals J is of finite type, which means that locally it can be generated by a finite number of sections. Because in the affine, we are reduced at once to the affine case by definition, and that just means that if we take the quotient of a ring by an ideal, then this quotient is a finite presentation if and only if the ideal is of finite type. And then let's make it, in this connection, let's make a little statement, which is that if f is locally of finite type, then the diagonal of f is locally of finite presentation. You remember the significance of a diagonal having certain property, being in certain class, also means that it is this statement is equivalent to saying that if we have a morphism locally of finite type, then any section is locally of finite presentation. Or it also means if x over s is locally of finite type, and if you have two S morphisms, u and v of z into x, and if you take the kernel of this pair, and if you look at this morphism from this kernel into z, then this will be locally of finite presentation. It's an immersion, which will be locally of finite presentation. Now let's prove this fact. So, well, let's prove it in the term of diagonal morphism as it's stated here. We have x over s, and want to prove that the diagonal morphism x goes to x times sx is locally of finite presentation. I can assume already s to be affine, and clearly the question is local on x, you see. You just viewed by doing as before by covering x by xi's, so that this here will be covered by xi times sxj's. And here then we have xij's, and we have to prove that these are local of finite presentation. And then we covering then, and of course open immersions are local of finite presentation, so I call this C. I'm just reduced to proving that C goes to Z times SC is locally of finite presentation. And again I cover Z by affines as before, I'm reduced to the case, and everything is affine. Alright. And in this case, the situation boils down to the following. I have an algebra B over A which is of finite type, which expresses that x over s is locally of finite type. And I look at B tensor B goes to B by product, x tensor y goes into xy. And I claim that B is of finite presentation over this algebra. In other words, that the ideal I here is of finite type as an ideal in this ring. And for this, we use the following thing. If B is generated by elements Bi, and whether the number finite is finite or not, then if you look at Bi tensor 1 minus 1 tensor Bi, they generate the ideal I. That's an immediate exercise to check. This essentially means in terms of universal problems that in order that two morphisms of B into an A algebra C should coincide, it's enough that they coincide on the generators. That's what it means really. It's almost topological. In other words, in order that a morphism from this into some C vanishes on I, it's less than sufficient that it vanishes on these elements, which means that I is generated by these elements. Alright, so this shows that if B is generated by a finite number of elements, then as an algebra, then I is generated by a finite number of elements, and these as an ideal. Alright, so this is kind of amusing. Play around. Yeah. All right, so I think that's all we have to say about immersions. So let's remember that immersions are something that one meets all the time in algebraic geometry. For instance, whenever we have a section of a scheme of another, it's an immersion. Whenever we have a kernel, the embedding is an immersion. Many of the monomorphisms one has to deal with in algebraic geometry are immersions. Now we come to separation motions. Perhaps we could underline those notions here which are always satisfied for old-time algebraic geometry. Everything is quasi-compact, everything is a finite type, everything is locally finite type, everything is locally finite presentation, but everything is not an open immersion or closed immersion or an immersion, however. Not quite true. Almost. Well, it's almost true. But there are, of course, morphisms which are not monomorphisms. So, all right. Now, let's take a separated morphism. And this, again, will always be true for the old-time algebraic geometry. Now, we will say that f from x to s is separated if and only if delta f, the diagonal, which goes from x to x times sx, which is already an immersion, is a closed immersion. Now it's pretty immediate to see that an immersion is a closed immersion if and only if the image of this immersion, which is a locally closed subset, is in fact closed. It est delta f of x is closed in x times sx. Now, we have already stated in several ways what it means for a diagonal morphism to have a certain property to be in a class M, a class stable under base change and composition. So, this means also that for every s prime over s, if we look at the morphism deduced from f by base change from x prime into s prime, then for every section g of x prime over s prime, g, which is therefore a morphism from s prime into x prime, is a closed immersion. Or what amounts to the same, its image is closed. And still another way of stating it, so this can be also expressed by saying that if you have a morphism of an object s prime over s into x, or call it y over s now, that if you have an s morphism of y into x, then its graph over s is closed. That's just the same thing as here essentially. And still another way of stating things is by saying for every pair of morphisms u and v from y into x, s morphisms in SCH over s, the kernel of uv mapped into y is a closed immersion. In other words, the kernel is a closed subscheme of y, not just a subscheme of y. So all these are equivalent ways of stating the property of being a closed immersion, of being a separated morphism. The last property can be viewed as being it's something which can be viewed as being a prolongation principle of identities. I will make it clear, prolongation principle of identities. Therefore, I will give a reformulation of this in the following way. let y be reduced, y over s be reduced, and of course in this property here anyhow nothing changes if y is reduced, because topologically y has not changed if we divide it out by the important elements. So in this criterion anyhow there is no trouble restricting to the case y reduced. Now the consequence I'm going to state is that y over s be reduced, and let u and v be two morphisms, S morphisms from y into x, such that u restricted to some open set u is equal to v restricted to the same open set u, with u open in y, let's say, open in y open in fact. No. Well, let's state it like this, we will make a remark as to how to generalize it in an obvious way. Open in y and dense in y. So we have two S morphisms. From y into x that coincide in a dense open set. And then the conclusion is, if we assume x to be separated over s, you see, if these equal conditions hold, that u is equal to v. If u and v coincide in a dense open set, u equals v. Now let's show that this statement here is a consequence of this here, namely of the separation of x over s, because we know that the subscheme of coincidences of y is a closed subscheme of y. But and as a subset of y, it's just a closed subset of y with a certain structure on it, certain structure scheme on it. But now this subscheme contains u as subobject, and therefore as a subset it contains u being everywhere dense, and the subset being closed, the subset must be equal to y. On the other hand, because y is reduced, a subscheme of y that theoretically coincides with y must be equal to y. Maybe we should give this as a little compliment here about surjective immersions, so that we know that the subscheme of a reduced scheme that is theoretically everything is a scheme. But once we admit this, then it follows that the kernel of the pair uv is equal to y, it's the whole of y, which means that u is equal to v. And in fact, the same argument would work whenever, instead of having an open subset u of y, if you have a morphism from u into y, such that the image of u and y is dense, and if we assume, I call this morphism I, it need not even be a monomorphism, then assuming that I of u is dense in y, and assume that u composed with I is equal to v, composition with I, then this together must imply that u equals v. Argument is the same. The subscheme of coincidences of u and v is a closed subscheme that contains as a subset the image of u, therefore it must be equal to the whole of y set, and therefore it must be equal to the whole of y because y is reduced. Now let's make here little parentheses, and let's look at what are the immersions f goes into y which are surjective. So if being surjective, there must be certainly closed immersions because the image must be closed. Now if we cover y by affine open subsets yi, then the fact that f is a closed immersion is expressed through the fact that the images of the yi's, called them xi, are affine schemes, and xi goes to yi is a closed immersion. In other words, on the rings we have ai goes to bi surjective. xi is just the spectrum of a quotient ring of ai divided by an ideal. And what does it mean if you have a homomorphism of rings, surjective in this case? Yes, that the corresponding morphism for the spectra is an isomorphism. That just means we have seen, I'm sorry, that the morphism of the spectra is bijective. That means just that the ideal by which we have divided out here, Ji, defines as a corresponding closed set for the Zariski topology, defines the whole set, which means that Ji does the same thing as would do the zero ideal, which means that every element in Ji is nilpotent. That means that Ji is a nil ideal. Now, if you come back to the sheaf of ideals J and Y, crazy coherent sheaf of ideals, that defines X as a closed subscheme of Y. This just means that J is a nil ideal, and that means that any section of J over any open set of Y must be locally nilpotent. So over any quasi compact open set, it must be nilpotent. Now, if Y is reduced, this just means that the biggest, that in fact means that the nil radical of the sheaf of ideal is the largest sheaf of ideals, which is a nil ideal, and which turns out to be quasi coherent because of the affine dictionary. That this just means that this sheaf is zero, and therefore any nil ideal in OY must be zero. That means that at surjective closed immersion, surjective immersion must be an isomorphism. So we have defined the notion of a separated morphism in various disguises. So there are various ways of visualizing it. There are some more, but by the way, we have also, it's not hard to check that we have also the implication in the other direction. I want to prove it here. That's the prolongation principle, so that it holds for X is necessarily sufficient for X to be separated over X. Now, here, it's pretty clear that every monomorphism is separated, because a monomorphism is a morphism for which the diagonal morphism is an isomorphism. And isomorphisms are always in the classes we are working with. So, all monomorphisms are separated, and a fortiori all diagonal morphisms are separated. Therefore, we are now in a typical situation when we know that if GF is separated, if GF has a property and it being separated here, then F also. In terms of relative schemes, we will say if you have a morphism from X to F, so that X becomes a scheme over S, instead of saying that the morphism F is separated, you will see that X is separated over S. And what we have said here is the following: if X is separated by S, and if you have an S morphism of X into any Y, then X is also separated over Y. Because the compositor being separated, this one is separated. So therefore we can encircle this. Diagonal morphisms are separated. Now, what about absolute separation? Well, any scheme can be viewed as lying over the spectrum of Z, and therefore, whenever we have a relative notion for morphisms of schemes, that is, notion for relative schemes, we can make it absolute by saying that X has a property, M, let's say, if the structural morphism from X to spectrum of Z has this property. So we will say that the scheme X is separated in the absolute sense, if and only if X is separated over spec C. Now, assume that X lies over scheme S, and let's assume that S is separated itself. Now, for instance, S affine. Maybe we should check that an affine scheme is separated. If you have an affine scheme, then it's defined by ring A algebra over Z, and the diagonal morphism over Z corresponds to the homomorphism from A tensor A into A. Now this is surjective, which means that in opposite direction diagonal morphism is a closed immersion. So affine schemes certainly are separated. So I assume that now that X lies over any separated scheme, for instance over an affine scheme. I assume that X, for instance, is a K scheme, where K is some commutative ring. Then I claim that X is separated in the absolute sense if and only if X is separated over S. So in this case, the relative notion over S is the same as the absolute notion. Now that's quite clear. If X is separated over S, if we assume S to be separated over spec C, then by transitivity X is separated over spec C. On the other hand, if X is separated over spec C, we have seen, because of this here, that X is separated over anything lying over Z, whether S is separated or not. Now I should give an example, before giving a counter example of schemes that are not separated. And they're quite a dressing one, by the way. You shouldn't think that non-separated schemes are really pathological. I mean, in very nice geometrical conditions we meet, like Picard schemes and such things. We meet with schemes that are not separated. First, the old-timers didn't want to consider them. But before giving an example, let's state some more things. Yes. Let's state the following thing. If X is separated, a separated scheme, in the absolute sense now, namely separated over spec Z, and if Y is an affine scheme, call it rather S perhaps here, S is a separated scheme, and if X is an affine scheme, and if X lies over S, if you have a morphism from X into S, then F is necessarily affine. So X affine, S separated, implies that the morphism F is affine. What does it mean? That means for every affine open set of S, the inverse image in X is affine. In fact, we can also state it in a more symmetric way. Instead of taking an open subset of S, just take an affine scheme, Y, that lies over S. And what we want to prove is that the fiber product, X times Sy, is again affine. Because if this would be affine over S, then this would be affine over Y, and Y being affine, this would be affine. So, what I have stated here, this theorem, or proposition, I mean, it will come out pretty trivially, is equivalent to the following. If X and Y are both affine, and if they lie over S, which is separated, then X times Sy is affine. Now let's prove this. How do we get X times Sy? We get it by taking the absolute product X times Y in the case of all schemes, namely schemes over Z. This is mapped into S times S. And we take the diagonal morphism here. And the fiber product of this and this over S times S, that's the inverse image of the diagonal, which is the monomorphism here. In here, that's just the fiber product. Alright, now this I know to be affine. That's the absolute construction of products of affine schemes in terms of tensor products of their rings over Z. So this here is affine. Therefore, in order to prove that X times Sy is affine, this amounts to the same to saying that the morphism here is affine. So is this morphism here, is this morphism from the fibered product to the absolute product affine. This would be so if we knew that the diagonal morphism here is affine, because by base change, then this would be affine too. On the other hand, if it's a closed immersion, it's certainly affine. And as a particular case, we see the corollary. If U and V are open subsets of S, and U of V affine, S being separated as before, then the intersection U intersects V is affine again. In a separated scheme, the intersection of two open affine sets is again affine. And now I think I'm ready to.
What about the converses too? The converses too?
No, because this made just use of the fact that the diagonal morphism is affine. But take the line over here, let's say, and do as before, dedouble the origin by taking two copies of the line and matching them together by taking the identity isomorphism between the complement of the origin. Now this is a typical example of something which is not separated. And however, the diagonal morphism I think is affine because its inverse image on the two pieces is the complement of a point in a line and it's affine. So maybe I should be more thinking about this. Look at the scheme E1 and take two copies of this, x prime and x second, let's say, and now take the zero section of E1 over any scheme S. I mean E1, I take E1S, the affine line over S. It's vector bundle over S of rank 1 if you want. So take the complement of the zero section. Viewed as an open subset of x prime calls x prime star, and as an open subset of x second calls x second star. And takes the identity morphism between these two, and now glue together x prime and x second according to this isomorphism between the open subsets. Then I claim, so call this x, this thing obtained by gluing together, call this x. So it's the union of x prime and x second, and the intersection of x prime and x second is just x prime star or x second star, viewed as lying in x prime or x second in the way explained. Now I claim that this is not separated over S, and therefore theory it's not separated in the absolute sense. Take for S if you prefer field over spectrum over field. Doesn't make any difference. Well, let's see. In fact, we will show that it doesn't satisfy to the prolongation principle, because now I will define you two morphisms from call this C here E1 into X, U and V, that will coincide on Z star on the complement of the zero sections that will not coincide. In fact, I take for one of these morphisms I map E1 Z into X prime by the canonical isomorphism, and the other I map Z to X second by the canonical isomorphism. And of course, the two morphisms U and V are not the same because their image is not the same, at least if S is not empty. The union of the images is everything, but none of them is surjective. All right. And however, they coincide on Z star, which is an open subset of C, which is everywhere dense, as you will easily see. All right. So it's not separated. However, the diagonal morphism in this case, as you will easily check, is, well, why shouldn't we check it now? Let's check that the diagonal morphism, however, is affine in this particular case. So X is covered by, maybe we rather call them, to be faithful with our previous notations, X1 and X2, the two pieces. So, therefore, X times Sx can be viewed as being the union of X1 times Sx1, X1 times Sx2, X2 times Sx1, and X2 times Sx2. That these are just all xi times sxj. Perhaps it's easier to write it like this. And so these cover x times sx, and if I look at the diagonal in here, then the inverse image of this open subset, as we have already noticed, is xi intersects xj. And to say that the diagonal morphism is affine just means that these morphisms here are affine. To say that diagonal morphism is closed, which it isn't, would mean that these here are closed, and you will check again that these morphisms are not closed. Now, for I equals j, there's no trouble in fact. Then we have xi mapped into xi times sxi, and xi is just, isomorphic to E1, it's something perfectly separated, so we have a closed immersion, which is affine. So there's something interesting going on for I different from j. Therefore, for I equals 1, let's say, and j equals 2, or the opposite. So here, x1 intersects x2. That's just what we call Z star here. And now, xi and xj, they are both isomorphic, S-isomorphic, to Z itself, in fact, by character isomorphism. Therefore, this tensor product is just, this conjugate product is just isomorphic to Z times Z over S, which is just E2, standard affine space of dimension 2 over S. And Z star is mapped into Z times Z by taking the two components, their inclusion of Z star into this vector and the inclusion of Z star into this vector. And therefore, we see that this, I'm sorry, that's not nice, that this morphism from Z star into this private product is just obtained by first mapping Z star into Z by the inclusion, and then mapping Z into Z times SC by the diagonal morphism. Alright, so we have everything well in hand here. Now this here is a closed immersion, because Z is affine over S and therefore separate over S, closed immersion. Therefore, Z star goes to Z is a closed immersion if and only if Z star goes to this is a closed immersion if and only if Z star goes to Z is a closed immersion, which it isn't. It's an open immersion, but the image is everywhere dense. The image is not the whole of S. Of Z. So we see again that the morphism is not separated. But in order to show that the morphism is affine, as this already is affine, we just have to check that Z star goes to Z is affine. But that's clear because Z is affine over S, and Z star is affine over S also. It's in fact the multiplier of group over S. So both being affine over S, the morphism from Z star to Z is affine. This is clear. Alright. Therefore, the condition that intersection of open subsets be affine, which just means that the diagonal morphism is affine, is not sufficient for ensuring that the morphism is separated. And now, let's however give examples of morphisms where the intersection of two affines, of schemes where the intersection of two affines is not affine. So, we just take a scheme over anything, or a field, or an affine scheme, let's say. And if we take the complement of the zero section, then So it's hard to show that this complement is not affine. You see, if you take the complement of the zero section and affine space of dimension 1, this is affine. But if you take affine space of dimension at least equal to 2, the complement of the zero section is not affine. Alright, so we start with this, and now we do as before. We take two copies of x, x1 and x2, and we match them together according to the common intersection, which should be u. So x is the union of x1 and x2, and x1 intersects x2 should be equal to u, which I view as being open subset of x1 and x2 in the obvious way, both x1 and x2 being identified to x here. Alright, so for the same reason as before, x is not separated, but even more so, x1 and x2 are both affine open sets of x because, I'm sorry, call it not x, call it x there. Maybe we call this x here, we call it z as before. Alright. So this x here has in fact two open subsets, x1 and x2, which are affine because they are isomorphic to z. In the intersection, it is isomorphic to u, it's not affine. Now these schemes, they're not so tautological after all. I mean, the construction is extremely natural. And you actually do meet such kind of schemes as representing some very natural functions that are having very definite relative meaning. So I think they shouldn't be despised. But now, so even making algebraic geometry of finite type over a field, you see, after a while, one will likely meet such non-separated schemes. But now we come to a variant of the separation notion, a very, very weak variant, quasi-separation. A morphism f from x to s is said to be quasi-separated. Now we will ask only that the diagonal morphism is quasi-compact. And here again, this can be formulated in various different ways. It means also that for every base change s prime goes to s, and every section g of x prime equals xs prime over s prime, the section g should be quasi-compact. So we want that sections of x over s should be quasi-compact, and the same should hold after any base change. And again, this is equivalent with saying that if whenever we have two morphisms over S from a scheme Y into X, U and V, let's say, then the kernel of UV morphed into Y, that this morphism here is quasi-compact. That the kernel of U and V is quasi-compact over Y. We can formulate things in a way perhaps which is more immediately topological, which shows that this property doesn't depend really on the scheme structure, but only on the topological space. No, I'm a little tricked perhaps. No, that would be for the absolute notion. Let's leave it at this for the time being. Of course, a separated morphism is quasi-separated because a closed emulsion is certainly quasi-compact. That's pretty clear. And therefore, so a monomorphism is quasi separated. And therefore, any diagonal morphism is quasi separated. A diagonal morphism may not be quasi compact, but it certainly, as a monomorphism, is separated, are forcefully quasi separated. And therefore, you get that if GF, if the compositum of F is something else is quasi separated, then F is also quasi separated. So provided X, now therefore we introduce also the absolute notion. A scheme X is said to be quasi separated in the absolute sense, not over something, but just in itself. If and only if X is quasi separated over spec Z. Namely, which means also that the diagonal morphism X goes to X times X. Here now is the absolute product of schemes. Product over spec Z is quasi compact. And then we see, as before in the case of separation, that if S is quasi separated scheme, let's say the following: if X is, first of all, if X is quasi separated, in the absolute sense that it's quasi separated over anything over which it lies, that comes from the fact that GF quasi separated implies F quasi separated. So the absolute notion of quasi separation implies the relative notion, whichever way you send X into something. And on the other hand, if S is quasi separated already, and if you have an X lying over S, then X is quasi separated in the absolute sense, if and only if X is quasi separated over S. Just as before, if X is quasi separated over S, S being quasi separated over spec Z, X must be quasi separated over spec Z, namely in the absolute sense. So therefore, this implies this, and we have already seen that this implies this, even if S was not quasi separated. Now, really, all schemes I have seen anybody working with, or I have worked with myself, are quasi separated, or it amounts to the same essentially. All morphisms that one has worked with so far are quasi separated. So that's really a very weak notion. Let's, however, show that there are examples of non-quasi separated morphisms or non-quasi separated schemes. And for this, again, let's state the notion of quasi separation of a scheme in a purely topological way. A scheme is quasi separated if and only if for every two open subsets U and V and X that are quasi compact, the intersection U and V is also quasi compact. So quasi separation just means in the sense that the intersection of two open subsets which are quasi compact is again quasi compact. So the dreadful thing to happen is not so much that the intersection of two affines is no longer affine. The dreadful thing to happen is that the intersection of two affines, which form the natural basis of quasi-compact nice open sets, that such an intersection may be not quasi-compact, that you couldn't cover it by a finite number of affines, that you couldn't take an infinite number of affines. Now let's prove this statement, and let's give it still another apparently more general formulation. X is quasi separated. Let's call it S rather. Perhaps. If the following holds, if for every scheme X that is quasi compact, and every morphism F from X into S, F is also quasi compact. So, before proving this, I will state something which, in fact, will be apparently stronger. That if you have a scheme lying over S which is crazy compact in the absolute sense, then it's crazy compact over S. And when we apply this here to the situation when X lying over S is just a crazy compact open subset of S, then to say that F is crazy compact just means that the inverse image of any other V, crazy compact open subset V in X is crazy compact, but this inverse image is just the intersection. So this here is just a particular case of this. Then we have when X goes to S is an open immersion. And now what does this mean that F is crazy compact? Just means, as we said, that for every open subset Y of S, the inverse image of X of Y and X is crazy compact. But let's state it in a way, in appearance, still more general, although it's equivalent. It means that if Y is any crazy compact scheme, and if you have a morphism from Y into S, then the fiber product, X times Sy, is crazy compact. Certainly, this is more than enough for ensuring that F is crazy compact, because we have only to take open immersions, but the converse is true too, because if this is crazy compact, then by base change what we obtain is crazy compact. And if Y is crazy compact, this would be crazy compact. And therefore, our statement here, our second statement is just equivalent to the following, that if X and Y are crazy compact in the absolute sense, and if they are mapped to S, X goes to S and Y goes to S, then the fiber product X times Sy is crazy compact. So let's prove that S crazy separate implies this statement or this equivalent statement, and then the converse. Alrighty. Alright, I just do as before. I express the fiber product in terms of the absolute product, X times Y, by, what is this? Mapping this absolute product into S times S by F times G, and looking at the inverse image of the diagonal. Now, if S is crazy separated, this diagonal here will be crazy compact morphism. Will be crazy compact over S times S. This here is crazy compact. Therefore, this morphism from X times Sy into X times Y will be crazy compact. So it's just the argument as before, but crazy compact replaces affine. Now, if X and Y are crazy compact, then their product, the absolute product, must be crazy compact, because X and Y are covered, each of them, by a finite number of affines. Therefore, the product is covered by the X times Y is covered by the X Y times Y, Xi times Yj's, and these are crazy compact because they are affine, because absolute product of affines are affines. Therefore, this here is crazy compact, and X times Sy being crazy compact over something crazy compact must be crazy compact. The inverse image of the whole thing, which is crazy compact, must be crazy compact. All right. So S crazy separated implies this very strong thing, and let's go that if this apparently less strong thing is satisfied, then X is crazy separated. I think that's pretty clear, because S can be written as the union of open subsets Si that are affine, and are for theory crazy compact, and therefore S times S is just the union of Si times Sj, which are also crazy compact. In fact, they are affine if you take the Si as affine. Alright, now we have here the diagonal morphism S goes to S times S, and the to say that this diagonal morphism is quasi compact just means that the inverse image in S of these partial products that cover S times S are quasi compact, but they are just Si intersects Sj. So in fact what we have proved is the following. If S is covered by a family of quasi compact sets Si, whether affine or not, doesn't matter, then S is quasi separated if and only if the mutual intersections of the Si's are again quasi compact. So we really like this to be true. If it's false, really, then one would run into a lot of trouble. Fortunately, one hasn't really met so far with objects where it's not true, but one can construct doing things, you see, exprès. It's pretty easy to construct an example. Doing things sheer malice. One can construct quite easily an example of something which is not quasi separated. Because take a scheme, you could call it Z as before, which is affine, let's say, and therefore quasi compact. And let's assume that there is an open subset U in Z, which is not quasi compact. Now that's not hard to construct, of course. You couldn't do this with affine schemes, with Noetherian schemes. Of course, because an open subset of a Noetherian space is Noetherian. But take, for instance, something like, for Z, take a ring of polynomials, the spectrum of the ring of polynomials in infinitely many variables. Ti, let's say. And so we have the spectrum of this and takes the complement of the origin. It's pretty trivial to check that this is not quasi compact. This just essentially means that we don't, that the ideal generated by the TIs in this here, K being, let's say, a field or any non-zero ring, that this ideal cannot be generated by a finite number of elements, or that we can find, if we have an ideal which is contained in it, which is generated by a finite number of elements, it's not true that any of the TIs has a power which lies in the ideal. If you have an ideal which contains all power, which contains for every Ti some power of Ti, this ideal, and if this ideal is contained in the maximal ideal generated by the Ti's, this ideal cannot be finally generated. 1 minute, easy checking. Fine. So taking some big non-Noetherian rings, one can construct such a situation, and now I just do as before. I take two copies of Z, x1 and x2, and I take their union, but these being glued together according to the common intersection equal to U. And now in the scheme X, I have x1 and x2 which are affine, let's say, and therefore quasi compact, and the intersection is U, which is not quasi compact. Now this makes a lot of trouble, working with such schemes. But would make a lot of trouble. One doesn't have to face it. Fortunately.
Is there a condition that you can have to quasi-separated, get separated something like? What sort of conditions can you have quasi-separated to get separated? Natural condition.
To add on upon quasi-separated order to get separated morphism, I don't see anything else but the definition we know already. Let's see. Well, no, let's see. No, I don't see anything really useful. Question is knowing whether there is a certain morphism. It's that an immersion is quasi compact. Does it make it any easier to check that it's a closed immersion? In other words, that the image is closed. Maybe then it would be sufficient to check that it's stable under specialization. But of course, we are here really working for non-Noetherian schemes, you see. Otherwise, there would be no problem. But no, is it true? Possibly so. I have not seen any such criterion stated and used. And now we can give some converses of properties of the type if GF is element of M for some class of morphisms M, that then with a slight extra condition on G, that then F is an M. And the very slight extra condition, with respect to always satisfied, is that G is quasi separated. It asked, to recall what it means, delta G is quasi compact. And therefore, if M is a class of morphisms which contains, now on the other hand, delta G we know already, is locally of finite type. Any emulsion is locally of finite type. And therefore, being quasi compact, it is in fact of finite type. That's the same, that's equivalent to say that the diagonal morphism is quasi compact of finite type. Therefore, if M contains all morphisms of finite type, then to say that G is quasi separated implies, implies, yes, that's it, that delta G is an M. And therefore we can conclude that F is an M. Therefore, what I said is true if we take the notion of quasi-compact morphisms or of morphisms of finite type, or that's it, or what else? If F is, let's give these two, yes. If GF is quasi-compact, then F is quasi-compact, and G is quasi-separated, which is a very weak condition indeed, then F is quasi-compact. If GF is of finite type, and G quasi-separated, which is an exceedingly weak condition, then F is of finite type. Now, let's see. Let's now look at the conjunction of some of the previous properties. We have coherent morphisms. A morphism is said to be coherent if it is quasi-compact and quasi-separated. That means that both F and the diagonal morphism delta F are quasi-compact. Now, this terminology, coherent morphisms, has not been introduced into certain literature, I think, of algebraic geometry for morphisms of schemes so far. What people will say all the time is quasi-compact and quasi-separated. There are lots of quasis, it sounds very unpleasant. And now this is a condition on schemes or on morphisms that enters into a great many of statements. It's in fact some pretty important technical notion on schemes, and in fact quite analogous notions we meet in the study of topoi. We have coherent morphisms of objects in the topos and coherent objects of the topos, etc. And the formal properties are just work the same in the general context of topoi as here in the special context of scheme. In fact, the special context is really a specialization of the general style. So it is really worthwhile to have a simple terminology for this notion. So we just say coherent, whereas there is no quasi any longer. Praise is kind of pejorative, and it shouldn't be thought of as being something pejorative to be coherent. It's just really among the very weak kindness conditions, it's the one which is what really gives us a lot of things. We will give a few examples. Of course, because crazy separation and crazy compactness are stable by base change and by composition, the same is true when we compose these two notions for coherence. All right. What about diagonal morphisms? They need not be coherent. They will be coherent if a morphism is crazy compact. If a morphism is crazy separated. So you see therefore that GS is coherent, and if moreover delta G is coherent, which just means that G is crazy separated, then F is coherent. That means that from GF coherent one can practically conclude that F is coherent, except that the second one should be crazy separated, which is extremely weak. So we make a dotted circle around to indicate this. Here we are also coherent in the absolute sense, as scheme is said to be coherent if it is coherent over the absolute basis, spec Z, what amounts to the same if it is both crazy compact and crazy separated. Yes?
If you have that backwards, GF is coherent, shouldn't it be that F is quasi-separated? Implies G is coherent?
If GF is coherent, yes, and F
Right.
crazy
I'm
separated,
asking, do you
no, if takes the empty, take as the source of F takes the empty thing, you see, then a morphism of the empty thing into anything has all properties. But from this we can conclude that G is anything. You see, let's G be from X to Y, let's say, and you want to conclude nice things about G, but from knowing something about the GF, but takes the empty scheme mapped into X by F. So in order to conclude something on G, knowing something on GF, you should know that F has an image reasonably dense in X, you see. I mean, that the image is kind of large in X. So certainly you wouldn't like here to have the empty scheme. So we have coherent schemes in the absolute sense. And as before, we see that if you have a coherent scheme in the absolute sense, then it is coherent over any crazy separated scheme, so practically over any scheme. If X is coherent, and if X is a morphism, if you have a morphism from X into S, if you assume only S to be crazy separated, which is practically always satisfied, then F is coherent. And in fact, the converse holds true. If S is crazy separated, X is coherent if and only if F is coherent. So for all practical purposes, as the scheme here working with will be always crazy separated, although many will not be crazy compact. For all practical purposes, to say that X is coherent in the absolute sense or in the relative sense will be essentially the same thing. Now, let's finish for today with just one statement of a typical theorem about coherent morphisms, which is very often useful. It is the following: assume that the coherent morphism X goes to S, and then F be a modulo on X, which is crazy coherent. So the crazy coherence for sheaves of modules doesn't have too much to do with crazy coherence of morphisms of schemes or of schemes. Coherence has. The coherence notion for modules can be viewed as being a particular case of the general coherence notion in categories or in topology, but crazy coherence is another funny notion. Alright, never mind. Then the direct image of F, which is a sheaf of modules on S, is also quasi coherent. And in fact, for those who know some homological algebra, if it takes the higher direct images of F in the sense of an array, then these are also basically coherent for every I. So maybe we will prove this tomorrow because the proof is kind of pretty and easy, and the statement is very, very useful. So we'll start with a few things about, more related to algebraic groups, a few things about schemes over fields within 10 or 15 minutes again. Or like being connected, which is a purely logical notion. Now, this absolute notion is for x, which doesn't depend on the presence of any ground field, is generally not stable. Then we make a field extension, xk prime. And therefore, one has to look at the corresponding notions which are obtained by demanding that for every field extension, the notion we have just set, the property we have just set, for instance, x being connected, should be true. So not only that over k, it should be true, but also over k prime. And this can be phrased in several alternative ways. In fact, when we assume over fields in this relative situation, the properties that are really interesting for us, which we call so-called geometric properties, are those which are stable under ground field extension, so that x has a property over k if and only if xk prime has a property over k prime. This for any given k prime. So we are going to transform properties that are absolute, that are stable under base change, into properties that are relative to ground field, that are geometric properties. By geometric, we essentially mean properties that are expressed over what happens when we replace the ground field k by an extension that is algebraically closed. So we are doing things geometrically, and we are working in a certain sense over an algebraically closed field. Whereas when we are working over a subfield of an algebraically closed field, which is not yet algebraically closed, we view this as a study of the scheme x over k. In the absolute sense, however, we view this as being of a more arithmetic nature, because for some subtler notions also, and also for some, in a way, the reducibility notion is a subtler notion when we take it absolute, then we take it geometrically. So let's now do things specifically. I will freely use certain number of results of commutative algebra, of field theory especially, that we will state as comes on. So let's first speak about separability, which will be the geometric version of reducedness of a scheme. The scheme being reduced, namely the structure sheaf having all the important section of the structure sheaf has to be 0 over any open set. Alright, so here we have to start with some statement about field theory. Let K be a field. I want to give equivalent formulations for a field to be perfect, because it's over a perfect field that the absolute notion and the relative notion coincide. So this can be expressed as follows: that K be a field, the following conditions are equivalent. First of all, A, K is perfect. B, for every two algebras A and B over K, all algebras are commutative with unit. If A and B are reduced, then A tensor KB is reduced. Or to say that for every A algebra over K, and every extension K prime of K, it's just a field now containing K. The algebra reduced from K by making the base extension is reduced if A is. A reduced implies that A tensor K prime is reduced. So this states it's an algebra over K that is reduced, remains reduced by an arbitrary ground field extension. And B, let's say if K prime over K is any purely inseparable, is any finite purely inseparable extension of K, and therefore it is certainly reduced. We want that K prime tensor K prime should be reduced. Alright, I claim that all these four properties are equivalent. I think it's kind of well known. So of course the property B implies the property C, which is just a particular case taking B to be an extension of K. And of course C has this particular case D, which is obtained by taking A equal to K prime and K prime to be a very special type of extension of K, namely just a finite pure and simple extension of K. And this is really the most special you can make it. Now, certainly, on the other hand, what means that K is perfect? Let's recall the definition. Either the characteristic of K is equal to 0, or the characteristic of K is equal to P and positive, and the relative piece power, which we know to be an endomorphism of the ring K, and of the field here, therefore it's injective, is surjective. Therefore it's an isomorphism. So a relative of K is a piece power. That's what it means to be perfect. I mean, that's one of the definitions. It's the most concrete definition. And then now, D implies A. That's well known because assume that X is in K, and assume that X is not in Kp. Then look at the extension K prime obtained from K by joining the piece root of X. So that's just K of T divided by T to the P minus X. So that's a radical extension, in fact, of degree P of K, purely inseparable extension of K of degree P. And if I take K prime tensor K prime over K, we see that this is isomorphic to K prime of T divided by T P minus X, but X now becomes a piece power in K prime, and therefore this here can be viewed as being K prime of T divided by T minus alpha to the P, where alpha is this piece root of X in K prime. Recall that residual piece power is a homomorphic algebra, so T minus alpha to the P is T to the P minus alpha to the P. And this clearly is not reduced. You see, this has T minus alpha, this is an local article that has T minus alpha as an equal ideal not reduced to 0. T minus alpha equals S. In fact, as an algebra over K prime, it has as a basis S equals T minus alpha and its powers S to the I for I between 0 and P minus 1. All right, and therefore we see that we have a contradiction. That means that the condition B implies that K is perfect. On the other hand, the fact that K is perfect implies this here, and this we will admit as standard fact of commutative algebra. It's generally stated by taking A and B to be field extensions. but we easily reduce to this case, I guess. Because if A and B are reduced, this implies that they are contained in the product of fields. The intersection of the prime ideals in A are equal to 0 and the same in B. And therefore A tensor KB will be contained in the product of the tensor product of fields. And therefore what we really use in order to prove this is, if K is perfect, and if capital K and capital L are extensions of K, then K tensor L over small k is reduced. So that's when an effect from field theory that I'm using here. So the perfect fields are just those for which the notion of a reduced algebra behaves nicely with respect to base extension or with respect to tensor products. Now let's make some more cohesive algebra before speaking of schemes. Let A be an algebra over fields K, and I will state a certain number of equivalent conditions, which will be stronger than A reduced, and that A is geometrically reduced. In order to state them, I will fix myself an extension K1 of K, which is perfect. So, which has these nice properties. There would be a standard choice of a perfect extension of K, taking for instance the perfect closure of K, with Dieck limit of K mapped one into the others by raising to piece powers, which is an injective homomorphism of fields. So it would be the maximal radical extension of K, which is defined up to canonical isomorphism. But we don't care. We can as well take the algebraic closure or any algebraically closed extension or any perfect extension will do. All right, we fix this, and now our equivalent conditions will be the following. On A, first, for every algebra B over K, such that B is reduced, we want that the tensor product A tensor KB should be reduced. Of course, when we take B equal to K, then this means that A itself is reduced. But we want something much stronger. A should remain reduced by tensoring by any reduced algebra. Now, second condition, for every extension K prime of K, AK prime deduced from A by making the ground field extension from K to K prime is reduced. So this is what we would like to call geometrically reduced. A is geometrically reduced over K, and it's reduced and remains so after any ground field extension. Now C, the same thing, but we're taking the one ground field extension K1 here. A lower K1 is reduced. So we have to check it just with one ground field extension, provided the new ground field is perfect. And D, for every finite extension K prime over K, K prime finite and traditional, let's say, we can even assume it of degree P, the characteristic exponent, the has 0, P will be equal to 1. A tensor K, K prime is reduced. So I claim all these conditions are equivalent, and if they are satisfied, I will say, by definition, that A is geometrically reduced according to the general terminology. Maybe it's reduced and remains so after on ground field expansion, or also, which is shorter, A is separable. It's such an important notion that it deserves an extra name. That's the algebra A over K is separable over K. It's a relative notion, algebra over a field. Now, let's check this. Of course, B is a particular case of A by taking B an extension of K. C is a particular case of B by taking k prime to be equal to k1. And on the other hand, D is another particular case of B obtained by taking k prime, just a finite radical extension of degree p. In fact, here in the statement, we could inseparable extension of degree p if we want. The proof shows that we can just include those one. All right, therefore we have these inclusions. And so all we have to show is that C and D imply A. Now how will we do? Well, to say that B is a reduced algebra over K just means that it can be embedded into a product of fields. And therefore this here will be embedded in the product of tensor products of A with field extensions. As the subring of a reduced ring is reduced, here in A, in order to check that A is true, we have only to check that B is true. In this case, when B is an extension. So we first remark this. All right. Now, so let's take a field extension. Now let's prove that C implies B. That if for the field extension K1, tensoring with it gives you a reduced ring, then tensoring with any field extension, you get something reduced. So we will now prove this. Now let K prime any field extension, and let's take a field extension which is larger than both K prime and K1, or as K prime 1 if you want. Now, the algebra AK prime deduced from A by making this field extension is contained in AK prime 1, deduced from A by making the extension still further. And therefore, in order to prove that this is reduced, we have only to prove that this is reduced. That is, we are reduced to the case of a field that contains K1. But in order to make the ground field extension from K to K prime 1, we can go over K1. We have here A lower K1, which by assumption is supposed to be reduced, and now K1 being perfect, being reduced over K1 is stable under any ground field extension. Therefore, A K prime 1 is also reduced. So A, B, C are equivalent. Now I have just to prove that they are consequence of D. And in order to do so, I will look at a particular case of a perfect extension of K, namely the extension what should I say? That is called K, P to the minus infinity, the perfect closure of K. We know already that these conditions here are independent of the particular choice of K1. So I will take now K1 to be this perfect closure of K. Now this perfect closure is the Dirac, because it's an algebraic extension, it's the Dirac limit of finite extensions Ki of K that are purely inseparable. Ki. Alright? And therefore, A lower K1 is the Dirac limit of A tensor over K, Ki. And of course, in the Dirac limits, the transition morphisms are monomorphisms, if you feel better about it. Now, by assumption, so, well, I said of degree P here. I think that's true, but I don't really want to bother so much. So let's say just a finite radical extension. Okay. All right. So by assumption, these rings here are reduced, and therefore the Dirac limit is reduced to 2. So there's just, if you want really here to check, to test only with a radical extension of degree P, then we would have to work a little more. I think it's true. Well, I don't think I want to ponder now with a proof. So let's be some content with this here. Alright, so this is a pretty standard notion of commutative algebra. The notion of a simple algebra or a field, or commutative field, just means it's not only reduced, it remains reduced after any ground field extension. Now, let's give the variant of this when we replace algebras over K by schemes over K. Let X be a scheme over K. Then we have equivalent conditions. Namely, A is that for every scheme Y over K, if Y is reduced, the product of X and Y over K is reduced. The second is the same thing except that now Y is the spectrum of a extension, K prime of K, which means that for every K prime over K, an extension xk prime is reduced. Here we take xk1 is reduced by just taking a given perfect extension. And here for every K prime over K finite traditional extension of K, we want that xk prime be reduced. I claim that all these conditions are equivalent, and I mean it's kind of trivial, for instance, because it reduces at once to the case when X is affine, because when we cover X by affine pieces Xi, every Xi being the spectrum of a ring AI which is an algebra over K, then each of these conditions is equivalent to the same condition for all of the Xi's, namely for all of the rings AI. And for the ring AI, it's just the corresponding condition that we have seen in the statement before. With the exception perhaps of A, but then Y also will be covered by affine open sets. So that's the case A is reduced to the affine case. So when these conditions hold, then we will say that X is geometrically reduced by definition. Then we will say that X is geometrically reduced over K, or that X is separable over K. So the two terminologies are synonymous. Now, so remark, if X is separable over K, then of course X is reduced, so the geometric notion implies the absolute notion. And when is the converse true? Converse is true by the first proposition, if and only if K is perfect. Where perfect ground field, separable and reduced is the same thing. So that's clear from what we have said so far. What else? Assume that we have X over K. Take any ground field extension, K prime. Then we see that X is separable over K, if and only if xk prime is separable over K prime. That's quite clear, because if you take a perfect extension K1 of K prime, it will be a perfect extension of K, and then the two conditions here, this and this, just mean that X lower K1 is reduced. Because both mean that X lower K1 is reduced. So, therefore it's clear that our notion of being separable is a geometric notion, namely, if it's true, if the boundary extension is true after field extension, if it only it was true before. So, anything else to say? All right, so I think that what exhausts the problem of reducedness and its geometric version. Now we come to irreducibility of a scheme, which is a pure topological notion, but we are going to do it now for schemes over a field K. And here again we begin with the lemma of commutative algebras, namely properties of a field, of the ground field K, to proposition. The putting conditions are equivalent, conditions on K are equivalent. So here now, the good property for the fields stated in Google term is that K is separably closed. What does it mean separably closed? The naive notion is that every algebraic simple extension or every Galois extension that amounts to the same, because the two types of extensions are cofinal with respect to each other, is trivial, is reduced to K. So there may be finite extensions that are not trivial, but they should be radical. So that's what amounts to the same. Every finite extension, every algebraic extension, or every finite extension is radical and purely inseparable. Of course, recall that in characteristic 0 every field is perfect, and therefore in the characteristic 0 separation is over K just is equivalent with reducedness, and here in characteristic 0 K separably closed is equivalent with K algebraically closed, because all the additional extensions of K are equal to K. Alright, so that's the more usual way of stating property of K. K just separably closed, and now geometric disguises of this. So let's say if A and B are algebras over K, and if their spectra are irreducible, namely A divided by nilpotent elements of A is an integral domain, and the same for B, and B divided by the nil radical of B integral domain, then A tensor B divided by the nil radical of A tensor B is an integral domain. So, in fact, in this condition, we could as well assume A and B to be integral domains to start with, because these nilpotent elements in A just will give rise to more nilpotent elements in here. So it just means also that if A and B are integral domains that are K algebras, then A tensor B perhaps is not an integral domain, but divided by its nil radical, it is an integral domain. So that's the property. And now C is the same property B being an extension. That A, B, well, that's an integral domain after all. Lying over K, and K prime over K an extension. Then A over K prime divided by its nil radical is an integral domain. And the last condition is a particular case of C, obtained by taking here finite separable extensions that you want. If A is an integral domain, hey, why not being still more restrictive? If K prime over K is any finite separable extension, so why not just say any Galois extension then, to make it still more specific, any Galois extension. Then K prime tensor K prime is an integral domain. Let's joke a little. So I claim that all these conditions are equivalent, and if they are true, I say that K is separately closed. All right. Now B implies C, and C implies C implies D. That's reality, because They're just particular cases. Now D implies A, that's in reality 2, because we know that if you have a Galois extension of K, K prime tensor K is a product of capital gamma copies of K prime, where gamma is a Galois group. So therefore, if this is an integral domain, then again the Galois group should be reduced to one element. And therefore the extension should be trivial. But that just means that K has no Galois extensions except itself. That just means that K is similarly closed. Alright, so all we have to prove is now that if K is similarly closed, then B holds. And now here again we refer to a classical statement of commutative algebra. Of course, if A and B are integral domains, we want to prove that the tensor product divided by the put elements is an integral domain. And A and B will be contained in the total field of fractions. And we are immediately reduced to this case when A and B themselves are fields. And so what we are using is the following: if K is similarly closed, and if capital K and capital L are extensions of small k, then K tensor L maybe is not an integral domain, but divided by its Lie radical, it is an integral domain. So that's the second statement of commutative algebra of field theory essentially that we are using. And if we don't prove here, I think you should find proofs of this in any treatise of commutative algebra of field theory. Alright. Now, when I said that a ring divided by its Lie radical is an integral domain, this just meant that the spectrum of the ring is irreducible. And therefore, we like now to state the following proposition, but now it will be a condition on the scheme X over arbitrary ground field K. So I give this scheme X over K, and I give an extension K1 of K, which I now suppose to be separately closed. Which means that for an affine scheme at least over K1, if it's irreducible, then it remains irreducible after any ground field extension. That's why we can take K1 to be separately closed. That's what we would like to be true. And then I say that the following conditions are equivalent. Now they are not conditions on the ground field, now they are conditions on this relative scheme. A, for every y over k, if y is irreducible, then x times ky is irreducible. The second condition is particular case of A obtained by taking for y the spectrum of the field extension. For every extension k prime of k, x lower k prime reduced from x by making the field extension to k prime, which is just the Fayard product of x and spec k prime over spec k, is irreducible. So taking k prime to be equal to k, we see that x should be irreducible. But not only x, but should remain so after any ground field extension. Now, C, we take k prime here to be k1. xk1 should be irreducible. And D, we take just finite Galois extensions for every k prime extension of k which is finite and Galois. X k prime is irreducible. So I claim that all these conditions are equivalent, and of course, when they are satisfied, I will say by definition that X is geometrically irreducible over K which is a stronger notion than X to be irreducible. Now let's prove the equivalence of A, B, C, D. So B is a particular case of A, C is a particular case of B, and D is a particular case of B. You see, we have exactly the same scheme of implications as before. In fact, we are more or less doing 4 times the same kind of things. Now, we want to prove that C or D either implies A. Haha, ho ho. So I think you will have to do as before, first to prove that B implies A, and then work upwards. All right. We want to prove, assuming B to be true, we want to prove that for every y over k, y being irreducible, the product here is irreducible. So y can be covered by affine open sets yi, affine and non-empty, let's say, and then x times y will be the union of x times yi, and these will be open sets in x times yi, and the intersections of these open sets are just x times yi intersects yj, and yi, because y is irreducible, the yi's intersect in a non-empty way, and therefore these here will be non-empty, assuming x to be non-empty. And we can do this because B implies, of course, that x is non-empty. It implies that x is irreducible. All right. So, therefore, x times y will be covered by these open sets, which are non-empty open sets and that meet mutually. And therefore, to prove that this is reducible, it amounts to the same to proving that these open sets are reducible. So this reduces us to the case when y is affine. So we may assume as well y to be affine, and of course, dividing out by the nilpotent elements, which doesn't change anything, we may assume y to be integral. So we may assume y to be the spectrum of the algebra A over K, A being an integral domain. And now, well, now I do the same thing that I did with y, I do it with x in order to reduce to the case that x is affine. So it's just really the same game. So the condition here for x is the same, is the conjunction of the same conditions for the open sets, affine open set xj that cover x. All right, non-empty open sets, non-empty affine open sets xj that cover x. So we can already assume now that y and x are both affine. So then maybe the spectrum of the ring of y I'd rather call B perhaps. Now the ring and x now is a spectrum of A. Now x times y is just the spectrum of the tensor product of A and B over K. And this is contained in the tensor product of A and K prime over K, where K prime is a total ring of fractions of the integral domain B. And from this, therefore this here is intermediate between this ring and the total ring of fractions, and its total ring of fractions. And from this, it follows immediately that in order to check that the quotient of this by its near radical is an integral domain, we have only to check the same thing for this tensor product. Because the quotient which we have here is contained in the corresponding quotient ring here, put by the radical, and the subring of the integral domain. So this shows that A and B are equivalent. Now how will we prove that C implies already B? That's the same game as before. We want to prove that if after the extension K1 we get something which is irreducible, then for any other extension K prime, we get something that is reducible. And for this, we look at an extension which contains both. So it's irreducible after passing to K1, therefore it's irreducible after passing to K prime 1. But this implies that it's irreducible over K prime, because we have here xk prime 1 is mapped to xk prime, because spectrum of K prime 1 is mapped to spec K prime. And this morphism on the spectra being surjective, this morphism also is surjective, because it's deduced from by base change. On the other hand, if you have a surjective continuous map of irreducible topological spaces, then the target space is also irreducible. Alright, so B is equivalent to C. Now we know already the equivalence of A, B, C, and therefore that C doesn't depend on the particular choice of K1. You can take any any similarly closed extension. And now in order to prove that D implies the other conditions, and then we are done, we just take for K1 the separable closure of K, namely the which is defined up to non-canonical isomorphism. And this K1 will be the Dirac limit of all sub-extensions of K1 that are finite and Galois over K, which are finite Galois extensions of K. Now I have Kx over K. I want to prove that xk1 is irreducible. And I know already by the assumption B that all of the xki's are irreducible. So all I have to show is that if the xki's are irreducible, xk1 is. Now, this is a general nonsense situation, I think, with inverse limits of schemes, you see. K1 as a ring is the Dirac limit of filtering Dirac limits of the Ki. Therefore, the spectrum of K1 is the filtering inverse limits of the Ki's, and for the same reason, we're making the base extension here from spec K1 to xk, from spec K to x. You see that xk1 is the inverse limit of these schemes, all of these being affine over x. And now all I have to show is that if we take such an inverse limit of irreducible schemes, all in filtering inverse limit, all being affine with the same basis x, then if the intermediate schemes xi are irreducible, then the scheme x is reducible. It's probably true, certainly true, but are we going to prove it? All right. Well, I guess all these xi's here, and here we have x1, which is the inverse limit of the xi's. So as before, let's perhaps reduce to the case when x is affine, because we will cover x, the affine open sets. I do not dare anymore call them xi, call them u alpha if you want, call them u upper alpha if you want, that are affine and non-empty, and of course irreducible, because x is already irreducible because of this here, taking k prime equal to k, and therefore x being irreducible, these non-empty open sets must meet each other, and therefore if I take the inverse image in the xi's, because xi goes to x is surjective, these ui alpha will be open subsets of each xi that meet each other, and the same in u alpha 1 here. So I have only to prove that these open subsets of x1, u alpha 1, that these are reducible, because as they meet each other, they are open. That will imply that x1 is irreducible. In other words, And we know already that the ui alpha I for any alpha are reducible as open non-empty open subsets of an irreducible space. Alright, this reduces us to the case when X is itself is affine. And then we can express everything in terms of commutative algebra. So, provided there's no change if we divide out by the nil radical of the structure field of X, that doesn't change the problem. So we can assume that doesn't help anyhow, I think. That X is a spectrum of an integral domain. It doesn't help anyhow because after making all, oh well, maybe, let's see. No, that may help. Alright? And our assumption is that after making any one of these extensions from K to Ki, the ring AKI which I have here, divided by its nilpotence, must be an integral domain. But this ring has no nilpotence because Ki over K is separable. So it must be an integral domain. Is this clear? Because it's divided by its nilpotence, it's an integral domain. It has no nilpotence because A has no nilpotence and Ki is separable over K. Therefore, the AKI make a direct system of integral domains, the transition morphisms of course being monomorphisms. And therefore the direct limit is an integral domain. And therefore if you divide it by its nil radical, which is 0, it's still an integral domain. So that does it. So when these equivalent, so all these conditions written down here are equivalent, when they are satisfied, I will say that X is geometrically irreducible. And now again, we see over K, depends on the K structure of X. Now we see again that if X is geometrically irreducible, then X is irreducible. We have said it several times. We take K prime here to be equal to K. And the converse holds if and only if for every X, if and only if K is separably closed. So the separably closed fields are exactly those for which we can say that a scheme over this field that is irreducible is even geometrically irreducible. What else can we say? Oh, I forgot something before, but never mind. If we have a field extension from K to K prime, so that if you have a scheme X over K, we get a scheme XK prime over K prime, then X is geometrically irreducible over K if and only if XK prime is geometrically irreducible over K prime. Now there's something which I should add to our theory. It's about how these notions behave with respect to taking products. So let's state now, if let X and Y be schemes over K, if X and Y are both separable over K, respectively geometrically irreducible, then X times Y taking products, and the notion of being geometrically irreducible is also stable under taking products. And this is again, both statements are a trivial consequence of the proposition that introduced the definition. Because recall that X to be separable, let's say, meant that if I multiply X by any y that is reduced, I get something reduced. Now I assume that x and y are both separable. Let's prove that this product is separable, that is that its product by z, which is by any reduced z, is again reduced. But this product can be obtained by taking first the product of y and z, that's something reduced because y is separable, and then multiplying it to x, it's again reduced because x is separable. And their argument is exactly the same, it's geometrically reducible. Now we have dealt with the case of reduciveness of a scheme and of irreducibility of the scheme. What if we take the two together? Then we get the notion of an integral scheme, a scheme that is both irreducible and reduced. So now we will study this notion in the geometric context as a corollary. So the ground fields over which everything is nice concerning the notion of integrality, and there is no problem whatever. These are the ground fields which are both nice for reduciveness, namely that are perfect, and nice for irreducibility, namely that are separably closed. Now these are the algebraically closed ground fields. And so maybe we begin, as before, with the lemma of commutative algebra. Let K be a ground field. Then the following conditions are equivalent. A, K is algebraically closed. B, if A and B are algebras over K that are integral domains, then X times K, I'm sorry, A tensor K be an integral domain. C, let's put a B prime if you want the schemes. If X and Y are schemes over K that are integral, then X times KY is integral. Now, a C, if A is an algebra over K, it is integral. And if K prime is any field extension, then AK prime should be integral. Integrality for an algebra over K should be conserved by field extension. So C prime is the same, but it was as X over K. And what about D? We will take now something extremely special. Let's say if K prime over K is a finite extension, then the tensor product K prime tensor K prime is an integral domain. So all these conditions are equivalent. In fact, we don't have to get any proof because it has already been proved in the two previous lemmas. And now, again, a proposition which will introduce geometric integrality of a scheme. Let X be a scheme over K, and let K1 be an algebraically closed extension. Then the following conditions are equivalent. First, for every Y over K a scheme, if Y is integral, then so is X times Y. B, the same as an extension here for every extension K prime over K. X K prime is integral. C, that after the extension K1, X K1 is integral. And D, for every extension K prime of K, which is finite, let's say X K prime is integral. All these conditions are equivalent, and it's just a corollary of the two analogous propositions which we have given with the property of reducedness and the property of irreducibility. And when these properties are satisfied, we'll say that x is geometrically integral, which just means that it is separable over k, namely geometrically reduced and geometrically irreducible over k. And once again, geometrically integral implies integral, and the converse holds for every x if and only if the ground field k is algebraically closed. In fact, it was already stated here. And if you have a field extension k prime of k, then x k prime is geometrically integral over k prime, if and only if xk is geometrically integral over k. And moreover, if you have two schemes x and y over ground field k, then if both are geometrically integral, their product is geometrically integral. All right, all this is here, I think. And now we come to the fourth notion, which is the notion of connectedness. Let's see how this works. No. Well, here, as you see, you may suppose that from what came before that for the notion of connectedness to work very smoothly over a given field without having to make it just geometric, the field should be separately closed when it will come out in due course. So let's first give a theorem. Let K be a separately closed field. Then let X and Y be two schemes over K. Then I claim that if X and Y are both connected, this implies that their product over K is connected. So the product of two connected schemes lying over a separately closed field is again connected. Now, maybe it's more generally stated this when K is algebraically closed. Maybe before going over to the proof, I should make a comment why there is, for such pure topological statements, there is not an essential difference between taking a separately closed ground field and an algebraically closed ground field. Because let K be a separately closed ground field, and let K bar be its algebraic closure. Then, to say that K is separately closed means that K bar is purely inseparable, is radical over K. So it's an algebraic radical extension of K. Now what one can prove, or at K prime perhaps, no why not K bar, is the following, that if you have an algebra K and another algebra containing it and finite over it, and such that it's radical over it, that then for every scheme X over K, when we make the base change from K to K bar, so we get an X bar over K bar, then the homomorphism from X bar to X is that's the projection from X bar to X, which comes from spec K bar going to spec K, see, is a homeomorphism. It's not an isomorphism of schemes, but it's an isomorphism of topological spaces. It's a homeomorphism. So for all topological notions, X and X bar are just, S code. We won't prove the statement here, it will probably come out in more or less connected with the crossing of the desert, this kind of thing. Therefore, I mean, any topological notions that we can state for X actually with the corresponding notions after making the ground field extension. So in a way, it's just for the sake of, you see, of being fancy, for making the most general assumptions that one will assume here K to be similarly closed, but in fact it's essentially equivalent with the same statement, assuming K to be algebraically closed. And that's how things are generally stated. By the way, for irreducibility, I could make the same comment. X is irreducible if an order X bar is. Therefore, to state that the product of two irreducible schemes over X is again irreducible, we can at once reduce to the case when K is algebraically closed, not only similarly closed. All right. So if you prefer, you just assume K to be algebraically closed. What follows? Now, I will give two separate proofs of this. One will be in a special case. If X and Y are locally of finite type, over K. That means that any affine subset of X has an affine ring that is an algebra of finite type over the ground field K, and the same for Y. So that implies that, according to our crossing of the desert, pretty trivial, that the product also is locally of finite type over K. So locally it just looks like a scheme of finite type or a field, you see, and therefore it's certainly locally Noetherian. Now, to prove that a local Noetherian scheme, a locally Noetherian topological space, in fact, is connected, we just have to prove, it's equivalent to proving, that we can join any 2 points by a sequence of irreducible components, such that 2 consecutive irreducible components meet. That is a connectedness notion, then, in the case of such spaces, is reduced to playing around with irreducible components. And that will reduce in the first proof, which works only under these respective assumptions. So let's take 2 points of, let's say, Z and Z prime of X times Y. So Z lies over 2 points X and Y, respectively, of capital X and Y, and Z prime lies over X prime and Y prime. And then I can find a chain of irreducible components of X joining X to X prime. Call them X alpha if you want, so that X1 contains X, Xn contains Y, and Xi and Xi plus 1 meet. And the same here, X prime can be joined to Y prime through irreducible components Y beta. Y1 contains X prime, Ym contains Y prime, and Yj and Yj plus 1 meet for the J. All right? And now look at the product of X alpha by Y beta. Now these are reducible because K is separably closed. The product of 2 irreducible schemes over K is reducible. And I guess it should be clear, while X1 times Y1 contains X and Xn times Ym contains Z, I'm sorry. Xn times Ym contains Z prime. And on the other hand, one can connect these X alphas and Y betas in such a way that mutually they will intersect. But I would like to prove the theorem without assuming X and Y locally of finite type. For instance, one would like, for instance, to be able to take for Y the spectrum of a field and then to say that if X is connected, then it remains connected after any field extension. Now, a field extension of a finite type over the ground field, you see. I mean, you always get out of, when you make some restrictions, you are always sure that you will be annoyed at some point. Now, let's just prove it in full generality, but we have to admit one statement which will come out of flat descent, which is the following. If you have x over k and y over k, and if you look at the product, x times ky, that then this morphism here, which we know already to be surjective from the product to x, that the topology of x is a quotient topology coming from this morphism. That the set of x is open, if and only if its inverse image here is open. In other words, in fact something even stronger is true, namely that this morphism is an open morphism. The image of any open set is open. It's a lot stronger, but we don't need so much. We need to know that the topology of x is a quotient topology. So this will come out when we will speak a little bit about flat descent. It's not a deep statement. It comes out pretty easily. I could prove it here in 5 minutes or 10, but let's not interrupt the other arguments for the sake of proving this lemma. So that's what I will mainly use. And now, let's see. I first prove a particular case. If x is connected, and let's add non-empty, then for every field extension, k prime of k, xk prime is connected and non-empty. We know, of course, the non-emptiness is conserved by field extension. So, I mean, it's a non-empty, it's the way in which we will use it. But if we dropped it, it would be an essentially equivalent statement. Because x is empty, or if x prime is empty. All right. So let's prove this. So we take y here to be the spectrum of k prime. So we want to prove that xk prime is connected. But we know already that xk prime is mapped to x, so that the topology of x is a quotient topology. And we know that x is connected. So all we have to prove now is that the fibers are connected. Because if we have a surjective homomorphism such that the target space is a quotient space of space above, and if the fibers are connected, then the whole space is connected. Let's give the argument. That's general topology. Because if you have a subset of xk prime which is both open and closed, then it will meet every fiber which is connected in a set which is either the whole of the fiber or the empty set. And therefore, this subset will be saturated by the equivalence relation defined by this map. And therefore, it will be the inverse image of a subset of x. But as the topology of x is a quotient topology, the subset also must be both open and closed, and therefore it must be either x or the empty subset. So what we have to prove is that the fibers are connected. But what are the fibers? We have already seen if you take a point x in capital X, then the fiber of this morphism is just the spectrum of the tensor product of kappa x and k prime over k. But now kappa x and k prime, they are integrity domains lying over k, and the tensor product, because k is similarly closed, must be a ring which is irreducible, namely divided by the near radical. It should be an integral domain. In other words, its spectrum is irreducible, and therefore so is the spectrum is connected. So therefore, the first particular case when y is the spectrum of a field is dealt with. And now general case, take a general y, and now look at, if you want, look at it in the other direction, look at this morphism here. Y is connected. In order to prove that x times sy is connected, we just have to prove that fibers are connected. But what are the fibers at a certain point y and capital Y? It's just x tends over k with kappa y. That's the transitivity of fibers. The fiber of this over the point small y of capital Y is just what we deduce from X by making the base change from K to kappa Y. But this is connected because, I'm sorry, we have to prove that the fibers are connected and non-empty, you see. I mean, we know already that this map is surjective. And Y is a topological property, so the fibers are non-empty. All right. So we just have to prove that these fibers are connected, but that's what I proved in A. Of course, for this term to hold, it's essential that K should be separately closed. If K is a field, and if such that for every finite extension, K prime over K, finite Galois extension U, the product spec K prime times over K spec K prime, of course spec K prime is connected, it's reduced to a point. If this is connected, id est, well, whatever, then K prime, then I'm sorry, K is separately closed. So even if we state the theorem, I mean, the conclusion of the theorem, for a very special tape of X and Y, namely X equals Y equals the spectrum of the finite separable extension, this already implies that K should be separately closed. Because, once again, if K prime is a Galois extension of K, the tensor product of K prime with itself over K is the product of capital gamma rings isomorphic to K prime, of capital gamma copies of K prime, where gamma is the Galois group. So if the spectrum of this cannot be connected unless gamma is reduced to one element. So really here, we just, this is really the most general, the weakest assumption we can make in order for the conclusion to hold. All right, so I'm about to terminate, I think. So maybe we have 5 minutes more. All right. Now I have to relativize these things. Let K be any ground field, and let K1 be a separately closed extension, and X be a scheme over K. Then I again have equivalent conditions. So I think a computer now at this point makes a statement. First, for every Y over K, if Y is connected, then X times over KY is connected to B. Same thing, but with Y the spectrum of a field. For every field extension K prime over K, Y lower X lower K prime, I'm sorry, is connected. C, the same with the field extension K1, XK1 connected. Small d, what should be small d? For every finite Galois extension, K prime of K, FK prime connected. All these things are equivalent, and we express them by saying that X is geometrically connected over K, which of course implies that X is connected over K, because we take K prime to be equal to K. It's a stronger notion. The converse is true, that for every scheme X over K that is connected, that it's symmetrically connected. This holds if and only if, as we have seen, K is symmetrically closed. But let's prove the existence of these conditions. We have, it's clear that A implies B. B implies both C and D as a particular case. So as before, we should prove that C and D imply A, and we have to prove separately first that B implies A, then that C implies B, and that D implies B. So why does B imply A? All right, let's look at the Y over K, and let's look at the product. If Y is connected, I claim that if B holds, for every Y connected, this is connected. Indeed, this is, we know that the topology of Y is a quotient of this, of the topology of this thing above, this morphism here being surjective. Well, being surjective, assume if X is empty, there's nothing to prove, so assume X non-empty. So that this then is surjective, and the topology of Y is a quotient topology. All right? Then in order to prove that this is connected, we have only to check that the fibers are connected, and the fibers are deduced from X over K by making Grothendieck extensions. So by in which of B they are connected. That's fine. Now we have to prove that C implies B. Well, that's the same argument. We have to prove that if xk1 is connected, then for every ground field extension k prime of k, xk prime is connected, and we again take an extension that contains both xk1 being connected and k1 being superbly closed. Xk prime 1 is connected, but xk1 is deduced from xk prime by making the field extension from k prime to k prime 1. On the other hand, xk prime is the image by the projection of xk prime 1, and the image of a connected space by a continuous map is connected. So that makes this, and now we just have to prove that D implies B, and then we are through. And here again, it's a passage to limit. I take for K1 the separable closure of K, which is a Dieck limit of finite gamma extensions Ki of K. By assumption, all the xki's are connected. And I want to prove that xk1 is connected. Now xk1 is the Dieck limit of the xk, is the inverse limit, the filtering inverse limit of the xki's. So what I have to prove is that if you have schemes over X that are affine over X and that form a filtering inverse system, and if each of these schemes are connected, then the inverse limit is connected. And this is true for the following reason. So let me give the principle of proof, pretty easy. Assume first X to be quasi-compact. Alright, so each of these xki's is quasi-compact, and the limit xk1 is quasi-compact too, because they are all affine over X. And then, X being quasi-compact, it's quite easy to see that whenever we have a decomposition of this as a sum of two sets which are both open and closed, let's say if you have a set within here which is both open and closed, then it comes, for I big enough, from a subset in here which is both open and closed. Well, I mean, that's kind of the same order of difficulty as what I did before with our passage to limit. Quite easy. Now, as xki is connected, this open subset in xki must be either empty or the whole, and therefore the set which we have here is either empty or the whole, which we wanted to prove. Now, if X is not quasi-compact, then X, how can I say? Okay. Can I make that up? Yes, I think I can. No, I don't see it here. So let's state this if X is quasi-compact, and I should, maybe next time, I should try to get rid of this assumption. I don't think it's really necessary. All right, now, what about this notion of geometrical connectedness? It's just as before, that if we have a ground field extension K prime of K, x is geometrically connected by k if and only if xk prime is geometrically connected by k prime. And because of this way of stating things, we see also that the product of two schemes over k that are both of them geometrically connected by k is geometrically connected. All right. So that's the main part of the story I had in mind. So tomorrow afternoon we are going to give an interesting case of an arbitrary ground field which need not be symmetrically closed, where the notion of connectedness and geometric connectedness is the same. So yesterday we went on, yeah?
I just wanted to ask a question, something that you did 5 or 6 lectures ago.
Yes.
Just a definition. Suppose you're given objects fi of schemes over S curve. How would you define sub fi?
Sub-objects of a scheme. Fi's are contained in a scheme. That's the data.
Well, I just suppose you're given objects fi belonging to schemes over S curve.
Fi.
Objects of schemes over S curve, right? How would you define sub of fi?
I don't think it makes much sense. They should be sub-objects of a given object. If the Fi's are sub-sheaves of a given sheaf,
Right.
then it can be, the sheaf can be defined.
As?
All right. It's, you can do it in various ways. You can, for instance, look at the direct sum of the sheaves Fi in the category of sheaves, and then the set of morphisms, of include morphisms Fi equals to F, defines your morphism from the sum of the Fi's into F. And I define the sweep of the Fi's just as being the image of this. So any homomorphism of sheaves can be factored canonically into an epimorphism followed by a monomorphism. And this monomorphism, I mean, the source of this monomorphism is called the image of the morphism. Just as with sets of sets can be factored into the epimorphism. Surjective map followed by an indective map, and this indective map or its source will be identified to a subset of the part that is called the image. So here it's the same. Like I described in various ways what the subfunctor, call it f prime if you want, so they all can be factored through f prime, what this subfunctor is. But we can also alternatively describe f prime as being the smallest subsheaf of f, which contains all of the fi's. So these are pretty abstract definitions in terms of the global category of sheaves, but I described also how you can make it concrete, and I said, what is a functor? I just described the functor. When is, take an element of fs, u element of fs, I'm sorry, s is already there, so we have some s prime, let's say, over s, and we want to describe what is f prime of s prime being the sweep. So it should be contained in f of s prime. And we ask, what is the subset of f of s prime? And so the point I made, which I tried to explain, maybe it wasn't too clear, is the following. That an element u in f of s prime belongs to f prime of s prime if and only if it belongs not to the images of one of the fi of s prime, but that's of course the first thing that comes to mind. In this set f of s prime, there sits the subsets fi of s prime. One can take the union of these subsets and then declare that u belongs to f prime, but this would be wrong if it only belongs to some of the FIS prime. No, the correct definition here, as we are working with sheet and not with pre-sheet, is to say that U belongs locally to one of the FIS prime, namely that we can cover that for every point S prime capital X prime, there exists a neighborhood, open neighborhood U of S prime, and there exists an I in capital I, such that the restriction of U, this element of Fs prime, to U, which will be a priori an element of F of U prime, belongs to, in fact, Fi of U prime. So the sup therefore is defined as being the points of the sup are the points of F with coefficients in some S prime that locally belong to, locally on S prime belong to some of the FIs. That's always the same story with sheets.
That's just the map from the product of the FIs to F primes.
The sum of the FIs.
Right, the sum, sorry. The sum of the FIs is an epimorphism.
Yes. So that's also the only subobject of F prime of F in the capital of sheets. So that the Fi, the sum of the Fi is going to F factors to F prime, and that this should be an epimorphism. I mean, in this way we have decomposed this map into an epimorphism full of a monomorph. But when you come back, I mean, to the definition in terms of properties that should hold locally, everything becomes extremely clear. And all exactness properties of the capital of sheets have become pretty evident. For instance, property that every morphism factors into an epimorphism followed by monomorphism in a unique way, etc. All this comes out pretty evidently. Is this all right? So, last time we studied a few more classes of morphisms. So I think we spoke about immersions, closed immersions, open immersions, and general immersions, which are just compositum of an open immersion followed by a closed immersion, or conversely. For instance, we have seen that every diagonal morphism is an immersion, and therefore every section is an immersion, and every kernel morphism is an immersion, so there are lots of immersions. Immersions are locally of finite type, but they need not be locally of finite presentation. But if you have a morphism, if you have a scheme or another which is locally of finite type, then every section is an immersion that is locally of finite presentation. You have seen these kind of things. Now, the separated morphisms separated morphisms are those for which the diagonal morphism, corresponding diagonal morphism, is a closed immersion, or what they want to say, a closed map. So, classically, all morphisms were separated, but we have seen some examples of non-separated schemes, that means of morphisms into the final scheme, let's expect U into any separated scheme that are not separated. Maybe I should give a little, I claim that you meet with non-separated schemes in rather natural ways, you see, without looking for them. Maybe I should give an example. In what kind of geometrical situations one really turns up without looking for them is non-separated schemes. So assume that we have a scheme X over S. Think of S, for instance, as being a curve, a parameter curve, might be the line, and X is a family of varieties parameterized by this curve. And now something which happens quite currently is that the general fiber is irreducible whereas a special fiber decomposes into, whereas a certain special fiber at a certain point, S0 and S, decomposes in two irreducible components, two or more irreducible components. Now, assume that we're interested in following, you see, the number of irreducible components, the set of irreducible components from point to point. So in this way, we will get something like a covering of S, you see, whose point at every point of S is the set of all irreducible components of the fiber. That's something extremely natural to the situation. So now this covering at the general points of S, all points except S0, let's say, will have just one point. Therefore it's the trivial covering of S, just equal to S. So in the complement on S0, it's just S minus S0. But in S0, all of a sudden, two points appear. And if we look now at the structure of this scheme, it is just obtained by taking two copies of S minus S0, you see, and matching them together according to the, two copies of S, and matching them S1 and S2, and matching them together by the identity on the complement on S minus S0, exactly the construction which we have described. If there were more components than one here, then we would have the same situation, but if there are n components in the special fiber and just one in the others, then this would mean that we match together n copies of S. And that means that we have dedoubled, that we have multiplied the origin S0, so to say, of the line S n times. Now sometimes it might even happen that you have an infinity of components appearing. This will not happen, of course, with a morphism that is of finite type, like here. But let's say we start with a morphism like here of finite type, proper, let's say quite beautiful, projective, everything you want. Let's assume the general fiber is a projective line, and that the special fiber is two copies of the projective line that cut as I have said. All right, and therefore, if you want to follow the irreducible components of each fibers, we wind up with such non-separated schemes. But now let's take the so-called Picard scheme of X over S, or Picard functor. I will describe in 2 words what it is. So, for every fiber, I will give intuitive description of it, not the technical description of the functor. So, it will be, in many cases, this functor will be representable, so it will be a scheme over S. And what are its fibers? Or what are the geometric points of its fibers at any point S? All right, we take the fiber of X over S at the point S, it's a certain algebraic variety over the residue field, and we take the set of isomorphism classes of invertible bundles on this. That's the so-called Picard group of the scheme. And well, this turns out for any fixed S to be an algebraic group, commutative algebraic group, which is an extension of a discrete group by a connected group. The discrete group is a so-called Néron-Sévère group, whatever it is. It's a group scheme that is locally of finite type over the ground field, but which is not of finite type over the ground field because of the infinitely many components. And when the point S varies, all these group schemes for the number S, they make up a group scheme over the basis S, which is called, so I gave just an intuitive definition, not the formal definition of it, the Picard scheme of X over S. Now in this case, what is a Picard scheme? Well, we know that the classification of invertible sheaves on P1 is just given by the degree of these invertible sheaves, or degrees of divisor classes. So that's just over these fibers here, the Picard group would just be Z. But at the special fiber, hey, there we have two copies of P1, which match in the point. And therefore an invertible sheaf on this union is given by its degree on each, of its restriction on each of the components. So here, the Picard group is Z times Z. So we have a group scheme over S, whose general fibers are all isomorphic to Z, but all of a sudden there's a special fiber that appears, an exceptional fiber, where the fiber is Z times Z. Now let's see how these fibers match together as a scheme. Now let's fix a total degree for the general fiber, N. This would correspond to, if at the special fiber we have 2 degrees n1 and n2, then we have one component of the scheme corresponding to integer n, which corresponds to those invertible sheaves on the fibers for which the total degree n here and n1 plus n2 here is fixed. All right. Take for instance n equal to 0, and let's look at the open and closed subscheme of here, which corresponds, call it peak naught if you want, which corresponds to global degree 0. So this again is a scheme which is reduced on the complement of the point S naught to just the zero group scheme over S minus S naught. We have taken the zero element in Z. And what now for the special point S naught, there all of a sudden we get all pairs n1 and n2 with sum equal to 0, which is a group canonical isomorphic to Z. Therefore we have a group scheme that is everywhere 0 except at this one point where its fiber becomes Z. And if we look more closely at how it is built up, we see that it's obtained by taking capital Z copies of capital S, piling them up, and then identifying all the complements of the point S naught with each other by the natural way, so that only the point S naught now remains in infinitely capital Z times, and all the rest is just reduced to S minus S naught. So this is an example, by the way, of a scheme that is connected and not crazy compact. Look your finite type over S. I mean, it's just, the union of capital Z sections of the scheme over S. So, and it comes up really in the most natural way, the Picard scheme of something exceedingly simple that one meets every day. So this is about separated schemes. So many schemes are separated, some are not. And then crazy separated morphisms. We have studied those morphisms for which the diagonal morphism is quasi compact. Now practically all morphisms that one deals with are quasi separated. All schemes one deals with are quasi separated. The morphism to the final scheme spec C is quasi separated.
They're non-separated, they are all pre-schemes.
They were called pre-schemes at one time, and then finally it was unpleasant to say always pre when it was so rare that one had to make the separation axiom in the statements. So then finally one dropped the pre and now this scheme instead. Yes. So it's often important, but perhaps even more often it's quite irrelevant whether a scheme is separated or not. Because crazy separation is very often needed, almost always. All right. I would like to give some compliments about what we have said so far. About local Unitarian schemes, 2 days ago I think, there's an important fact which is a lot more significant than the fact that the underlying topological space only is locally Unitarian, namely that the structure sheaf OX is a coherent sheaf of rings. Now I should recall what this means, a coherent sheaf of rings. Let me first recall what a coherent sheaf of modules is. If X is any ringed space with a sheaf of rings OX on it, and F a sheaf of modules over OX, then F is said to be coherent by definition, if and only if, for every homomorphism of a free module into F, OXN to F, but free of finite type, but this over some open set, U, which is just the same as to give a system of n sections of F over U. We want that the kernel of this homomorphism, let's say U, is of finite type. That means that locally on U, it can be generated by a finite number of sections. That means that locally, it est, there exists locally on U a homomorphism of OM U to ON U such that the sequence here is exact, such that the image of OM goes to ON is exactly the kernel of U. So in this case, oh, I'm sorry, if this holds, and moreover, f is of finite type. F of finite type just means that locally we can find a surjective homomorphism of a free modulo of finite type onto F. But then we are concerned with the question now, what about the kernel of this? And here, this is a statement which is a lot stronger than to say that the kernel of an epimorphism is of finite type. We want that the kernel of any homomorphism of the free module into F should be of finite type. Now, this notion of coherence, I mean, there's a theory about this, which is pretty easy that you can do as an exercise if you want, which is due to Serre, and which says that the notion of coherent sheaf of modules is extremely stable. It's stable under finite sums, under taking kernels and co-kernels and images and co-images of homomorphisms between coherent sheaves. It's stable under extensions of sheaves, and an extension of the coherent sheaf by another is coherent. The only trouble with the general sheaf of rings is that we don't know at all if there are any coherent sheaves except 0. 0 is certainly coherent, but it might be the only one. And so the notion of coherence is really interesting only if OX itself, as a modulo over itself, is coherent. Then we will OX in the end is coherent also, and therefore every sheaf which is of finite presentation, which is a co-kernel of a homomorphism of a free sheaf, finite type into another locally, will be coherent too. And in this case, we will know that coherent sheaves are exactly those that are finite presentation. Now, if OX is a coherent sheaf of modulus over itself, we will say that OX is a coherent sheaf of rings. And the statement is the following: if X is a local Nusselt's scheme, then the sheaf of rings OX is a coherent sheaf of rings. It's kind of remarkable. This is one of the first things Serre proved in his introduction to algebraic geometry, in his algebraic coherence. And it's kind of remarkable that we have not really ever used this fact so far. In fact, for us, we have mainly worked with the notion of quasi-coherent sheaves, which are just good enough, and with the notion of modular finite presentation. We didn't have any use so far of coherence. However, in a number of questions, coherence plays an important part. Now let's prove the fact that OX is coherent if X is locally Noetherian. We are of course reduced to the case when X is affine, namely the spectrum of the ring A being then a Noetherian ring. And so all we have to prove is that if we have any homomorphism of OXN into OX, that then the kernel is finally generated. And we have to prove the same thing on any open set. But as we have the basis of open sets which are of the type XF, which are the spectrum of the localized rings A lower F, which are again Noetherian, we are reduced for checking this local property to looking at a homomorphism from OXN to OX that is globally defined. And now we know these sheaves OXN and OX, they are respectively A tilde N and A tilde, and the homomorphism between them comes from a homomorphism of AN into A, and taking the kernel of this homomorphism corresponds to taking the kernel of this homomorphism of modules, because of the language of the dictionary between modules over ring and quasi-coherent sheaves of modules. Now let's look at this kernel K. So the kernel here is just K tilde, and we know that K is a submodule of AN, A being Noetherian ring, A to the N is a Noetherian module of this ring, and any submodule is Noetherian. Therefore, it's of finite type. and therefore k tilde is a finite time. But we got it. So that's something pretty trivial. This coherence business. But over general schemes, you see the interesting notion is, which replaces coherence, is modules of finite sheaves of modules of finite presentation. That means that locally can be described as a co-kernel of a homomorphism of three sheaves of finite type. Now, something about the terminology with immersions. We have defined open and closed immersions. Now, beware that an open immersion is not an immersion that happens to be an open map, or such that the image of this map happens to be an open subset. For instance, take an immersion that is surjective, then it's a homeomorphism, it's certainly an open map, and the image is certainly open. But this immersion is an open immersion if and only if it's an isomorphism. But we have seen that a surjective immersion is one which is defined by a sheaf of ideals n in Y, which is a nil ideal. And of course, there may be nil ideals in OY which are not zero. There are such quasi-clear nil ideals if and only if Y is not reduced. In this case, there exist immersions, surjective immersions to Y, therefore that are open maps, but that are not open immersions. Open immersion is a very strong notion. You really want that not only the map should be open, but that the structure sheaf of X should be induced by the one of Y. Now let's be a little specific about these nil ideals sitting in a given sheaf of rings. Let's say quite generally the following thing. Let's look at a scheme X and let Y be a closed subset. For the time being, just a subset, not a scheme. Then the question arises, does there exist a subscheme of X whose underlying set is Y? And if so, are there many of them? All right, I will define a canonical one, which is the largest of all subschemes whose underlying set is Y, in the following way. I will take as ideal corresponding to this J in OX the ideal of all functions on X, or on open sets of X, that vanish in the sense of the value at the residue fields at Y. So-called, therefore, the sections of this ideal that I just described over an open set JY is the set of all sections of the structure sheaf over U, such that for every element X in Y intersects U, Fx as an element of cover X should be equal to 0. So that's really the largest possible sheaf of ideals on X that could possibly define Y, because for any sheaf of ideals J in OX such that the corresponding subscheme contains Y, for every such sheaf of ideals, it's pretty clear that J must be contained in JY, because every section of J must vanish on Y in the sense that I just said. Now it turns out, that's easily checking by just looking at the affine case again, that this sheaf of ideals here is already quasi-coherent. And in fact, when we look at the affine case, in order to check that it's quasi-coherent, as the description of this is a local description, we are reduced to the case when X is affine, X equals spec A, but then Y can be described by an ideal J in A by Y equals B of J. And there's a canonical choice of such a J, namely the unique ideal which is equal to its radical, describing Y as a closed subset. And now if you look at J tilde, which is a sheaf of ideals in OX, we see at once, by the dictionary established, that J tilde is this ideal J lower Y. And therefore, J lower Y is quasi coherent. And at the same time we see that, alright, look now at this ideal. Now I claim that if I look at the corresponding subscheme of X defined by this ideal, that this is actually equal to Y as a set. That's the underlying set that's denoted by this B of J between two bars. That is equal to Y. Here again, we are reduced to the affine case, and there follows from what I have said here. And on the other hand, we see that this B of J is a reduced scheme because we have just to check it locally on affine pieces, and there the ring of Y is obtained by dividing A by radical ideal, which is a reduced ring. And it's pretty clear that in this way we have obtained the unique closed subscheme of X, which is reduced and whose underlying closed scheme, whose underlying closed subset of X is Y. Now, endowed with this structure, Y endowed with the sheaf OX divided by J lower Y, that J lower Y is the ideal of the closed set, because we say that this is the induced reduced structure. So any closed subset of X may be viewed as being a subscheme, but if we take the induced reduced structure, which has the merit of being canonical. But of course, if we have any ideal that describes Y, it may be, for instance, Jy, the one we have just said, then if you take any power, for instance, of J to the n, it will find the same subset of Sy. So we have a lot of, a priori we have a lot of different schemes, closed subschemes of X, having the underlying set Y. In fact, if we have one such, call it Y now, defined by an ideal J, then the subschemes defined by the ideas Jn plus 1 are called the n's infinitesimal neighborhoods of Y and X. Do them like something like just the germs, infinitesimal germs with the tube around Y. And passing to the limit, we get the formal neighborhood of Y and X. Passing to the limit of Y and we can also ask the following question. Assume we have an inversion, X goes to Y, F. When is the underlying map F open? Of course, as F an inversion. When is F as a map open? So let's rather call it an open map. As F is an homeomorphism into, that just means that Fx is open in Y, and therefore if Fx is called U, this means that F induces a surjective inversion between X and U when U is endowed with the induced structure. And we have already seen that this means that such subschemes X of a scheme U are those which are defined by a nil ideal in U. And an ideal contained in the nil radical, which according to what we have just said, is itself quasi coherent radical. And therefore, we see that the inversions that are open maps, they are the so-called nil inversions, namely those for which can be described by a nil ideal in an open subset of Y. These need not be, of course, open inversions. because they are open enough that they can be described by the zero idea in some open subset of Y. So, about quasi preparation, and there's an example of schemes that are always quasi separated. If X is local in a certain scheme, then X is quasi separated. For instance, if X is local of higher type over a field, so that X is local in a certain, then X is quasi separated. Why is this? Well, we have to prove quasi separation means that if U and V are two affine open subsets, or quasi-compact open subsets amount to the same, that then U intersects V is also quasi-compact. But if X is local in a Euclidean, an affine subset of X, or a quasi-compact subset of X, is in fact an Euclidean topological space. And therefore any subset of it, for instance intersection U intersects V, must be again an Euclidean and therefore quasi-compact. So no trouble concerning quasi-separation with local Euclidean spaces. Now I think, yeah, we have also defined coherent morphisms for the old timers. All morphisms were coherent anyhow, which are those which are both quasi-separated and compact. Quasi-compact and quasi-separated. And this for morphisms, and the scheme is said to be coherent if it's coherent over spec linear, if it's a quasi-compact scheme in the absolute sense, and if it's quasi-separated. So a scheme X is quasi-separated if and only if, first of all, X is a union of a finite number of, let's say, affines. So that expresses quasi-compactness. And if, moreover, the mutual intersection of these affines, xi and xj, are quasi-compact. So that's what it means. If you want to see what it means for a morphism to be quasi-separated, well, you come by S bar, let's say, affine open sets, or more generally, by subsets that are quasi-compact and quasi-separated. Maybe that are coherent, but let's say Si affine, to be specific. You look for every I to the part of X line over Si called as Xi, and then X is separated, is coherent over S if and only if each one of these schemes, Xi, is coherent in the absolute sense. That means it satisfies the conditions just stated here. Because we know that X is coherent over S if and only if every Xi is coherent over Si. But Si being itself coherent, that means that Xi is coherent in the absolute sense. Alright, so I think the notion of coherence is pretty clear. And now, I promised last time to show the following. If F is a coherent morphism, and if F over X is a quasi-coherent sheaf on X, then the direct image of F is a quasi-coherent sheaf on S. And in fact, the same will be true essentially with the same proof for the higher direct images, R, I, F, star F. For those who know what they are. Now let's prove it. So the problem is purely local on S, so we may assume S square S to be affine. Spectrum of a ring A, and then quasi-coherent of the morphism just means that X itself is quasi-coherent. So, I'm sorry, then the coherence of F just means that X itself is coherent in the absolute sense. So we can write X to be a finite union of affines Xi. That's it. So the union is finite here, that's essential. And we know that the Xi intersects Xj are quasi-compact. And now let's see. Let's look at the restrictions of F to each of the Xi's, call this Fi. Now, if we have, it's quite clear that the direct image of F is mapped into the direct image of the restriction to F to each of the Xi's, call this restriction Fi. Because if you have a section of F over X, it induces a section of Xi. And the same if you have a section of F over the inverse image of an open subset of S, it induces a section of the inverse image of the same open set on X in Xi over the inverse image of the same open set in Xi. So we have this map here, which defines therefore a morphism from the direct image of F into the product of the direct images of the Fi. And in the same way, we have a morphism from this product into the twofold product of the Fij star Fij, where Xij is the intersection of Xi and Xj, Fij is the restriction of F to this, and where Fij is a restriction of F to Xij. And then it's general nonsense, which doesn't depend on schemes, which doesn't depend on finiteness of set of indices, which is that this sequence of sheaves on S is exact. So this sheaf here appears as the kernel of this pair of homomorphisms, known as the kernel of the difference of these two homomorphisms of sheaves. And therefore, in order to prove that this is quasi-coherent, we have only to prove that these two here are quasi-coherent. Now, Fi is a morphism of an affine scheme into an affine scheme. And we have already seen that for morphisms between affine schemes because of the affine dictionary. The direct image of a quasi-coherent sheaf is a quasi-coherent sheaf. We have made it explicit in terms of modules what it means. Taking direct images of quasi-coherent sheaves corresponds to taking a restriction of scalars and modules. So for this, no problem. Now what about this here? Here, the Xij's are not necessarily affine, but they are quasi-compact, and they are contained in affines. So therefore, on the other hand, the product that we have here, here we have a finite product of quasi-coherent sheaves, therefore it's quasi-coherent. Here also we have a finite product of sheaves. We have to prove that each one of these sheaves is quasi-coherent. That means that we are reduced now to the case of a scheme, Xij, that is not affine itself perhaps, but the set is contained in affine. So now we repeat the whole thing once again. But assuming that X can be contained, that X is contained in an affine scheme as an open subset. But then Xi and Xj can be viewed as being called this open subscheme X, called this affine scheme X prime. But now Xi and Xj can be viewed as being affine open subschemes of X prime. And we know that now the intersection of Xi and Xj is affine too. And therefore now we can complete our argument here. We know also that the Fij, the images of the capital Fij by small Fij are again quasi-coherent and get true. So that's the proof for the direct image and the proof in the case of higher direct image. Higher direct image is essentially the same. We are reduced to the affine case. And in the affine case, the higher light images in fact are zero, except for R naught, the RIF stars are zero. So there's no trouble.
Where did you use the quasi-compactness?
Because I had a finite covering of x by xi's. It is not true, so that the products of quasi-coherent sheaves I took downstairs were finite products. An infinite product of quasi-coherent sheaves is no longer quasi-coherent.
Direct sum will be a quasi.
Yes. Of course, I mean, the theorem would be false if we didn't take F to be quasi-compact. Assume, for instance, that we take X to be the direct sum of capital I copies of I, of capital I copies of S. So just piling up copies of S. So S being affine, let's say, as before. So certainly X would be quasi-separated, but not quasi-compact. And now, to give a sheaf of X is just the same thing as to give a sheaf on each of the pieces of S, each of the pieces of X isomorphic to S. You to give a family of sheaves Fi on S, indexed by the set I. This is clear? And what is the direct image? It's just the product of sheaves Fi. And therefore our statement would be that the direct image of a quasi-coherent sheaf is quasi-coherent, that the product of quasi-coherent sheaves is quasi-coherent. But this is true only for an arbitrary S, let's say, if the indexing set is finite. Let's say, except if S is discrete, I think. Already if it's a spectrum of a discrete vibration ring or something like this. It shouldn't be true that's an infinite product of quasi-coherent sheaves is quasi-coherent. I had cautioned against this aspect of formats of quasi-coherent sheaves that one has to be careful about infinite products. Now let's give a consequence of this, an extension theorem for quasi-coherent sheaves. Let's assume that let X be a scheme and U an open subscheme, and let's assume that the inclusion I is coherent. Of course, as it is monomorphism, it is already quasi-separated. Therefore, that amounts to the same as saying that the inclusion is quasi-compact. And this means that the intersection of U with any quasi-compact subset of X is quasi-compact, or else that the intersection of U with any affine open subset of X is quasi-compact. So we may also call such open subset of X retrocompact. Its intersection with any quasi-compact set is quasi-compact. All right, and let F be a quasi-coherent sheaf on U. Then I claim that there exists a quasi-coherent sheaf G on X and an isomorphism between F and the restriction of G to U. Now this is completely trivial because I take for G the direct image of F. Now it's true, whenever we have an open subset of the logical space, that the inverse image of the direct image is a sheaf we started with after canonical isomorphism. Now, therefore here, of course, here we use the fact that the direct image of F is quasi-coherent because I is quasi-compact and therefore a coherent bond. Now, so there's even a canonical choice of an extension, quasi-coherent extension. Now let's state it a little differently. Let's assume that F is already equal to the restriction of some larger sheaf of some
My friend told me,
So last time we said a few things about morphisms of finite presentation. We explained how these give rise to nice statements concerning passage to limit, so that for morphisms of finite presentation over a ground scheme, as far as symmetrical type statements are concerned, they are always reduced to the case when the ground scheme is of finite type over the integers, or if there is some bound field involved of finite type over the time field, let's say. So we are now closure of the time field. Yeah. These kind of reductions. Are there any questions perhaps concerning the last exposés?
The proof of that isomorphism between FP of SI and the direct limit of those,
Okay.
and is that only here, or is
Yeah,
that?
reverse to it.
But the hypothesis of finite presentation becomes essential at some point. Doesn't that mean this?
Everywhere, I mean, you just, the idea is that things pass to limit because things can be expressible. You see, with respect to if you have a direct system, filtering direct system of strings, the direct limit is A. So we want to say that to give a schema finite type over A is essentially the same as to give a schema finite type over one of the AIs, I beginner. So that's the yoga. And this essentially comes from the fact that when you formulate the notion of a schema finite presentation, we just did it in such a way that it means that it can be expressed in terms of a finite number of data. Let's say a finite number of, let's say the affine pieces are defined by a finite number of equations over the rank A, so these equations will have their coordinates, their coefficients in some of the AIs. On the other hand, you have to match together these affine pieces, match them together according to common open subsets that are quasi compact that themselves can be covered by a finite number of affines. And the matching data also are expressed on each of these affines in terms of isomorphism of finite presentation. So that's again something that comes to the limit. So once you have stated the theorem, I mean, there's just it's like a trivial computation. I mean, there's just one way, or essentially one way of proving it. It's pretty evident. So according to your skill, you have to do it in a more or less short, elegant way. But I mean, the main types, I think, it's always the same. So it's just a question of reductions you provide in a more or less neat way to prove, but it doesn't make any difference. So we try to find it down neatly in ETA. And the same thing for sheaves. For sheaves of modules of finite presentation. The limit. Now this whole setup of passage to the limit, the whole yoga of passage to the limit, and not only for schemes and morphisms of schemes, but for properties of schemes and morphisms of schemes. This is dealt with quite systematically in EGA, Minimum Geometry Algebraic, chapter 4, paragraph, I don't remember where I think it's part 8. Paragraph 8 and connection with constructibility of subsets, whatever is tied up with this is done in paragraph 9. So these are the two paragraphs. They are most useful statements concerning this are contained.
Can I ask?
You
talking about the certain classes of morphism which has a certain property and try to correspond like this. If morphism has such and such property and diagonal is, for example, and then this first second coordinate is
Assume that GF is an M, for instance,
right.
and that delta lower G is an M, then N is an M,
Right.
assuming only that M is stable under composition and base change, and contains isomorphisms.
Yeah.
Yeah.
And every has certain property like the quasi connect and things like that. What I'm thinking is there any characterization the other way around, like with such a property, the smallest class of morphism is such a property, and the other way around. Your condition is if F has certain property and the diagonal is in, and then F is in. The other way around, like the largest class, the smallest class with the restricting some putting conditions on the classes of morphism and try to get the property of the morphism.
Let's see what's new. So this here was a consequence of two axioms, of two properties we assumed on M, which was true in all the examples we gave. Namely, first, stability by composition and stability by base change. And on the other hand, let's say by stability by composition, we also assume that it contains the isomorphisms. Let's put these together. All right. Now, these two put together imply this property here, that whenever GF is an M and delta G is an M, the diagonal corresponding to G is an M, then F is an M. That's an easy formal play. Now the question is to find the smallest M which satisfies these conditions. Well, you take all isomorphisms.
Oh well, yeah, that's just what I.
Now the largest one is you take all morphisms. So
Well, what I mean is like, for example, if F has certain property and diagonals in the morphism class, then FG has a certain property and diagonal is in M, and you have many propositions that F is in M.
you want to know the smallest or largest class is having just this property isolatedly? Isolation, that's the problem?
Yeah, another thing is like the first, for example, if G is in M and the condition varies in proportion.
If G is an M,
yeah, that sort of theorems like that. Probably my question is too much vague. The thing is that mainly I'm asking the merit of considering the class N in this case, and your propositions and implication.
well, maybe we should. I don't worry. I don't bother so much about the axiomatic you see about general classes M. It turns out that we have about 20 or 30 really important classes of morphisms. You see, which satisfy all these properties, and one has to juggle with these a great deal. So instead of repeating this kind of argument 30 times, I mean that's the proper of the axiomatic method. I just point out once and for all this kind of implication, but what I'm really interested in are every one of these 20 or 30 classes of morphisms, of which we gave a dozen or so of examples. Maybe 2 dozens we gave, so maybe there are more than that, 40 or 50 dozen of morphisms that are everyday used, so to say, in algebraic geometry. And that satisfy these conditions here. So I don't want to make a big algebra of classes of M's that satisfy certain properties. Do any big abstract nonsense with this. It's already abstract enough. Any other question perhaps? So should I go on getting a few more classes of morphisms? So I think we will finish today with this kind of botanics of zoology of morphisms. And I guess tomorrow we will start with properties of flat and phasically flat morphisms, and say something about flat descent. The trouble is that after tomorrow there will be no class, so it's independence day. So we have only today and next week altogether. We have only five more talks left. So I don't know how much we will be able to do. But I think to give a general sketch, of some of the main notions of algebraic geometry, we should say something about classes like projective morphisms, basic projective morphisms, program morphisms. These are the basic notions. Finite morphisms, also they're extremely important in everyday work. So I think, without going too much into detail, we should review a little bit these notions. So that when you read them, I think if you work at all in algebraic geometry, you're pretty sure to read them, that you know what you're at. So let's take the notion of quasi-projective morphisms, and quasi-projective morphisms. All right. I will give, what about the definition? So, the first definition that comes to mind for morphism x goes to y for projectivity is that x can be embedded as a closed subscheme in P of E, the projective bundle associated to a quasi-clear sheaf of nucleus on Y. But however, with a restriction on E, I want that E should be of finite type, a quasi-period module of finite type over Y. So that the fibers of this projective bundle, for instance, are just union projective schemes over the residual fields. Now, if E is of finite type, then P of E is a finite type over Y. This implies that the projective bundle P of E is itself of finite type. Namely, whenever Y is affine, let's say that then P of E is a finite union of affine schemes which correspond to algebras of finite type over V, over A, over the affine algebra, affine ring of Y. This comes from the construction of P of E. We have seen that P of E can be covered as Y affine. P of E can be covered by open subsets that are indexed by the set of indices occurring in a system of generators of E. And if you finite type, you can calculate a finite system of generators. And also the way this algebra was constructed was some quotient of a symmetric algebra over E is to remember. If E is a finite type, then symmetric algebra is a finite type again. So the projective bundle P of E is a finite type over Y whenever E is a finite type. Also, it's easy to check that P of E is separated over Y. fortiori. It's crazy system.
That algorithm is.
Yes, I want
Yeah,
that there should
no.
exist a Y morphism of X into P of E.
Mhm.
Yes.
Is it necessary the finiteness condition in order to ensure that P of E be separated?
No, P of E is separated in any case over Y. But it may not be crazy compact over Y. I would suspect that P of E can be crazy compact over Y only if E is of finite time. That's certainly true over field, let's say. Or if E is free, fortunately. But I definitely want for projective morphism, I want X over Y to be of finite type. And of course, a crazy compact. Therefore, I better ask it then would be here with finite type. So that's really the first intuition for projective morphisms. We will say also that the scheme X over Y is a projective over Y. What if Y is a field? You have just the projective schemes over a field. But of course, it's a relative notion with respect to that field. A projective scheme over a field, when you view it as being a scheme with a subfield, which is a prime field, for instance, may no longer be projective because the field is too far away from its prime subfield. And still less will it be projective over the spectrum of the integers. So it's a relative notion. Yeah. So this here is a closed immersion. Yeah? So that would be the first definition that comes to mind. However, there's a difficulty. We want, of course, that that's a thing that we're introducing, that this notion we are introducing should be stable under base change and stable under composition. So stability under base change is pretty clear of the notion I have just introduced. If you make a base change Y prime goes to Y, then you get a Y prime morphism of X prime into PE prime, which is closed immersion, because what you get deduced from a closed immersion by base change is again a closed immersion. And PE prime, the base, what we deduce from P by base change, we have seen is just P of E prime, where E prime is a module on Y prime inverse image of E, so E over Y prime if you want. And this is a critical module of mankind over Y prime. So with respect to base change, our definition works nice. However, there's a difficulty for composition, I guess. Also, the notion, K, of being crazy projective, of being projective over Y, doesn't quite seem to be local over Y here, with respect to Zariski topology. It's by no means clear if we can, that when we can cover Y by open subsets such that over each of these X is projective, namely can be written as X over Yi can be written as closed subscheme of P of EI, where EI is a sheaf of modules of finite type, basically on of finite type over UI. It's not by no means clear that we can find an immersion of X into a PE where E is some equivalent sheaf of finite type over the whole of Y.
When Y is quasi-compact, when Y itself is quasi-compact.
No, it's not true either. No, it's in fact, one can give counterexamples. Even assuming all of the EI's functions, if Y is affine, of course, we may always assume that E is a free module of rank N, because E can be globally written as being the quotient of a free module of rank N. And therefore P, E itself is contained in P of the free module OY of rank N, but this is standard projective space of dimension n minus, relative dimension n minus 1 over Y. So we can always, as a composition of two closed inertial, closed inertial, in this case, when we take affine pieces over Y, over each of these affine pieces, our scheme can be embedded into standard projective space of some dimension, which can be taken common for all these for all these affine pieces if we assume there's only a finite number of them, if Y is clearly compact. All right, but the trouble is that all these embeddings of xi equals x restricted to yi into p capital N yi where capital N is big enough, these embeddings don't mesh together, you see. They don't come from a single, from just one embedding of x into p upper N lower y. You see. So here there's a real mathematical reality. So
Excuse me. Under which circumstances you have this closing embedding where P of E going to...
whenever the sheaf P is a quotient of a free sheaf of rank, let's say N. But this will certainly be true when Y is affine. Because every module over a ring is a quotient of a free module, and the module of finite type over a ring is a quotient of a free module of finite type. So the non-dictionary. Because that's what we know. Therefore, we have to. Anyhow, this last difficulty we are not going to eliminate. I mean, it can be eliminated by giving a slightly more astute definition. This fact that the notion is not local over Y. If you want to make it local over Y by taking the locally projective schemes over Y, this would be a notion that definitely doesn't behave well under composition. The composition of two such morphisms, of two locally projected morphisms is no longer locally projected. And this is a very big drawback. All right, what we do in order to get to the right definition? Well, before going over to trying to explain it, let's also say what quasi-projective should mean. Quasi-projective would be the same definition, except that instead of a closed inversion here, we would have only an inversion. And this will be the correct definition if you are working over, for instance, over an affine scheme or for instance, over the spectrum of a field. So these two definitions I just proposed, for projective and quasi-projective, will be the correct one, the one that is finally adopted, and Y is affine. So if Y is not too global. Now I'm going to modify this definition somewhat in order to get a notion that we have spread not only on the base chain but also on the composition. And how are we going to do? Well, what is a morphism first of all of X into some PE for the time being? Let's not bother whether this morphism is an immersion or a closed immersion. A morphism of X into PE, when X lies over Y, I'm speaking of Y morphisms of course. We have seen what it means by the very construction of P of E as the scheme representing a certain functor. To give such a morphism is the same thing as to give a quotient sheaf of E lower X, the inverse image of E on X, let's say L, which is invertible. So really, what dominates the situation for a projective scheme X over Y, which dominates the way of embedding it into some projective space PE, is this invertible sheaf L on X. And we will say that an invertible sheaf L on X is ample. Now let's give the definition. L an invertible sheaf on X over Y. We will say that L is ample relative to Y, or F ample, if F is a morphism that we have from X to Y. If there exists an E on Y quasi-coherent of finite type, and an epimorphism of the inverse image of this on X onto L, such that the corresponding morphism from X into P of E is A. Well, here for the impedance in general, I want to assume that E is of finite type, just quasi-coherent. Just a quasi-coherent sheaf, such that X goes to P is an immersion. So let's define this as meaning emptiness. And let's make a remark here, which is easy to prove, but it's slightly technical to prove, but it's nothing deep at all. I don't give the proof here. If X over Y is of finite type, already this implies that X is separated, of course. If X has an ample sheaf in the sense, this implies that X is separated over Y, because P of E is separated over Y, and X is a subscheme of something separated. An immersion is separated, and so the composition of something separated with immersion, therefore, is separated. If X over X is of finite type, over Y, then we may take E of finite type. I'm sorry, I have also to assume that Y a coherent scheme, quasi-compact and quasi-separated. Then we can take E of finite type. If we can find an immersion of X into PE with E a quasi-coherent sheaf, such that L is associated to this immersion, then we can even find one for which E is of finite type. I will give at least the idea of the proof. In general, so E may not be of finite type in this description, but if Y is coherent, is a coherent scheme, then from what we have said, in fact, from since we have proved about extension of quasi-coherent sheaves on schemes, it's not hard to prove that any quasi-coherent sheaf on Y, like E, is a direct limit, a filtering direct limit of quasi-coherent sheaves of finite type. In fact, we can take the EIs to be the subsheaves, quasi-coherent subsheaves of these that are of finite type. And now, of course, one would like to write, therefore, that PE is the inverse limit of the PEI, and that X being morphed by immersion into the inverse limit of the PEI, it will already be an immersion at a finite layer into one of the PEIs. So it's almost true, except that the PEIs don't make an inverse system because the transition morphisms between the EIs are injective, not surjective. So in fact, we have to replace the PEIs by the open subsets on which the transition morphisms are defined. But up to this little technical difficulty, I mean, the idea is essentially correct. And what one shows is, so instead of PI, let's say, let's write here some open subsets. UI using then of so X going to PE is in fact the system of morphism of X into the various UIs. And X going into, if you assume now that X is of finite type over Y, then the fact that X goes to P is an immersion can be checked already in the fact that it's an immersion on a finite layer into one of the UIs. So that's the idea.
Excuse me.
Yes.
How do you match this definition with the classical one? I mean, a sheaf, an invertible sheaf is ample with multiple of it is very ample.
You're quite right. I was probably running into trouble pretty soon. we will call this very ample.
And this very ample.
Yes. All right. So L is said to be a very ample sheaf if what I have said here is true. Yeah. 2.5. And therefore, we see that if y is coherent at least, then the fact that there exists an immersion of x into a projective bundle P of E associated to E critical of finite type over y can be just expressed by saying that first of all can be decomposed into two conditions. First of all, x over y is of finite type, and second, there exists on x a very ample sheaf relative to y. So in fact, let's see. Yes. So in fact, when I said that this definition I first proposed here for crazy projectivity or projectivity, that it works all right if y is affine, it's in fact true whenever y is coherent, which is really pretty wide, conditions. Whenever y is clearly compact and clearly separated. The definition I wrote down here is the correct one. So, and in this case, if y is coherent, we see that the following conditions are equivalent conditions. First of all, there exists an immersion of x into P of E with E quasi coherent of finite type, or to say that x of finite type over K and there exists L invertible sheaf on X, which is very ample relative to Y. Now, here we have therefore decomposed, when Y is coherent, we have decomposed the condition that we would like to view as meaning that F is of phase coherent into 2, X of finite type over Y. Now this is a local condition over Y. And on the other hand, there exists an L on X such that L is very ample with respect to Y. Now, for a given invertible sheaf, that it's very ample with respect to the basis, is at least when the basis is quasi compact, is a local condition on the basis. However, the existence of such an L is not a local condition. But really what is important in here is that one should have already the invertible sheaf globally. And then expressing the ampleness, or very ampleness of this sheaf with respect to Y is purely local. Now the definition in general of a quasi-projective morphism would be the following. F is said to be quasi-projective if and only if, first of all, F is of finite type, and second, there exists L in invertible sheaf on X which is ample with respect to Y. I still have to define the notion of an ample sheaf. I have defined only very ample sheaves. So before I give the definition of quasi-projective, the final definition of quasi-projective morphism. define what an ample sheaf is. It's a very slight variant of very ample. Let's first note the following thing. A few properties about the notion of very ampleness. So, A, if L is very ample on X relative to Y, and if we make a base change by Y prime, so that we get an invertible sheaf L prime on X prime, then L prime is very ample on X prime relative to Y prime. That's an immediate consequence of the definition. Because if to say that L is very ample means that L can be induced from the canonical sheaf on a projective bundle by an immersion of X into this projective bundle, and all these things commute to base change. And second, if L prime are very ample on X, then L tensor, I'm sorry, that has nothing to do with L prime here now. If L and M, let's say, are two invertible sheaves on X that are very ample, then L tensor M, which is again an invertible sheaf, is very ample. In fact, this comes from the fact that if you have two inversions of X into two projective bundles, PE and PF, which give respectively L and M as the inverse image of the canonical bundles here, then if you look at the morphism from X into PE times PF, this is an inversion again, and we get L tensor M, which is the inverse image of a certain bundle on PE times PF, which is a tensor product of the inverse images of the two bundles L and M on the two factors. And this now is it's well known that this can be induced by a canonical morphism of this product into the projective bundle associated to E tensor L by taking the canonical invertible bundle on E tensor L. So this here is the so-called Segre immersion. It comes from the fact that if you have a quotient bundle of E and a quotient bundle of F, we deduce a quotient bundle of E tensor F by taking tensor products. Therefore, we have a homomorphism of this functor to this functor, which is a homomorphism of schemes, therefore. And that's the inverse image of the canonical invertible sheaf on here is a tensor product, which I said here is pseudological again. All right. And as this turns out to be an inversion, that's pretty clear also, and therefore this composition will be an inversion. And we see therefore that if you take M equal to L, we see that if L is ample, then L squared is ample, and more generally by induction we see that all its positive powers, L and N strictly positive, are ample. I'm sorry, very ample. Yes. If L is very ample, then for every N strictly positive, L tensor N is very ample. And now we come to the notion of ampleness. It may well be that L tensor N is ample for some high enough integer N, is very ample without L being very ample. Now we will say that L is ample relative to Y, assuming first Y quasi-compact for simplicity, if and only if there exists an N high enough such that L tensor N is very ample. Then we can even, it's easy to check that then for N big enough, then there exists an N naught. This implies that there exists a node such that for every N at least equal to N naught, N tensor N is very ample. Alright, so that's the definition of ampleness for an invertible sheaf.
You don't mean for all N?
Yeah. Exists an N naught such that for every N.
Previous.
After
You've
the-
written for all n instead of the existing n.
This is
Oh, the existing n. Yes. Such that L tensor n is very ample. Yes. Now, this notion is local on Y once we assume Y to be quasi-compact. Because very ampleness being a local notion, if we can cover Y by open sets Yi, such that over each of these, when you're restricting the situation to over each of these, you get something very ample that is, for n big enough, let's say bigger than Ni, the nth tensor power of L restricted to this open set becomes very ample with respect to Yi. Then taking the supremum of the Ni's, we can assume that's a finite covering, the covering is finite. Then taking the supremum of the Ni's, we see that this condition here is satisfied. And now, of course, if Y is not crazy compact, we will say that L is ample if it's ample locally over Y, namely for over every crazy compact piece of Y or the affine piece, doesn't make a difference. The inverse image of the sheet is ample with respect to it. If Y is arbitrary, not necessarily crazy compact, L is called ample with respect to Y if it is locally over Y ample. And locally over Y we are reduced to the previous case. And now that we have the notion of ampleness, we can again make the little surrogate here. If L is ample on x over y, if we make a base change by y prime to y, then L prime is ample on x prime over y prime. This is quite evident. If L and M are ample on x, then L tensor M is ample. We can drop the very everywhere, and then L is ample, then for every n strictly positive, L tensor n is ample. In fact, here we have something more precise. Let n be a strictly positive integer, then L is ample if and only if L to the n is ample. L tensor n is ample. The reason that we say very ample for one notion and ample for the other, instead of doing this converse, calling one, the first notion we have introduced ample and the other, let's say, almost ample or something like this, is that what we call ample here is a more important notion. It's the one that technically is met with more than the very ample sheet.
I assume that the inverse of an ample sheet is not an ample.
That what?
That an inverse.
No, it's just the opposite that I last said. You see, ampleness has something to do with positivity, you see. Let's say the following. If you look at all isomorphism classes of invertible sheaves on X, this is called the Picard group of X. It's canonical isomorphic to the first Cauchy group of X with coefficients in OX star. All right. Now, within this Picard group, the isomorphism class of ample sheaves, of course, being ample is property only of the isomorphism class, is something which is such that let's write additively, as it's usually done. It's multiplication in here, although it's a tensor product. All right. Therefore, this here means that L is ample if and only if its multiple NL is ample for a given strict positive integer. So it depends only on the image of L in Picard tensored over Z with Q, which is a vector space over Q. All right. On the other hand, we see here that the sum of two ample classes is ample. And therefore, we see, in fact, that the ample classes make up a cone in the vector space over Q. Except let's say that we will say that the class in here, and this is ample, It may not come from peak x if the multiple, positive multiple is ample. So then we get here a cone, ample cone, and we see that if you look at the canonical morphism of peak x into this here, into peak x cube, that the ample set here is just the inverse image of this convex cone in here. And what will happen generally is that the intersection of this cone, which is symmetric, which would correspond to taking L tensor minus 1 for all ample sheaves, is reduced to 0 in most cases. Assume, for instance, that x over y is proper. We will introduce this notion later. So it corresponds more or less to the notion of properness. Then we can see that there exists a sheaf, no, I can give you a more general statement to answer your question. If we have an ample sheaf on x such the inverse is ample, alright, this means that the sheaf OX is ample because L tensor L minus 1. This implies that L tensor L minus 1 is ample. Therefore, in fact, the sheaf OX is ample. Of course, it's the isomorphic to its inverse. So the existence of an ample sheaf such as the inverse be ample is equivalent to saying that the sheaf OX on X is ample with respect to Y. But it can be shown that this means, well, after all, comes out pretty easily from our general theory. This means also that OX is very ample because OX is isomorphic to each of its tensor powers. At least if Y is pretty compact, this means that OX is very ample. So this means that OX corresponds to an embedding of X into projective space. But the fact that OX has a section, well, it's easily seen that in fact this factors through an immersion of X into an open substance of projective space that is already affine over Y. So in fact, this means that X is so-called quasi affine over Y, namely that it can be embedded as a subscheme in a scheme which is affine over Y. For instance, if X is proper over Y, then this implies that X is finite over Y, that it has finite fibers. For instance, over an let's say over a field, for instance, or try closed if you want, a proper scheme can have the property you state only if it's a finite, if it's reduced to a finite number of points, which is a relatively trivial situation. So if you assume that X is not quasi affine over Y, you see that this convex cone in here just defines at least also the following: if Y is quasi compact, and if L is ample, and M is any invertible sheaf that need not be to be ample, then there exists an N strictly positive such that L tensor N, L to the N tensor M is ample for this L prime and for L tensor N for this L second. So provided we have a given invertible sheaf, provided we multiply by suitably high power of an ample sheaf, it becomes ample itself. So for the structure of this convex cone in this vector space over Q, this means that this convex cone generates the whole space, provided it's not empty. This convex cone is not empty if there exists at least one ample sheaf of X with respect to Y. Then this convex cone generates the whole, because M, any invertible sheaf M, can be written as being the quotient of L prime, as being L prime tensor plus L second minus 1, where L prime and L second both are ample. So in this cone, every element of this vector space over Q can be written as the difference of two elements of the positive cone. It's a very pretty geometric situation. So we have defined ample sheaves, and now we will say that the morphism F from X into Y is quasi-projective if first of all, there exists an invertible sheaf on X such that L is ample with respect to Y. So if Y was quasi-compact, then we could even equivalently demand that L is very ample, because taking such a high power of L, again we get something very ample. But in general, if Y is not really compact, we just demand that L, that should be an ample L. And second, we want that F should be of finite type. And that's the definition. And we will say that F is projective if we have A as before and B prime, F is proper. We will study this a little later. Namely, if F is of finite type, it est F of finite type, and F is a closed morphism, transforms closed set and closed sets, and remains so after arbitrary base extension. Finite type separated, I'm sorry, but yeah, separated. But that's already follows from the existence of an ample sheaf. Separated over Y. So we need not add it here, because it follows already from A, plus the fact that F is universally closed morphism. Namely, it's closed and remains so by any base extension. Now, we have already seen that when the basis is coherent, then F quasi-projective is equivalent to what is stated here, but with N being very ample, and this again in turn means that there exists an immersion of X into some P of E, where E is an Y immersion, where E is a quasi-coherent module of finite type over Y. So we get back the definition we had first envisaged. Now what about F projective? Well, if we are in this situation where we have already immersion of X into projective bundle PE over Y, E of finite type, this morphism here is proper, because E is a finite type over Y. And then it's easily seen that the immersion, if you have this immersion here into a proper scheme over Y, then X is proper over Y itself if and only if the immersion is closed. Therefore, again, when the basis Y is quasi-coherent, to say that F is projective just means that there exists a closed immersion of X into a PE as before. So we come back to the definition as we had envisioned it in the first place. Now, these two notions, it's pretty trivial, that they are stable under base change. Very rare that we will meet with notions where stability under base change is not trivial. And now what about stability by decomposition? Turns out that indeed the two notions being quasi-projective and being projective is stable under composition. That properness, that morphism being proper is stable under composition is clear because of finite type and separated. This is stable under composition, and being a closed morphism is stable under composition. If two morphisms have the proper continuous map between topological spaces, transform closed sets into closed sets, the composition does the same. And therefore, if we take the property of being universally closed, of being closed to morphism and remaining so after base extension, it's clear also that it's stable under composition. Alright. Therefore, to prove, so F being F projective, it just means that F is quasi-projective and proper. 1. and as proper is already stable under composition, we are reduced to proving that quasi-projective is stable under composition. So quasi-projective is the combination of two notions, being of finite type and having an ample sheaf, and we'll see that these two notions separately are stable under composition. We know it already for f of finite type. So all we have to prove is the following. If we have morphisms f and g here, and if we have on x a sheaf L which is ample with respect to y, and on the y a sheaf M which is ample with respect to z, then we can find on x a sheaf which is ample with respect to z. Now, dear me, will we be able to do this? I hope that it's true. So the idea is to take L, to take the inverse image of M, and one might think of tensoring these two. So L is here, and M is, let's see. But this may not do. We will have to take the power of one of these two sheaves, and I have to remember which. So either we have to take it, we may have to take the power of L. M is a sheaf of Y, it will be the inverse image here. I think that's it. Yes. I claim that provided, so what is true is that provided we take n big enough, this sheaf here will be ample with respect to z. But now again, maybe we have to assume that Z is quasi-compact. Otherwise, the integer which we may have to take here may become larger and larger as we go further away from the given point of Z. Therefore, composition of quasi-projective morphisms, right? Is this quasi-projective or not? I'm not quite sure anymore. It will be at least if the scheme Z is quasi-compact, therefore Y and X. Y will be quasi-compact because G is quasi-compact and X also. So alright, so provided we are working with quasi-compact schemes, let's say, composition of quasi-projective morphisms is quasi-projective. So I think, I should check whether this restriction is needed or not. I don't really remember. For this fact here, that provided Z is quasi-compact, that this is ample for n large, I won't give the proof here. I just refer to EGA chapter 2 somewhere, where you will find chapter 2 paragraph 2 or 3, something like this, where you will find the suite of ampleness and projective, quasi-projective morphisms.
Could you give a rough idea of the proof? Could you give a rough idea of the proof?
Rough idea of the proof. All right. So M, we may already, you see, to say that this is ample is the same thing as to say that any given power of it is ample. So with some fixed k, and so taking k large enough, we can already assume that m to the k is very ample, and that L to the k, which I have raised to the nth power then, is very ample. So I assume L and m are already very ample. This doesn't really change the problem. So m is deduced from an embedding of y. I try to, so what I'm saying here maybe is not too useful for the proof. I just try to recollect the geometric picture. So y is induced through immersion of M is induced through immersion of y into projective space. Over Z. That's it. Where E is a quasi-coherent modulo on Z of higher type. Alright. Now what about L here? It's deduced from embedding X into some PF over Y, where F is a sheaf quasi-coherent of higher type over Y. Alright. Now the trouble is, I think, that this sheaf F on Y how are we going to? Yes, now I see. This sheaf, if this sheaf on Y came from Z, you see, then I think things would be yeah. Maybe I want to try now to get back the idea, because we might lose 5 or 10 minutes or so. So maybe I tell you tomorrow. That's all right. Because here it's I have to be slightly careful at this point. It's nothing deep, but one has to do it right, and I kind of get mixed up. Well, that's about, yeah. I think that this proof here is, in fact, this statement is perhaps the only delicate statement in whatever I have said so far. So I think that's all we would like to say about quasi-projective and projective morphisms. So still, I mean, it's pretty accurate that these are the morphisms that factor through emergence or closed emergence into a projective bundle associated to a E. Quasi-coherent sheaf of finite type. It's true with the slight restriction that's the basis. Could be coherent. Now, about proper morphisms, I have said almost all I had to say. So, a morphism is set to F x goes to y is said to be proper if it's first of all of finite type and separated and moreover universally closed. Now, all these three notions of which we take the compositum, finite type, separated, universally closed, is clearly stable under base change. Being a closed morphism is not stable under base change, but once we said universally closed, we just make it stable under base change. And it's stable under composition, and therefore this notion is stable under composition. Now, if I have already said that fx is quasi-projective over y, therefore at least locally over y can be embedded into some projective bundle, then x is proper over y if and only if this immersion is closed. More generally, we have the following. Let's say if x over y is proper, and if z over y is separated over y, then any morphism g from x into z, any y morphism, making this triangle commutative, then g is closed. In fact, to say that a given morphism is proper once we know that it's of finite type and separated, just means that any morphism of X into something separated over Y is closed, and that the same property is conserved after any base change. So let's say it here. So this last condition in presence of the others, I guess. No, even without the others. This last condition is explained by saying that every morphism of X prime, something deduced from X or Y by base change, every Y prime morphism, and we make a base change here, of X prime deduced from X by base change into some scheme, call it Z over Y prime, into some Z separated over Y prime is closed. That's the equivalent. Now, assume that Z is proper over Y and therefore separated over Y. And that G is an immersion. F being just of finite type. So you have a scheme of finite type over Y. You have an immersion of the scheme, a Y immersion, into a scheme which is proper over Y. So this implies, as D is separated over Y, that F is not only of finite type, F is also separated. Because X is a subscheme of C which is separated over Y. Alright? Then we see that F is proper over Y if and only if the immersion G is closed. Because if F is proper over Y, then G is a closed map, and therefore being an immersion, it's a closed immersion. And conversely, if G is a closed immersion, of course it is proper. A closed immersion is proper, and therefore this composition is proper as a composition of two proper morphisms. So let's write down here that closed immersions are proper. So when Z is a projective bundle over Y, then we see in this way that the projective schemes over Y are just those which are, if we define them as here, quasi projective and proper, they are exactly those that when Y is coherent, let's say that Y isomorphic closed subscheme of some PE. But we should say also that there exist, even over an algebraically closed ground field, there exist proper schemes over this ground field that are not projective, that cannot be embedded in projective. So projective implies proper. In fact, closed immersions implies projective implies proper. What's this? We have these but we don't have an implication that proper implies projective over any ground field. We can find proper schemes that are not projective. However, there is a so-called Chow's lemma, which shows that to a certain extent proper schemes can be reduced to projective schemes by a certain type of Delisard, so at least partially equivalent to projective schemes over ground field. So, but that's something slightly technical we won't state it here.
So have you proved that projective implies proper? I mean,
yeah, it's not quite trivial. It's true, and So we have to prove that for every closed subset of P, the image in Y is closed. Now, the idea is to make a passage to limit to reduce to the case when Y is Noetherian, and then to use a evaluative criterion. It's slightly technical.
You know, down with elimination is
No. Anyhow, I think there's something to be proved. That's quite. So this is in fact.
Without choice. Without choice limit. Prove without choice limit.
Yes, of course. Yeah. You see, it's not really hard. You see, but you see, if I wanted to prove it here, it'd take me half an hour or so. It would, with some preliminaries on valuation rings and such things. I would have to develop something like a evaluative criterion for openness. And all these things are kind of, how should I say, they're kind of easygoing, but they take some time. So I don't think, perhaps I won't give the proof here. So that the closed inversion is projective is quite trivial. That something is projective is proper, or what amounts to the same, that Z projective bundle P of E, where E is crazy, is where E is real and a finite type, that this P of E must be proper over the basis Y. This is not quite trivial. I mean, it's not logical to have really something to prove there. Maybe, however, I can give an idea of the proof by, although I will use another criterion instead, which I will not prove, but I think it's a criterion which is quite useful. And it gives the right feel of what it means for modeling to be proper. So, you see P of E is closed in the being proper over Y is something local over Y. So we may assume Y to be affine, and therefore we may assume that E is a quotient of a free modulo-finite type. And therefore E is contained in standard projective space Pn over Y, which comes by base change from Pn over Z, over spectrum of Z, by base change from Y to spectrum of Z, which is the final object of the technique. So all we have to prove is that PNZ is proper over spec Z. So we are now reducing it to a Noetherian situation. And now, let's state the evaluative criterion of properness. It's the following. Assuming Y to be locally Noetherian, and F morphism from X into Y, F proper is equivalent with F of finite type on the one hand, so this we have to assume anyhow. And second, for every Y prime over Y which is a stroke, which is a spectrum of a discrete valuation ring. Spectrum of a discrete valuation ring. So a discrete valuation ring is just a principal ideal domain which has only one prime, different from 0. If you look at the inverse image, X prime or Y prime, then, and if you look at, the spectrum of a discrete valuation ring is, stroke has just 2 points. It has the general point eta and the closed point S. S being in the kernel of eta, but not vice versa. So eta, the general point, is an open subset. There are just 2 open subsets that are not empty. There is the open subset reduced to the general point, and there's the whole of Y prime. All right. Now I look to the sections of X prime over Y prime, and this is by a restriction. This gives up sections of X prime lower eta, the restriction of X prime over eta. That's both X prime lower eta can be both as being the general fiber or as being the restriction of X prime to the open subset eta. So by eta we have this map. And this map should be bijective. Namely, to give a section of x prime, after we make a base change so that y becomes a stroke, we want that any section should be, how should I say, that any rational section of x over y, I mean any section given over the general point, that is any rational point of the general fiber over kappa eta, should come from a uniquely determined section of x over y, once we replace y by something which is a stroke. So, why must be, let's prove that it's necessary. That's sufficient is slightly less trivial, but let's prove the necessity of this property. For properness, of course, x prime being proper over y prime, we can forget about y, and we have just now a basis which is a stroke. Now, first, why is this injective? This comes from the fact that something proper over basis must be separated over S. Therefore, two sections must be known when we know it. As the basis y prime now is reduced, a section must be known when we know it over a dense open subset. And eta is the dense open subset. In fact, the injectivity here is equivalent with separation of x over y. So that's the evaluative criterion of separation of the morphism. But we want still more, we want a lot more, we want the morphism to be proper. So why should it be surjective? All right. Take, so wherever should we call y now the stroke? All right, let's go y to the stroke, that's more natural. All right. So we have eta here, we have the general plus x eta, and we have a section of x eta over eta. So that's just a point of x of x eta, which is rational over eta, such that kappa of x is isomorphic by the natural map to the ground, to the residual field at eta. All right, now take the closure of x in capital X. Call this closure, call it, what do I know, y prime. So it's a closed subset of x. And you will endow it with the induced reduced structure. All right. And look at the induced morphism here. Now, this morphism has an image which is closed because x goes to y is a closed map. And therefore, as the image contains eta, the image must be the whole of y, because y is a closure of eta. So y prime goes to y is surjective. On the other hand, it's birational, because, kappa x is isomorphic to kappa eta. And on the other hand, y prime is separated over y. This we have already, because of what we have said before. Y prime is separated over y because x is separated over y, and x is separated over y. Because of evaluative criterion of separation. And therefore, y being normal, you see, if dimension 1, then by the main term of the risk or whatever, it's in fact more trivial here. It's in fact, it's essentially the definition of evaluation of the maximal local subring of its field of fractions and sugar. So, Zariski's main term will be too deep here. Y prime goes to y must be an isomorphism. And therefore, it corresponds to a section of x over y, because it's the inverse dimension. The inverse of this isomorphism is a section of x over y. Let's say the following: if y is a spectrum of a discrete vibration ring, and if x is proper over y, that's it, then this map here, and if x is, if the map from x to y is a closed map, so not even universally closed, just closed, then this map is bijective. But if I assume that the map is universally closed, then the same will be true after any base change. Assume that the map is universally closed, do no longer assume that y is a stroke. But for any base change, with a y prime, a stroke, that will be true that we have bijective map here. And now, So in fact, we didn't have to assume f of finite type for this here. In fact, what we have, if f is universally closed, then this is always bijective. But if we want the criterion of properness, then of course we should also assume f of finite type. All right, now that's the evaluative criterion of properness. And let's apply this to P of E, let's say. So as we know that forming a projective bundle associated, well, to a module is compatible with space change, we are just reduced to proving the following. If Y is already a stroke, and if we have the spectrum therefore of a discrete valuation ring A, and if we have our sheaf E over Y, which corresponds just to a module M of finite type over A, quasi-equivalent sheaf of finite type over Y corresponds to module of finite type over A, we have to prove the following thing, that if capital K is a field of fractions of A, which corresponds therefore to the general point of Y, so making the basic extension, we have M lower K, the vector space over K of finite dimension, which corresponds to this. We have to prove that if to every quotient L of M, which is a free module of rank 1 over A, invertible, that means SA is local, invertible is the same thing as free of rank 1. We associate LK viewed as a quotient of MK. We have in this way a bijective map. And this is pretty clear because when the injectivity is kind of trivial, I guess, isn't it? Because what should I say? So we have to show that invertible quotients of MK and invertible quotients of M correspond to each other one-to-one way. So assume that we start with an invertible quotient LK of MK, which is just MK divided. We can of course also assume M here to be without torsion because sections don't change. Anyhow, we have said that we could assume M to be free of rank N. All right. So M is contained in MK. All right. Now that's it. So LK can be viewed as being the quotient of MK by a vector subspace of codimension 1. Now associate to this H equals the intersection of M with HK. Then it's pretty clear that M over H will be a module over A that on the one hand is of rank 1, on the other hand is without torsion, in a finite type. Therefore it will be locally free of rank 1 because A is this evaluation ring. So the module of finite type without torsion over marginal principal ideal domain is free. All right. And of course, if you take M divided by H equals L, then L lower K is just what you started with. I mean, it's kind of clear. Comes out kind of trivial. So evaluative criterion is really one of the most handy criterion for checking properties. So I think that's about all we have to bother about for homomorphisms. Now I want to say something about finite morphisms. We have already and integer morphisms, and maybe I should first make a little statement of quantitative algebra, but algebras that are integer over the round ring. Let A be a ring, and let B over A be an A algebra. All right. and assume, yeah, and let X be an element of B, then the following conditions are equivalent. X is integral over A in the following sense, that there exists a polynomial in one variable with coefficient A with leading coefficient 1, f equals, let's say, t to the n plus a1 t to the n minus 1 plus etc. plus an. So leading coefficient here is 1, such that f of x is equal to 0. That's a classical definition of elements that are algebraic over a ring, that are integer over a ring A. And this is equivalent with saying that, let's see, this slide, I guess so, that A of x is the algebra generated, subalgebra of B generated by x, is a module of finite type over A, and this is still equivalent with saying that X is contained in a subalgebra B prime of B, subalgebra, which is a module of finite type over A, or as we say, which is finite over A. In algebra over A, which is a module of finite type over A, we will just call finite over A. Therefore, to say that X is integral over A in this sense, as satisfying an equation with leading coefficient 1 with coefficient A, is the same to say that the ring subring it generates is finite over A, or to say that X itself is contained in a submodule, in a subalgebra of B that is finite over A. So this is the general description of integral elements over another. We will say that B is integral over A if every x in B is integral, and this is equivalent to saying that B is the direct limit or the union of subalgebras Bi finite over A. So this is some general nonsense notions of commutative algebra. So any subalgebra of an integral algebra over A is an integral, and any quotient algebra of an integral algebra over A, quotient by an idea, is again integral. And integrality, if, on the other hand, if B and B prime are two integral algebras over A, then their tensor product is, in fact, if we have, we can say the following thing: if B is any algebra over A, then there exists, then let's say the elements x and b that are integral over A make up a subalgebra over B, which is the largest subalgebra of B, which is integral over A. This is called the integral closure of A and B. So there's the notion of integral closure. All right, so I think we have to have these notions in mind. Also, we have transitivity, let's say, if B is integer over A, and if C is integer over B, then C is integer over A. All these things come out quite trivially once we have prove this here, and this is, once you have stated it, it comes out very easily too. I mean, but this is really the important thing to remember. All right. So now, what about the morphism? We will say that f is an integral morphism, respectively a finite morphism, if the following is true. First of all, f is affine. So I recall that f being affine means that the inverse image of opposite of y is affine, but it also means that x can be written as a y scheme as the spectrum of a sheaf of algebras A, which is quasi coherent as a sheaf of modules. Call it perhaps rather V now, to harmonize with the previous rotations. B being a quasi coherent sheaf of algebras. And B now says, we have seen that the affine schemes over Y form a category equivalent to the category of these algebras B over A that are quasi coherent as sheaves of modules. And B, we want to say something about this sheaf of algebras B. B is integral. Hey, how do you say? Integral or integer?
Integral.
Integral. Is integral respectively finite over y. Now I have to define what I mean by this, that the sheaf of algebras is integral over the sheaf of rings. So the notion which I have defined in the absolute sense here for just algebras over rings, I now have to extend to sheaf of algebras over sheaf of rings. But all right, for finite, I mean that's pretty clear. We will mean that the sheaf of modules underlying B should be of finite type. When Y is affine and with of the spectrum of a ring A and therefore X will be spectrum of an algebra B over A, this just means that B as a module over A is of finite type. So this checks with the notion of an algebra being finite over a ring. And B integral, I mean, as for all of these notions, the extension to sheaf is about trivial, whether we are on schemes or not. In fact, that the sheaf of algebras is integral. It means that every section of B is locally, at least, over Y, a solution of an equation whose coefficients are sections of OY and whose leading coefficient is 1. That's one way of stating it. For example, sheaf of algebras over generally ringed spaces, whether locally ringed or not. But when we want to state this on a scheme, then again, everything boils down locally to an affine situation with with Y the spectrum of A and X the spectrum of B, and then it's pretty clear that to say that OX, that the sheaf B tilde on Y is integral over OY is just means that B is integral over A. The dictionary just works very smoothly. So here we have the notion of integrality, and we see and of integrity, one says, of a morphism being integrity or integrality, and being finite. Now, this notion again is stable under base change. That's pretty trivial, because the notion for an algebra, sheaf of algebras to be quasi-coherent and finite or integral over OY is stable under base change. And also it's stable under composition, which is pretty clear too, because if we have z over x, which is integral, let's say, so x is defined over y by a sheaf of algebras B, which is quasi-coherent and integral over OY. Now, on the other hand, quasi-coherent sheaves of modules on X correspond just to sheaves of modules M on Y, which are quasi-coherent and which are sheaves of modules on the B, in fact, and which are quasi-coherent on OY. And sheaves of algebras on X correspond to M's that are in fact algebras over V, so call them C now. And Z over Y being viewed as being an affine scheme over Y is just obtained by taking the spectrum of C viewed as being a scheme over Y. And now all we have to remark is that if C is integral over V and V is integral over Y, then C is integral over Y. So that's one way of saying it intrinsically. You can also reduce to the case when Y is affine. Then everything reduced to the case. Then everything is affine, B is integral over A, and C is integral over B. Therefore C is integral over A. And the same thing with finiteness. If B is finite over A and C is finite over B, it's pretty clear that C is finite over A. Alright, so what about diagonal morphisms? Before wondering this question, let's state the following. Now this is not quite trivial, it's quite important. Integral morphisms are proper. Of course, integral morphisms are finite. Finite implies proper. In fact, finite means integral and of finite type. That's pretty clear. That just reduces to the statement that in algebra B over ring A is finite over A if only it's of finite type as an algebra and it's integral over A. Alright, now integral implies universally closed. Of course, the important implication is this one, that integral implies universally closed, because finite means integral plus of finite type, so finite implies of finite type and universally closed. And of course, I'm sorry, and we should know also that it implies separated. Separated and universally closed. And therefore finite implies proper. Now this here, let's see what it boils down in terms of quantitative algebra, that an integral morphism is universally closed. It's separated because it's affine, of course. So this is trivial. But why is it universally closed? So this property, so we have taking a base change, we are just reduced to proving that it's closed. That's the image of a closed set is closed. On the other hand, a closed immersion is finite. That's quite trivial because this just amounts to saying that if you have an algebra B over A, which is a function of A by nu J, then it's finite over A. And now, so we are reduced to the following. We have x over y, which is integral. We have a closed subset x prime of x, and we want to prove that f of x prime is closed in y. Now, we can assume that x prime is equal to x, because otherwise we just take x prime with reduced structure, and we take the induced morphism. And this is a composition of a closed immersion and of an integral morphism, therefore it's integral. So all we have to prove is that f of x is closed. So we can already assume that f of x is dense in y, otherwise we replace y by the closure of the image. So we can assume that f is dominating. We can assume also x and y reduced. That doesn't change anything. And then we have to just to prove in this case that f is surjective. So that's what you have to prove. Now, this is again purely local on y, therefore we can assume y to be affine. Hence x affine. So y corresponds to ring A, x to ring B. The fact that f is dominating, which is an algebra over A, the fact that f is dominating means that it is contained in B. That's it. Because x and y are reduced, so saying that it's dominating means that A goes to B is injective. We have seen this. And now that f is surjective means the following thing, that for every prime ideal P in A, there exists a prime ideal in B that induces it. Now, all right, so that's the statement. That's the so-called going up lemma of Seidenberg. That's a well-known statement in commutative algebra. Fb is an algebra of A that is integral over A, that it contains A, then every prime ideal of A is induced by a prime ideal of B. So let's give an example, which we have already used, I think. If you have a field, let's say K, and if K prime is an algebraic extension of K, so it's a field extension. It's, to say that K prime is algebraic over K just means to say that K prime is integral over K. Now assume we have a scheme X over K, and let's look at the scheme deduced by base change to xk prime. And let's look at the projection from xk prime to x. This is a closed map. It's the image of any closed structure of xk prime. It's closed in X. We have used this fact plus the fact that this map is open. For the fact that this map is open, we didn't have to make any assumption on the field extension. But to prove that it's a closed map, we have to assume that the field extension is algebraic. All right, so I think this will settle our review of some of the main classes of morphisms, with the exception of the flatness question that we are going to speak about more systematically starting tomorrow. So yesterday we introduced some more class of morphisms. We spoke about projective and quasi-projective morphisms. The homomorphisms, which were a particular case of universally closed morphisms. Then we had integral morphisms and finite morphisms, yes, I think. Integral morphisms and finite morphisms. So then later we are going to write down the diagram to make it have a few implications.
Should we fill it in as a homework? Could we fill it in as a homework?
If I had done a homework,
I mean, a diagram and implications to be filled in as a fill in the blanks.
no, I think the implications are all that I'm going to state are all trivial. Maybe I write down a diagram at once to so yeah. So finite morphisms, they are projective, and projective morphisms are quasi projective. Now finite morphisms, they're integral. In fact, the finite are just those which are integral and of finite type. As projective are of finite type, you see an integral morphism is projective if it is finite. Alright. Now integral implies affine. In fact, it can be shown that integral is the same as affine plus universal closed. Now all these morphisms are separated. Alright, so, but we can go on. Projective implies proper.
Yeah, I got it.
And proper also implies separated by definition, and proper implies universally closed. But integral also implies universally closed. In fact, proper, you recall, is universally closed plus finite type plus separated. Here we have, now we can also fill in a little more here. Finite immersions, closed immersions are finite. Closed immersions are finite. Now we have quasi-compact immersions. Quasi-compact immersions. They are particular case, and closed immersions are quasi-compact immersions, of course, and quasi-compact immersions are projective. I'm sorry, I have to, they're quasi-projective. But I will, but we have here an extra notion which I will explain slightly later. It's the quasi-affine morphisms. It will turn out that the quasi-affine morphisms include the quasi-compact immersions. And then, instead of writing directly the implication of quasi-compact immersions to quasi-projective, I'm going to write it like this. So this we have still to say a few words about, and we started saying a few words about it yesterday. All right. And now, what about finite on the other hand will imply quasi-affine, and there's another, and in fact there will imply affine. In fact, finite morphisms are affine of finite type. Finite morphisms are affine of finite type. and I'm sorry, crazy affine of finite type are crazy projectors. So here is a diagram in which everything has been defined except the crazy affines. And here I insist that I take crazy affines of finite type in order to be able to write them, imply crazy projective. Crazy projective, I recall, means that on the one hand, it's of finite type and existence of relatively ample sheaf. So here is a diagram including most of the last notions we have seen. Now I have to give, so all those that are in the blackboard here, I think are in this diagram anymore.
Is it trivial that affine plus universally closed imply
No.
integral?
No, it's not true. But it's true. What we have seen is this one here. You see, integral we have seen is universally closed. It's closed in the universal function. Also, it's affine. The converse is a lot subtler. Let's also state the following thing, which is not trivial either. So that finite is the same as integral of finite type. So let's underline here statements that are kind of slightly subtle. So this one here is also the characterization of finite morphisms as being the proper morphisms with finite fibers. So this is true. Of course, that a finite morphism is proper and has finite fibers. Is clear. You see, it's proper because it's it's this include that has finite fibers comes from the fact that the finite scheme or a field is finite as a set. It's the converse that is that's what I want to indicate proofs here. But all these things are somewhere in EGA. But this kind of makes it gives another intuitive meaning of finiteness, meaning something almost a topological meaning. You see, in the analogous situation, if you're working with the complex numbers, then a morphism is proper if and only if the corresponding morphism for the locally compact underlying spaces when using the topology of the complex numbers for the corresponding for the if you have schemes of finite type over or local finite type over the complex numbers, then the C-valued points of these schemes, that means the closed points, they form a topological space, the underlying space of the analytic variety. And the morphism is proper here if and only if the map of topological spaces is proper and separated, let's say. Now, so therefore, properness makes it, in this case, a purely topological meaning, and the fact that the fibers are finite, I mean, is also a purely topological, in fact, that's analytic meaning. So in this case, finiteness of the morphism is a purely topological property. The fact that this rather coarse property implies that you can express x over y as being the spectrum of the, in this case, coherent sheaf of algebra is not altogether trivial. It's true. And the analogous statements, by the way, in all these notions of all these classes of morphisms make a good sense also for analytic space. They're exactly the same. The same inclusions. The story is roughly the same. Now, I have to make some rectification about things that I said last time. I didn't tell too properly the story of ample sheets. I didn't expect that I would say something about ample sheets at all, and then I discovered that it's really hard to speak about crazy projective morphisms or projective morphisms without speaking of ample sheets. So I will give here a statement that I took in EGA. and which tells part of the story. So I will take first the absolute case, where the basis is nothing, where we have no basis, or where the basis is an affine scheme. So I will define what is an ample sheaf on a scheme. And then we will relativize it. So let X be a scheme, and I assume X to be coherent. So call it a proposition, but we won't prove it here. Well, it's pretty elementary. You will find it in chapter 2 of EGA. And a coherent scheme that is quasi-compact and quasi-separated, and L, an invertible sheaf on X. And we will state a few equivalent conditions on this invertible sheaf. So the first is, but we will introduce some more notation also. I look at the sections of powers, tensor powers of L over X, call S lower n the set of these sections. For any n, we will restrict here in fact to n strictly positive or 0. These Sn make the components, of course, of a graded ring, because a section of L tensor n and the tensor of L tensor n multiplied with a section of L tensor n plus m. And in fact, in EGA you will find some equivalent conditions which introduce the homogeneous spectrum of this ring S, like some of the SNs. As we have not defined the homogeneous spectrum, I won't speak about this. It's slightly technical note, which is not so very important. All right. So we look at these SNs, and now if F is a section of L tensor n, and is an element of such Sn, we can look at XF, which is defined just in the same way as if F was a section of the structure sheaf. Here it's a section of a certain invertible sheaf. XF is a set of points of X, where the value of the section, the reduced value, which is an element of the reduced fiber of this sheaf, is not 0. So it's the largest set on which this section, so which is invertible, has an inverse, which would be a section of L tensor n power minus 1. Alright, so XF is defined in an obvious way. So, I mean, locally it's just the same. Locally the sheaf being invertible is just a free sheaf of rank 1. So F locally looks like a section of the structure sheaf. And look, in the description of XF is the same as if we had a section of the structure sheaf. Of course, XF intersects XG is equal to XFG if F and G are elements of Sn and Sm respectively. Yes?
You want the tensor symmetrized, or is that a symmetric algorithm?
No, it's just not symmetry algebra of anything, no. The Sns make up an algebra, but it won't be a symmetric algebra of something. Alright, so this is just some notation. So the XFs form a system of open sets which is stable by intersection. And now I proceed to state the first condition. The XF is for variable f in Sn, n is also variable, make a basis of topology. Now this is equivalent to the following, let's call it A prime. Those XFs that are affine form a basis. All XFs need not be affine. They would be affine if X was proper over an affine scheme, for instance, and therefore projective over the scheme if we assume that these conditions are satisfied. But otherwise, for instance, if you take now condition B, that says something about arbitrary sheaves, quasi-coherent sheaves of finite type. For every quasi-coherent sheaf of finite type, there exists an n naught such that for every n greater or equal to n naught, f twisted by n to the tensor power n, for this, that's the standard notation f of n, is generated by its sections. To say that a sheaf is generated by its sections, and that a set of sections generates a sheaf as a sheaf of modules is clear. And to say that a sheaf is generated by its sections just means that it's a quotient of a free sheaf. That means that Fn can be written as a quotient of Ox power I, where I, for instance, the indexing set can be taken as being the set of sections precisely of n if you want. But as f of n is of finite type, and as x is crazy compact, being coherent, then it's pretty clear that this indexing set here, you can take it even finite. If f is generated by its sections, it's generated by a finite number of sections. So this means that f of n, for n big enough, is a quotient of a sheaf Ox of m. That means we have such an exact sequence. Or else, if you twist back by minus n, you see, cancelling by the two members here by L to the minus n, this means that f is a quotient of Ox m to the minus n. That means, therefore, that every sheaf of finite type, quasi-coherent sheaf of finite type on X, can be written as a quotient, not of a free module of finite type, but of a free module of finite type twisted back by some n for any sufficiently large n. That's what it means. And B prime is this variant of this, same as B, but with f contained in X, with f being a quasi-coherent sheaf of ideals of finite type. All right. So this is true without any other finite restriction than X being coherent. But now we will say something more, as if we assume that X lies over some Y, where Y is affine. We can take, for instance, Y to be the spectrum of Z, but any other affine, we can take any other affine scheme. So this just means that we have Y is a spectrum of a ring A, and to give such a morphism, which I recall means that we have a homomorphism of this ring into gamma x OX. That means that the sheaf of rings on X, the structural sheaf is a sheaf of A algebras. Alright. Then these conditions are, for these conditions too, it is sufficient that the following condition should be true: that there exists an n strictly positive such that L tensor power n is very ample with respect to Y. And very ample with respect to Y means that it can be induced by the canonical sheaf on a projective bundle over Y, corresponding to a certain module over A, or sheaf of quasi-coherent sheaf of modules on Y, by an immersion of X into this projective bundle, an immersion, I say. So this condition is sufficient, that there exists a power of L with positive, strictly positive exponent, such that L tensor n becomes very ample. And a fortiori it's sufficient that there exists an n naught greater or equal 0, such that L tensor n is very ample for every, relative to Y, for every n at least equal to n naught. So this gives, yes?
If two sheaves are generated by their global sections, is the same true for the tensor product?
Yes. Yes, because I mean the tensor product of these global sections generates the tensor product. Yes.
So there in B is equivalent for a given n.
And
So in condition B, condition B is equivalent to the existence of a given n
Yes.
naught for which the twisted sheaf is
Yes.
generated by.
yes. Yes, I think so. In fact, the stronger thing will be true. All right. And these sufficient conditions are also necessary if we assume that the morphism F is a finite type. Now yesterday I kind of got things a little wrong. I defined a sheaf to be ample if it satisfies condition C or C prime. It's ample relative to Y, but here let's say Y to be affine. Now this is reasonable only if F is a finite type. In fact, the right notion which makes good sense, which works very nicely, even without F being assumed to be a finite type, in fact, without the existence of any F being assumed beforehand, I mean without giving any F beforehand, are these notions here. And if these conditions are satisfied, you will say that L is ample. That's the definition. So the ampleness is defined by these conditions, not by the fact that a certain power should be very ample. In fact, the condition which is most widely used is condition B here. That then that any sheaf provided is twisted by a sufficiently high power of L, any crazy coherent sheaf of finite type, will be generated by its sections. However, if we want to define quasi projective, all right. So this is the absolute story, and now what about the relative one? Let's give a morphism F from X to Y. Now Y no longer is assumed to be affine. And let L be a sheaf, an invertible sheaf on X. Then L is said to be ample relative to Y if there exists a covering. Well, we can say it either in this way, there exists a covering of Y by open subsets Yi that are affine, each Yi affine, such that the restriction of L to the part Xi of X lying over Yi is ample by every I. And it turns out it's pretty easy to see from the definition of absolute ampleness that if this is true for a covering by open affine sets, then it's true for every affine open subset of Y. But it's understood implicitly here that we want that the Xi's should be coherent. Namely, I want F to be coherent. So there will be no ample sheaf on X relative to Y unless F is coherent. In fact, coherent means quasi-compact and quasi-separated, but the conditions will imply that F is already separated. Here, in fact, it turns out that if there is such an ample sheaf, this implies that X is separated. Now the notion of ample sheaf relative to y, as well as the notion of very ample sheaf relative to y, is clearly stable under base change. Of course, we could state this relative notion of ampleness by trying to restate these conditions in a relative way directly. At least for B and B prime, this can be done pretty easily and if y is quasi compact, this can be done pretty easily by saying that for every quasi-current sheaf f on x, if you look, then Fn for n big enough, when we twist f by high powers of L, Fn is generated by its sections relative to y for n big enough, which means that if we look at the direct image of Fn, this is a sheaf on y, and its inverse image, this is mapped again to Fn, and we want to state that this is an apimorphism. This is surjective if n is large. So that's an equivalent condition. Because when we have stated this, you see, when y is affine, this just means the condition B. And on the other hand, it's a condition which is stable under restriction to an open subset of y. So that's an intrinsic way without restricting to open affine subsets of stating the ampleness of a sheaf. For every quasi-current sheaf of higher type F, the homomorphism here is surjective for n large, and therefore, if y is coherent, so that this sheaf here, which is a quasi-coherent sheaf on y, is a direct limit of quasi-coherent subsheaf of higher type, then we will have an epimorphism like this, where EI is a certain subsheaf of higher type. And this will mean that Fn can be viewed as the image, as a quotient of the inverse image of a quasi-coherent sheaf on y. That's again a different way of stating it. That this quasi-coherent sheaf on y, if y is quasi-compact and quasi-separated, y is coherent, can be taken to be of finite type moreover. So in this case, this sheaf here appears, the sheaf F appears as the inverse image of as a quotient of the inverse image of a quasi-coherent sheaf of higher type on y, twisted by minus n. So also this here can now be made relative, and we see that if it's some power of L, invertible sheaf on x, assuming, if there's some power of L, positive power of L, is very ample, then L is ample, and the converse is true if we assume that f is of finite type and moreover y quasi-compact. So if f is of finite type and y quasi-compact, then L to be ample relative to y just means that a certain power of it is very ample. Alright, so that's the situation. And now these notions of ampleness and very ampleness are stable under base change. And now I still have to say what happens when we take a composition and there I again made a misstatement. So here is the correct statement. We have two morphisms F and G. We have to assume indeed that Z is quasi-compact. That's pretty easy to see that the statement would be false without this. And we have a sheaf, invertible sheaf L on X and M on Y. And the statement is that if L is ample, respectively very ample, so there's two statements, one with ample, one with very ample, relative to F, and if M is ample, respectively very ample, relative to G, then there exists an N naught such that the sheaf L tensor with inverse image of M tensor N is GF ample, is ample relative to GF, or GF very ample in the very case for every N is equal to N naught. Sure enough, I put the exponent on the wrong side. So it's kind of hard to remember. One remembers when one looks at the proof, I think. I know that one trial statement is true and the other, when one changes the exponent, is definitely false. So the statement I made yesterday was false. All right, and of course, the ample, well, yes, so in fact, these two statements, this ample and very ample, if you don't make finiteness assumptions of finite type, they are really distinct. You can reduce them to the other. And you asked me to give an idea of the proof. You see, let me give the idea of the proof when F and G are supposed to be of finite type. So that's the notion of ampleness reduced to the notion of very ampleness. Huh? And so we have just to prove that the statement was very ample. And now, here is how it goes. The idea is the following: to say that L is very ample means that it can be induced by an immersion of X into some projective bundle over Y. So now assume for a moment, yes. All right. And in fact, assume for a moment that we can take as a projective bundle over Y, that we can take the standard projective space Pn over Y. Let's make it simpler. We will reduce to this case. All right. And in the same way, Y over Z, the sheaf M can be induced by an embedding of Y into a projective bundle over Z. Let's assume for simplest representations here, it's less important for the sake of the proof, that it can be induced through an embedding of Y into standard projective space of dimension M, let's say, over Z, like this. And now, what can we do? We can say the following: X is embedded in P and Y, but this is just, and call Y prime if you want, this projective, standard projective space over Z. So X is contained in P and Y, which is just the inverse image on Y of P and over Z. So this is just P and Z times over ZY. All right, and it's contained, well, it's contained, in fact, Pn over Y is induced by Pn over Y prime. So this is contained, and this being a closed immersion, you see, I get a closed immersion here. Let's write it like this: P and Y is contained by a closed immersion in P and Y prime, because P and Y, you see here is the situation, Y is contained in Y prime by a closed immersion, and P and Y is the inverse image of P and Y prime by this closed immersion. So it's here we have a closed immersion, this is P and Y prime, which is also P and Z times Y prime, because P and Y prime is the inverse image on Y prime of P and over Z, which is P and Z times P PMZ. So what we have found is that if X is projected by Y and Y crazy projected by Y and Y crazy projected by Z, then X can be embedded into a product of two projective spaces over Z, and hence it can be embedded by following this with a sigmomorphism into standard projective space PMN. This PMN perhaps not Pn plus 1, n plus 1, well, minus 1.
Separate.
Yes. Over Z. Alright, but here I have spoken about the morphisms, I have not spoken about the sheaves L and M, but let's see what is the sheaf on X which is induced by this immersion. Alright, we see that the canonical sheaf on here gives rise on this here to the tensor product of the canonical sheaves on these two factors. But these canonical sheaves on these two factors correspond respectively to the sheaf L on X and to the sheaf M on Y. And so when we look at what happens, we see that the canonical sheaf here induces on X the sheaf L tensor M. L tensor inverse image of M. Alright, therefore in this favorable case, when we can get L and M by N as induced from morphisms of X and Y in standard projective space over Y respectively over Z, we see that even L tensor with the inverse image of M already is very ample. It's induced by inversion of X into standard projective space over Z. But now what happens in the normal case? It is that we can only say, let's say a priori, of course, Z being crazy compact, and the notion of very ampleness with respect to Z being local over Z, you see we can assume Z to be affine if we want. So assume Z affine. Now, then every crazy coherent sheaf F on Z, you see, is a quotient of a free module over Z, and therefore P of F is contained in some Pm lower Z, and the fundamental sheaves, invertible sheaves on these inducing each other. Therefore, what I said about the embedding of Y into standard projective space over Z holds true here, doesn't make a difference. This comes from the fact that on Z, every crazy coherent sheaf is quotient of higher type, is quotient of a free one of higher type. But of course, the same wouldn't be true here. Now X can be embedded in PE, where E is a crazy coherent sheaf of higher type over Y. And it's not true that it's a quotient of a free one. But what will be true is that provided I tensor it with a high enough power of M, like this, call it E of N, it becomes now a quotient of a free one. So that's because M is ample on Y in the absolute sense. That's condition B. Therefore, we have a homomorphism of O Y at a certain high power into E of N. And therefore, P of E itself can be viewed as being contained in standard projective space of dimension N, where it calls N plus 1, of relative dimension capital N over Y. Therefore, we are reduced to the previous case, except that we have to be careful.
Is it P of E or P of N?
Yeah?
P of E or?
But, yes, I should also notice that the projective bundle associated to a crazy coherent sheaf E is canonically isomorphic to the crazy coherent, to the projective bundle associated to the tensor product of this with any invertible sheaf, how we'll call the invertible sheaf, I if you want. Because you see, if you have a quotient of E which is invertible, then tensoring by F you get the quotient of this which is invertible. And you have a map in the opposite direction by tensor by I minus 1. But in this isomorphism, here you have an invertible sheaf, which is a fundamental invertible sheaf relative to E, let's say. And here you have another one, which is relative to E tensor with I. And you see that this one is deduced from this one by just tensoring with I. So this is equal. It's a canonical isomorphic to O tensor with inverse image of I on P. That is, we have this isomorphism, but this isomorphism doesn't respect apparently the fundamental invertible sheaves that we had on these. Because after all, the modular problem wasn't quite the same. The invertible sheaves which you get as quotients of E and the ones that you want as quotient S here, they're not isomorphic. Those which correspond to each other, one is a tensor of the other by I. Alright. Therefore, that's it. The sheaf on X, which will be induced by this embedding, this will not be L, it will be L tensor with the inverse image of M tensor N. This was M tensor N, which was used in order to twist this. And now if I use the previous result, when I tensor this once again with the inverse image of M, I get something very ample. Now that's the same thing as tensoring L with M tensor N plus 1. And that makes it. So here, the stability under composition is true only when we make a quasi compactness assumption. That's not too bad. I have also to qualify the statement I made a week or so or two ago by saying that all classes of morphisms would consider that all properties would be local with respect to the basis. So that's not quite true. That's not true for the notion of a quasi projective or projective morphism. You see, these are the only two examples in the list of morphisms I gave. This notion of being quasi projective is not local on the basis. And on the other hand, as far as quasi-projectivity goes, it's stable under composition only if you assume, I guess for projectivity too, yeah. Yes, for both. It's stable under composition only if you assume that the schemes involved are quasi compact. So this is the only qualification I have to make for our announcement of what we will do later. All right. Now, I want now to look at the case of a scheme X, a coherent scheme on which the structure sheaf OX itself is ample. And these schemes are called quasi-affine schemes. Now I will introduce quasi-affine schemes by a number of equivalent conditions. So, maybe we give a definition in a slightly more dramatic way. I will say that X is quasi-affine. A scheme is quasi-affine. That's a definition now. If X is isomorphic to an open subscheme, open quasi-compact subscheme of an affine scheme. What's open in an affine scheme? It's of course separated as a subscheme of an affine scheme that is separated. So it means being quasi-compact, by assumption, it will be coherent. Alright, in a minute later we will relativize this notion, but let's now then give the proposition which will introduce a number of equivalent conditions. Equivalent conditions on a given X, assuming X already to be coherent, to be safe. I guess it could be more or less hidden in some of the assumptions. And so we will introduce also A, the ring of sections of the structure sheaf. And of course, there is a canonical way of mapping X into an affine, the universal way, namely mapping X into the spectrum of A. To map X into an affine is the same thing as to map the ring of this affine into gamma X or X. Here we have a universal way of doing so by taking the ring of the affine to be just gamma X or X. So let's look at this map. And now the following conditions I fill in, that X is quasi affine, namely that there exists an open immersion of X into an you can take this one, and this is equivalent with saying, let's say B, that that there exists an homomorphism X into an affine scheme, which is an homomorphism into homomorphism onto its image. For instance, an immersion need not be an open immersion. It need not even be an immersion. It's just an homomorphism of X onto its image. And of course, we could also state that U is such a homomorphism into. That would be still equivalent. Anyhow, I mean, if these conditions are really equivalent, then they will imply or even that U is an open immersion, which is much more. Alright, and now C, let's state it here. OX is ample. Now this, again, I recall what it means. In the particular case where the sheaf, invertible sheaf L is a structure sheaf, it means that the XFs for F and A make a basis, because now the tensor powers of OX are just isomorphic to OX, so the XFs are just the usual XFs. Form a basis of the topology, or it also means C second that the affine XFs, those XFs that are affine, form a basis. That also means that for every F quasi-coherent sheaf, which we may assume of finite type or not, that's to our choice finite type, F is generated by its sections. And we can even assume, we can state the same thing, assuming only F to be a sheaf, quasi-coherent sheaf of ideals, finite type. Same with F contained in OX. So that we need not suppose F of finite type is pretty clear here, because X being coherent, every quasi-coherent sheaf of finite type is a direct limit of its subsheaves that are, every quasi-coherent sheaf, is the direct limit of the subsheaves that are quasi-coherent of finite type. And so if those subsheaves are generated by their sections, then the big sheaf must be generated by the sections too. All right. So that makes a lot of equivalent conditions. I can add still one more. D. There exists an invertible sheaf L such that L and L to the minus 1 are ample. Of course, this implies that OX is ample because the tensor product of the two is OX, and it will be ample. And it also implies that every invertible sheaf on X is ample. So there you define. So there you have so for a proof I refer to EGA chapter 2 paragraph 4 somewhere, I guess. That's pretty elementary. You can do it as an exercise in a way. It's also the proposition about ample sheaf, all these things come out quite readily if you get started and have to get out. So this is the absolute case. And now, what about the relative case? As usual, we have now a morphism, fx to y, and we will say that f is quasi affine if there exists a covering of yi by all affine subsets such that for every I, x restricted to yi is quasi affine. That means also that the structure sheaf of x is ample with respect to y, and if y is affine itself, it just means that x is quasi affine in the absolute sense. In fact, if this condition is satisfied, then for every affine open subset of y, its inverse image will be quasi affine. Alright, so we can express this condition in various ways by just looking at the equivalent conditions in the absolute case. For instance, we can say that it means that f is coherent. So it means that Ox is ample relative to y, as we have seen. It means also that it is coherent on the one hand, quasi compact and quasi separated. In fact, it will be separated even. And for every f quasi-coherent sheaf on X, the canonical morphism which goes from the inverse image of the direct image of f to f is an epimorphism. Every quasi-coherent sheaf on X, that's amount to the same, is the inverse image as the quotient of the inverse image of a quasi-coherent sheaf on Y. So up to taking quotients, what you get on X comes from what you get on Y. All right. And now, what about the standard kind of conditions we like to be true for a class of morphisms? It's pretty clear that quasi-affine is stable under a base change, because, for instance, the notion of ampleness of a sheaf is stable under base change. And in the same way, we see that quasi-affineness is stable under composition here, because of this frequency on ample sheaves. That's one way of seeing it. There's many other ways. Of course, here we don't have to assume that Z is quasi-compact, because the condition of being affine, quasi-affine over Z is now local over Z, which wasn't the case for the What about diagonals? Well, I mean, emergents are quasi-affine provided they are quasi-compact. And here we have it. So quasi-compact emergents are quasi-affine, and in fact they are finite type. And of course, affine morphisms are quasi affine, and therefore affine morphisms of finite type are quasi affine of finite type. Now, therefore, as a consequence, we see that when is a diagonal morphism quasi affine, it is quasi affine if and only if it is quasi compact, because it's an inversion. So it just means that G is quasi separated. Alright, and as a consequence, we see that if a compositon GF is quasi affine, and if moreover we make a very small restriction on G that G is quasi separated, so it's practically always true, then F is quasi affine. So it means essentially that a scheme that is quasi affine over anything, except that the anything should be quasi separated, which is pretty weak. Now all this was, although I didn't practically give any proofs, all this is pretty easy going. Let me try to indicate a subtler, deeper result, which is kind of H forever. So let F be a morphism from X into Y, F being of finite type, separated. The conclusion will be that F will be quasi affine. So you certainly will have to assume F is separated and of finite type. Not of finite type, but I will assume it of finite type. And with finite fibers. So the structure of the fibers is discrete. Then this implies let's say finite fibers. This implies that F is quasi affine. In fact, it implies a lot more. It implies that we can factor F, at least if Y is coherent. So if we make some slight exception on Y, which is always true if Y is affine, for instance. And the question of F being quasi affine, in fact, is built on Y. So we have a stronger result. If we make these assumptions here, and if moreover Y is coherent, then we can factor F through a scheme X prime that is finite over Y, and here an open immersion. Therefore, X appears as an open subscheme, quasi compact, with an open immersion which is quasi compact, over of a scheme that is finite over Y. So there exists factorization, F equals F prime I, with F prime finite, and I an open immersion. This open immersion will be necessarily quasi compact, of course, because we assume F to be a finite over Y is quasi compact. So for this reason, the morphisms that are finite type and that have finite fibers, without necessarily assuming that the morphism is separated yet, we call them quasi-finite. So if we add the separation axiom on it, these are just those that appear as open subsets with the new structure of schemes that are finite over Y. So this strong statement is the strongest statement. This is Zariski's main theorem. In fact, it's a restatement in a more up-to-date way of Zariski's main theorem. So it's something pretty subtle. It's proved this here and this here, and at least these two. These I'm not too sure about this. But these two, they are proved by global methods using finiteness theorems about higher-like images of coherent sheaves by proper morphisms and such things. They can be squeezed. I don't think you can squeeze them out just by working with the definitions and doing some sort of nonsense. I mean, you have to use some fairly big machinery which are kind of far-fetched when you just look at statements. You wouldn't think of necessarily of using these tools. So it's not the kind of thing we have time to go into this box. But of course, the statement is kind of, it makes geometric sense. Kind of simple. But there are two statements that make geometric sense. That are whose proof is out of the scope, certainly of this introduction to algebraic geometry. So there's still one last notion I'd like to introduce. It's a rather different type from the ones we have seen so far, which is a variant of the notion of monomorphism of schemes. Of course, in this diagram there are a lot of notions which we have seen, like affine presentation and local affine presentation and quasi compact and the like, that are not in here. Here the accent is not so much on finiteness properties, but on somewhat subtler properties. So, let f x goes to y be a morphism of schemes. I will again introduce equivalent conditions. Now, I mean, they will be so trivial that we will prove them less immediately. First, f is injective and remains so after any base change, injective on this underlying sets. So we call this is universally injective. So that means that for every base change y prime goes to y, corresponding morphism f prime from x prime to y prime reduced from f by base change is injective. And then B, statement about the fibers. You see, what does it mean that it's injective? That means that for every y prime in y prime, the fiber x prime lower y prime of x prime over y prime is at most one point. But this fiber is reduced from the fiber xy of x over y by making the base change from kappa y to kappa y prime. So the condition just means that these fibers are either empty or they have at most one point and continue to have at most one point after any base change. Now I want to express this in a somewhat different way, more explicit way. For every y in capital Y, there exists at most one point over it, and moreover, the resolution extension kappa x over kappa y is radical. Now the equivalence of A and B just means that if, of course, the nilpotent elements that you might have in the local ring of this one point in the fiber, they don't change anything for the sensitive question whether how many fibers, how many points this fiber and the ones reduced to it by base change may have. So the question is, here the field K, here field extension K prime, and you wonder when is it true that spec K prime goes to spec K as universally injective, when it is true that for every field extension, call it another capital K here, this field extension, that for every field extension K prime, the spectrum of capital K tensor with K prime has at most one element. Or what amounts to the same if you make still a further field extension, that there exists at most one homomorphism of K tensor K prime into K prime. Because every point of a scheme over K prime becomes rational after we make it with a ground field after we make a field extension. We can always take the new field of this point. So this question is now under which conditions is it so? But the homomorphisms of this into K prime, they correspond to the K homomorphism of capital K into K prime. So we want that for every field extension K prime of K, there should exist at least, at most, one K homomorphism of this field into this one. But this means that this extension is radical. They're purely incidental extension. So I know. So A and B are certainly equivalent. And now, just a restatement of this. For every field capital K, the map which goes from x of k to y of k, k parallel value points of x to k value point of y is injected. It's clear that's the same thing. So the morphisms we are considering, we will call them radical morphisms. They are the next best to being monomorphism of schemes. Monomorphism would mean that for every scheme S, for every scheme T, let's say x of t goes to y of t, is injective. And the hom of t, x goes to hom of t, y is injective. Now we want this to be true not for points of x and y, this could in any scheme, so to say, or this could in any thing. We want to be true only for so-called geometric points, for points with in fields. And now there's another nice equivalent formulation. It is a condition on the diagonal morphism, delta f, which goes from x to x times over y x. This could be surjective. Just as something is a monomorphism if and only if the diagonal morphism is an isomorphism. Here, so being an isomorphism should only demand that it should be surjective. Now, let's see that C and D are equivalent. So, that it's surjective means that every point of this, with values in any field, comes from a point of x with values in perhaps a field extension. Maybe, I don't know if this is clear. Let's say if you have a morphism of schemes T goes to S, and if S is an element of capital S, what does it mean that S is an image? So let's look at, that means that the fiber Ts of T over S is not empty. So S, element of Ft, or call it T rather here, just means that Ts is not empty. And if you express this by picking a point T and Ts, then we look at the field extension kappa S over kappa T, and we see that the canonical point of S with values in kappa S, if you view it as being a point with values in kappa T, using this homomorphism, can be lifted into a point of T with values in kappa T. And the converse is of course true. If the point, analytical point of S is quotient, then S can be lifted to a point of T, as well as an extension field, then S belongs to the image. So, and therefore the morphism is surjective if and only if every geometric point of S with quotient in a field can be lifted after a field extension to the geometric point of T. And this is just the usual kind of translation. All right. Now, what is a geometric point of X times X over Y? That's just a pair of points of X with quotient K that map into the same point of YK. That is an element of the finite product of this set by itself over YK. And that we have here something surjective just means that provided you make a field extension, that you get something surjective from xk into this finite product. But this means that xk goes to yk is an holomorphism. So all these equivalences are pretty trivial. So we have the notion of a radical morphism. Now it's clear that a radical morphism is something stable under base change because we have defined it this way as universal injective. And it's pretty clear also that it's stable under composition. This comes from the fact that the compositum of two injective maps is injective. So the compositum of two universally injective maps is universally injective. Of course, the monomorphism is universally injective, and therefore diagonal morphisms are universally injective. And therefore, TF is universally injective, F is also universally injective. As a general theory, or it's also trivial directly. Now, let's give an example of two, but perhaps before giving an example, let's still make a little comment. Assume that we have a morphism F from X to Y, which is integral, radical, that means universal injective, and surjective. Then F is a universal homeomorphism. Namely, it is a homeomorphism and it remains so after any base change. In fact, being radical, it's universally injective. Surjective, that's something that is already universal, so it's universally bijective. On the other hand, being integral, it's universally closed. Now, a bijective closed immersion is a closed bijective closed map is a homeomorphism. It's a universal homeomorphism. All right. In fact, one can show that the converse holds true, that the universal homeomorphisms are those that are integral, radical, and surjective. This comes from the fact that integral morphisms are those that are affine and universally closed. Because the first thing one shows rather easily is that F is a universal homeomorphism. If the homeomorphism is enough, I think. If F is a homeomorphism, then F is affine. It's a little lemma. It's easily squeezed out. So if you are willing to admit this, then you get easily the converse here. Now, universal homeomorphisms, one meets them rather often. So let's give two rather different examples. Let K, for instance, be a field, and let K prime be a radical extension. We can take, for instance, the largest radical extension of K, which is defined up to unique isomorphism, which is the so-called perfect closure of K. K prime might be the perfect closure of K. Of course, in characteristic zero, a radical extension is just K. Then our example is not too interesting. Now, the spectrum of K prime over spectrum of K is, of course, integral radical and surjective. Therefore, it's a universal homeomorphism, which just means that for every x that we have over k, when we look at the base change from k to k prime, we get a scheme x k prime over k prime. And this morphism here is a homeomorphism. Now this we have already noticed in order to say that if we are only concerned with topological properties of a scheme over a field, that nothing changes if you replace the ground field by its perfect closure, let's say. For instance, if you are working over a simply closed field, nothing changes if you replace this field by its algebraic closure. Now let's give another example. Let's look at a rational curve or any curve with a cusp like singularity like this. So I could write an equation if you wanted. X squared plus y squared equals 0. That's the simplest one, I guess. And let's look at the normalization, you see, of this curve, which is just a curve without singularities that is mapped onto this curve by a in fact, bijective morphism. It's proper, and the fibers at all points are just the residue fields, the spectrum of residue fields, except at this point, where there's one point above, the residue field extension is trivial, and then there are some important elements around. So this point, in fact, in this case, the inverse image of this point is a point here, but which appears as a double point. All right? So it's certainly, therefore, integral, radical, and surjective. It's universal homeomorphism. So it remains a homeomorphism after any base change. So that's pretty good. Now let me give an example of a homeomorphism that is not a universal homeomorphism. And take a curve with an ordinary double point. And let's look at the normalization which we obtain by separating the branches. So over this double point, there are now 2 points in here. Here's one and there's the other. And so this was y, let's say. Here we have y tilde, the normalization. And now let x be obtained by removing from tilde one of these 2 points. Cut it out. So x is equal to y tilde minus small y1, let's say. The other point is y2 minus small y2. The other is y1. Then, of course, from the point of view of the risky topologies, I mean, x is homomorphic to y, in fact. The closed subsets here are just either the whole sets or it's bijective, and the closed subsets are either the whole curve or finite subsets, not including the generic point. Alright, so it's a homeomorphism. But it's not a universal homeomorphism, because having removed this point, this morphism is no longer finite, and it's quite easy to see, to ascertain it's not a universal homeomorphism by taking as a base change the normalization of y, for instance, and seeing the inverse image. You will see that after you make this base change, then the new projection is no longer homeomorphism. In fact, there will be an isolated, it's maybe kind of useful to look at what happens. So when we look at base change y tilde goes to y here, if you look at the product of the inverse image of y tilde by the space change y tilde, so we look at y tilde times y tilde. How does this look like? It's just, there's on one side there sits the diagonal in it. Of course, the fibers for every point, yes, this different from this one. I mean, over this and over the complement of this point, y tilde goes to y is an isomorphism. Therefore, this fiber product, when we look at it, it's a scheme over y, and the complement of this point, it's just y itself. And so we have to look separately what happens at this point y. Now the type of this point in this factor and in this factor, which are the same, is just 2 points. Therefore, over this here, there should lie 4 points. And now, what happens now is that y tilde times y over y tilde is just isomorphic to, on the one hand, y tilde, which appears as a diagonal. So that's just, so the projection of the diagonal to y is just an isomorphism everywhere, except that over this point, there are 2 points lying on it, and there are still 2 points lacking, and these appear as isolated points, plus at point z1, plus at point z2, that are isolated. And what has happened when we replace y tilde by x, removing one of these points, that means that now our morphism will be bijective and a homeomorphism, and when we look at the fiber product, then x times over yx will be isomorphic to x, which is a diagonal, plus one of these isolated points, either z1 or z2. You see x, that's it. And of course, if you look at the projection of this into y tilde, it's not a homomorphism, because x is reduced from y tilde by just removing one point, and one has added now this point that one had removed as an isolated point. So maybe I have not been too careful about how I presented this example. I think it's worthwhile to work it out. And there are really no difficulties. You just use the fact that y tilde is irreducible, that the inverse image of this point is 2 distinct points, and that as a complement of this point, if you have an isomorphism, that's all you have to know about the situation. In terms of this, you will reconstruct the structure of the fiber product as this topologically. So, a morphism being a homeomorphism doesn't mean of schemes, doesn't mean really too much. You see it. Need not be even a finite morphism. So it's really the universal homeomorphisms that count. Alright, so this completes our list of nice morphisms. We have the universal homeomorphisms. Now we have, in order to use it in connection with flat descent, we have still to say a few words about open morphisms. We have defined closed and universally closed morphisms. The universally closed morphisms are also stable under composition and base change. Now something about open morphisms. So if we have a model of schemes, we say of course that F is open if the map of the underlying topological spaces is open. And we'll say that F is universally open, but it's open and if it remains so by any base change. Hey, by the way, I guess it's about time now to stop. So I wonder if we shouldn't go on with some more algebraic geometry for the next lecture, because yes. So then we stop now and we go on with this so that we can really start with a little bit of some preliminaries of flat descent today. Yeah, maybe I should, before
a few of the people in this course are actually enrolled. That means most of the other people probably are more interested in open questions.
Yeah. So at this moment, I can't think of any open question on the level on which we've been working. But maybe you're thinking hard. And so we started speaking about an open morphism and universally open morphisms. Of course, open morphisms, that's something that is stable under composition. Of course, not necessarily under base change. I gave an example, by the way, with our point with double point. I mean, it was a bijective morphism, which was universally bijective, in fact. And it was a homeomorphism, that means open in this case, and it wasn't a universal homeomorphism, so it wasn't universally open. So, of course, once we speak of universally open morphisms, by definition, this is stable under base change. So it's both stable under base change and under composition, as we expect from a nicely open morphism. And I want to say a little more about it. So first, a necessary condition for morphism to be open. If F is open, this implies that for every x in capital X, the induced morphism which goes from the localization of capital X at X into the localization of Y at the point small y equals f of X should be surjective. Now this property, which I have just stated here, we express by saying that F is generalizing. Because this property means, if you recall, that the localization of Y at Y consists of all points that are generalizations of Y. It's a subset of Y, consisting of all generalizations of Y. Then we see that the statement here on the right just means the following: whenever we have a point Y and the point X, in capital Y and the point X above it, then every generalization Y prime of Y can be lifted into a generalization X prime of X. Now if you identify points of a scheme with irreducible closed subsets, we can say also the following thing: that every irreducible closed subset of Y and every irreducible closed subset of X which dominates it, then to give them names to these things, for the Y prime a closed irreducible subset of Y and X prime a closed irreducible subset of X which dominates Y prime, so that X prime is mapped to Y prime and its image is dense. Whenever we give, moreover, a larger irreducible closed subset of Y prime than Y prime in Y, Y second contains Y prime, then we can find an irreducible closed subset X second of X containing X prime and which dominates Y second. So that's the image of it is dense. It's the lifting of closed irreducible subvarieties. So that's the property. But in fact, it's more handy, and in a way, after a while, it's more intuitive to express it this way. That is, if you have surjective morphisms for the localizations. I will call it localization as a spectrum of the local ring, like that. It's a point X, and this is the spectrum of the local ring of Y at Y. So an open morphism is generalizing. Let's first see why this is true. All right, let's recall that we can of course assume X and Y are affine if you want, because the question is purely local both on X and Y. And recall that the localization of X at the point X as a subspace of X is just intersection of all open subsets U that contain X, and of course I can restrict to the affine open subsets, because they can be based on topology. Now, if the morphism is open, then each one of these open subsets is an open subset of Y containing, of course, small y, and therefore it contains the localization. And so our assertion comes from the following very general fact. It is that taking intersections of let's say retrocompact open subset of X commutes with taking images. What I want to say is that the image of this intersection is the intersection of the images. And as these images contain each of them the localization, we are through. So we have now to see this general fact. How will we express it? Because it's really pretty similar thing. Well, why not? So, I want to give a general statement. How to give it? Let's say it in the following way. We have an X over an Y, like here, and then we have schemes Xi over X that, let's say, are affine over X, like the U's here and X. And they form an inverse system, and I look at the inverse limit of these Xi's. All right, let's call this C. And this morphism I call F. The transition of the morphism from Xi to X I call Gi, and the morphism from Z to X I call Z, G, let's say. And I claim that F of G of Z, the image of G by Fg, or what amounts to the same, the image by F of the image of Z and X, is equal to the intersection of the F Gi's of Z. Of course, what is clear is that F of Gz is contained in each of the FGIZs, and therefore it's contained in the intersection. So what is less trivial is this one, but you will see that it comes out quite easily. And so we have to prove that if you have a point in here, then it belongs to here. So what does it mean that we have a point in here? It means that its fiber in each of the Xi's is non-empty. And we have to prove that its fiber in Z is non-empty. Now, of course, Zy is the inverse limit of the fibers Xiy. That comes from the fact that base change commutes with taking inverse limits. Where all the Xi That's it. Maybe I could assume that F is quasi compact. Right. So, but here, F being quasi compact, the fiber here is quasi compact. And for this reason, if you want to prove that Xiy is empty, for I large enough, when the Zy is empty, we are reduced to the case when Xy is affine. It's said, because if it's true over open sets that cover Xy, that will be true by taking an I which is larger than each of the integers each of the indices which correspond to there's finite number of open sets we have taken here. We are all right. So we are reduced to the case when everything is affine, and so therefore we have the situation is the following: we have a Dirac limit of rings AI. We take its Dirac image, its Dirac limit A, and we have to prove that if A is equal to 0, then there exists an I such that AI is equal to 0, because schemes being empty means that rings are 0. But what does it mean that A is equal to 0? That means that 1 is equal to 0 in A, but then 1 must be equal to 0 already to one of the AIs. So this is a procedural statement about the compatibilities of intersections with direct images. So it implies here our statement that if F is open, then F is generalizing, and as a consequence, if F is universally open, then F is universally generalizing. It's clear that the notion of a generalizing morphism, by the way, is stable under composition. It expresses the surjectivity of localizations, and surjectivity is something stable under composition. And therefore, universally generalizing is both under composition and base change. It's again a nice notion of morphisms, which is weaker than universally open. Now, it's easy to give examples of morphisms that are generalizing or universally generalizing and that are not open. For instance, take an integral scheme X, for instance, the spectrum of an integral domain, or any scheme as for that matter, it doesn't have to be integral. And take eta in X a maximal point. So if X was integral, it would just mean that we take the generic point. Otherwise, I might settle maximum points. And look at the morphism which goes from eta to X, just this one point to X, where I view eta as being induced with the field kappa eta. Now this is generalizing for a very trivial reason, because in X there is no generalization of eta except eta itself. I mean, the condition of being generalizing here kind of isn't satisfied. But of course this morphism is not open. Eta is not an open point in X, at least not in general. It would be so if X is a stroke, is a spectrum of a discrete validation ring. But take for X almost anything else, or the spectrum of a field that also we could take for X, for instance, the affine line over a field like this. So although the morphism eta goes to X is essentially of higher type here. But however, if F is of locally finite presentation, so that's another statement, then F is open if and only if it is generalizing. So then the converse is true. And as the notion of being local finite presentation is stable under base change, we see that F is universally open if and only if F is universally generalizing. Now, I'm not sure I'm going to give a complete proof of this. I will just reduce to something else, or something else has something to do with a general suite of constructible sets in a scheme. What we know when F is generalizing here is that the image of an open set must be stable under generalization, because if a subset of X with every point x contains the whole of the localization of x, and x contains all the generalizations, then the image of the set has the same property, because these morphisms here are surjective. And an open set in X is precisely stable under generalization, and therefore, if F is generalizing, its image must be stable under generalization. And therefore, what would we be looking for in order to prove that under certain conditions we have a converse is a criteria which will assure that subsets of Y, that certain subsets of Y, provided they are stable under generalization, are already open. And now it turns out that the type of subsets in Y that you obtain by taking images of schemes of finite presentation or local finite presentation over Y have this property. In fact, this is tied up with the notion of constructible subsets of Y. So one can define a certain subset of Y which are, roughly speaking, at least that's correlated Y is Euclidean, which are finite unions of locally closed subsets, in the case when Y is not necessarily, one has to be a little bit more careful about the definition. And it turns out that, assume everything locally, everything Gaussian for simplifying, that if you have a morphism of higher type of Gaussian schemes, then the image is a constructible subset. And therefore, if you are reducing here to X of higher type over Y, and you know the problem is local, we see that the image of X and Y is constructible. Or the image of any open subset of X and Y is constructible. On the other hand, it turns out that for a constructible subset of the scheme, it is open if and only if it is stable under generalization. In fact, if I have a point of a constructible subset, it's a neighborhood of this point, if and only if it contains the spectrum of the localization at this point, if it contains all the generalizations of this point. So that's the story. I'm not sure you will have time to speak with a little more systematically about constructible sets. But I mean, it's something quite elementary, quite nice, quite pretty. You could look it up if you have no time to speak about it more. In EGA New Edition Chapter 1, there's a paragraph. I don't remember which, but anyhow you find it in the index. About constructible subsets. Now, if on the other hand, the reduction to the case when Y is Gaussian, let's say, is immediate, because the problem being local on X, we can assume anyhow X and Y both affine. But then, according to the John setup, this situation comes from a certain situation by base change, because X would be a finite presentation over Y. And so all you have to show to make this reduction is the following. Let's assume that we have made that X over Y comes by base change from a Gaussian situation. So if you have proved the theorem in the Gaussian case, it would mean that after every base change of finite type over Y naught, so that we don't lose the Gaussian property, that then the corresponding morphism is open. But then it's a very easy question of passage to limit, that if a morphism is open, remains so after any base change of finite type, then it remains so after any base change whatever. That's again, I mean, the standard passage to limit, which is quite straightforward now. So the reduction in the term to the Gaussian case is very straightforward. In the Gaussian case, one can use Gaussian techniques if you want, but one can also develop the notion of constructible subsets, with being somewhat careful in the non-Gaussian case for quite arbitrary schemes. And then, if one does this, then one can just say that the image of X and Y is so-called constructible and being stable under generalization. It must be open. So maybe it's worthwhile noting that something a little more general than this here then. If f is a finite presentation, then f is open at x, by which I mean that the image of any neighborhood of x is a neighborhood of f of x equals y, if and only if the induced morphism from the localization of x at x to the localization of y at y is surjective. Or as you would say, if and only if f is generalizing at the point x. So it's essentially the same argument. The argument I gave there, in fact, shows that if f is open at the point x, then it's generalizing at the point x. And for the converse, we have to just to use the criterion that a point is interior to a constructible set if and only if the constructible set contains a localization at this particular point. And we have already used this, I think, in the other part of the course on pretended given algebraic groups, in order to prove that any morphism of a scheme into a spectrum of a field is universally open too. Because we know it's to be true when the scheme is locally finite type over the field by this theorem, and then by passage to limit, which is pretty standard. We prove it in general. Now we'll start now on flatness. In fact, if I stated this theorem, it was in order to apply it to flat morphisms later, because flat morphisms turn out to be generalized. So let's recall the general notions of flatness. So let's first look at the ring A. And you recall, I guess, that the module M over A is said to be flat if the functor cancelling by M, n goes to n tensor M, on the cut of A modules to the cut of A modules is exact, or not only right exact. And M is said to be faithfully flat if it is flat, then this function is exact, and if moreover this function is faithful, which also means that it's conservative, or it also means that because it's exact between additive categories, that m tensor n equals 0 implies that n equals 0. If the transform of some object by this functor is 0, then it should be already 0. And so exactness plus faithfulness imply, for instance, that the morphism is equivalent to saying that if you have a morphism n goes to n prime, which gives an morphism for m tensor n to m tensor n prime, it's identical in m tensor plus u, call this what we know t of u, if t is this functor here. So t of u is homomorphic from tn to tn prime, that u is injective if and only if t of u is injective, and the same with surjective, the same with bijective. either of these three conditions is equivalent to saying that M is faithfully flat, assuming already M to be flat. And the same, you can also express it by exactness of a sequence. If you have n prime, n second, and therefore we get tensoring by M, Tn prime, Tn second. So it will then, if M is flat, exactness here will imply exactness there. And since to say that M is even faithfully flat means that the converse holds also true. So faithful flatness means that when something becomes true after tensoring, it was true before, essentially. And that has been not used very much, I think, for modules. It has been used mostly for algebra. So if B is an algebra over A, to say that it's flat just means that the functor M goes, well, let's call it N again. N goes to N lower B, which is a functor of base change from A to B. It's an exact functor. The tensoring with B has now a nice geometric meaning of base change. And to say that B is faithfully flat over A means that this functor of base change is both exact and faithful. And so it can be expressed by saying a morphism of modulus on A is a monomorphism if and only if it becomes a monomorphism over B, or is an epimorphism if it becomes an epimorphism over B, or the same with bimorphism, or the same with exactness of a sequence, or the same with a modular over A is 0 if and only if it becomes 0 over B. Now I want to express strict faithfully flatness of a module, let's say first, in an equivalent way. So I say that M is faithfully flat if and only if it is first of all flat, of course. And moreover, I have to express the faithfulness for every maximal ideal M in A, M tensored with kappa M, which is just M because the ideal is maximal, which is just M divided by MM, is different from 0. So let's prove this. Of course, if M is faithfully flat, then for every ideal J in A, such that J is different from A, namely such that A over J is different from 0, it must follow that M tensored with A over J is different from 0, which means that M divided by Jm, because M over tensored with AJ is M divided by Jm is different from 0. So certainly the condition here is necessary, but we have, and for theory if we take maximal ideals only. So what we have to prove is that this condition, which looks kind of weak, already implies faithfulness, faithful flatness. All right, so let's N be any module different from 0, and let's prove that M tensor N is different from 0, assuming this. Now, if N is different from 0, N contains a submodule N prime, which is monogeneous, which is generated by one element, and which is different from 0. Just take an element X and N, which is different from 0, and the module generates. And then M tensor N causes T of N if you want. I think that the argument we are going to make doesn't depend on the fact that the functor we are considering is a tensor product. We are finding the exact functor and we'll never get it. All right, so Tn being different from 0, and Tn containing Tn prime, because N prime is contained in N. I'm sorry, that S as n prime is contained in n, Tn prime is contained in Tn, in order to prove that Tn is different from 0, which you don't know yet, you just have to prove that Tn prime is different from 0. Now, in the same way, n prime being monogeneous, it's a quotient, it's isomorphic to the quotient of A by some ideal, which is different from the unit ideal, and by Coyle-7, this ideal is contained in maximal ideal. In other words, a monogeneous module that is not 0 has a quotient which is isomorphic to A over M for some prime ideal, for some maximal ideal M. So let's look at such a quotient. For this quotient K, K would be the residual field of A at M. Right? And we have here a surjection, and therefore we have a surjection from Tn prime to Tk. And in order to prove that Tn prime is different from 0, we have only to prove that T of K is different from 0. And that's precisely what we assumed here. So it's a very little argument that you have an exact functor from modules over A into some abelian category for this functor to be phase split necessary and sufficient. Then it transforms the residual fields at maximal ideals into objects that are not 0.
You assume it to be additive to the...
Didn't I say exact? That's stronger than additive. I mean, additive just means that it commutes with sums, with finite sums, or equivalently with finite products. Exact means that it commutes with all finite inverse limits and all finite direct limits.
Now,
Anything wrong?
no.
Anyhow, I mean, this functor is certainly exact. It's certainly additive. That's M.
I thought that in the last argument you need to use additiveness and because the non-zero image.
I mean, an exact functor is additive. And anyhow, and if you don't want to know this,
Well,
the tensoring with M is additive, certainly. Yes, so this, I think, is all right. Now, let's take the particular case. Of course, it's also equivalent to flatness plus the fact that M tensor with kappa P is different from 0 for every P, for every prime ideal. That's quite clear. Because kappa P is not 0. All right. Now let's see what happens in the case when we take an algebra. Let B an algebra over A. Then B is faithfully flat, I claim. If and only if B is flat and over A, and the spectrum of B mapped to the spectrum of A is surjective. Namely, if you denote by x goes to y the map on the spectra, for the time being I don't care about the structure sheet, I just look at the sensor-deck map. It means that the fibers of this map are not empty. Every prime ideal of A is induced by a prime ideal of x, of B. But also, it's equivalent to saying that the fibers at maximal primes are non-empty for every M in A, M maximal, M is in the image of spec B goes spec A. All right. So if P is a prime, we just noticed that the fact that taking m to equal to b, that m tensor kappa p is different from 0, that means that b tensor kappa p, taking b to be equal to m, is different from 0. Well, that means also that the spectrum is non-empty. But the spectrum is just the phi of x at the point p of y. So in fact, the condition here is just this condition, and is just this condition. The condition with respect to maximal ideals is this condition here. So faithful flatness for algebras just means flatness plus the fact that the map on the spectra is surjective. It means, so to say, if the extreme opposite of faithful flatness would be that B is 0. I mean, it has no merit to be flat, but it's certainly not faithfully flat. So we want to think of faithful flat, it means that B kind of covers A, you see, and it's kind of big. And in geometric terms, it just means that X goes onto Y, that every point of Y is covered, and so on. So it has a very simple geometric meaning. Now let's give another corollary. Assume that our homomorphism A goes to B is a local homomorphism of local rings. That means that the unique maximal idea of A is mapped into the unique maximal idea of B. Then I say that B is flat over A if and only if B is faithfully flat. So in this case, flatness implies faithful flatness. Well, you can, for instance, say the following. Flatness, in order to satisfy faithful flatness, we have just to check that B divided by MB, where M is maximal ideal in A, is different from 0. But MB is contained in the maximal ideal of B, therefore this here is larger than B divided by its maximal ideal. Therefore it's different from 0. And therefore we see that if the spectrum of B is mapped surjectively onto the spectrum of A, if you have flat local homomorphism of local rings, then the induced map on the spectra is surjective. And now let's again notice that flatness for algebras is stable under localization if we have a set of elements T and B which we want to make invertible, so that now B is transformed into the ring which may call Bt minus 1. If T is just one element, it would be B lower T. And if T is a complement of a prime, it would be the localization of B at this prime. Alright, and if so that A is through B is mapped into Bt minus 1. And if S is a set of elements in A which become invertible in Bt minus 1, so that we get a morphism from AS minus 1 into Bt minus 1, I claim that if B is flat over A, then Bt minus 1 is flat over AS minus 1. That's completely trivial checking. Now, admitting this point, we see that if B is flat over A, then every local ring of B is flat over the corresponding local ring of A. And therefore, we see that if we have a morphism X goes to Y, which corresponds to a flat ring extension, now no longer assuming A and B to be local, then for every point X in capital X and every point Y in capital Y, the morphism for the spectra, I mean, the homomorphism for the local rings in the opposite direction is a local homomorphism which is flat by what we have just said, and therefore the morphism in the opposite direction, therefore it's faithfully flat by this corollary, and therefore the morphism for the spectra in the opposite direction is surjective. Therefore we see that a flat morphism is generalizing. Except that I was a little rushed because what means a flat morphism? I haven't defined it yet, really. So all I have proved here is that we have an algebra B over A that is flat over A, then the morphism was a spectra, is a generalizing morphism. But now let's globalize these notions. In terms of sheaves, so if X is a topological space, let's say, endowed with a sheaf of rings OX, then if M is a sheaf of modules on X over the sheaf of rings OX, the notion of flatness is pretty clear. It's defined as in the case when X is reduced to a point, in the case of a ring and modules over the ring, by just saying that the function that N goes to M tensor N could be exact. And it's trivial checking that this just means that the fibers of M, viewed as being modules over the fibers of the sheaf, of the structure sheaf, are flat modules. So the notion of flatness for sheaves is reduced by passing to the fibers as by the usual process to the corresponding notion for usual modules or usual rings. All right. Now, what about the case when X is a scheme? And if the module M is crazy coherent? Of course, the notion for a module M to be flat over OX is purely local on X, and therefore, to express it, we can assume that X is affine. Right. Because if X is covered by open sets, so that's restriction of M to each of these flats, this means that M is flat. So we are reduced to get X affine X, the spectrum of the ring A, and then M will be of the type M tilde, where M is an A module, and then what does it mean that M is flat over A? Well, we can express it by saying that the stalks of M are flat modules over A, or else that the various MPs, viewed as being modules over AP, where P goes through the primes of A, are flat. Now, for this, it's pretty clear that's in that sense sufficient that M itself would be flat over A. Therefore, the flatness of the sheaf of modules reduces to the flatness of the module. So, I mean, the usual affine dictionary here works perfectly smoothly. Of course, we have already said that if M is flat over A, then MP must be flat over AP. The localization is smooth. Well, I said it in the case of algebra, so I wasn't right. But it's, you see, it's just a base change, you see. And flatness will be stable under base change of things. All right. And the converse is pretty clear too, because in order to check that M tensor N goes to M tensor N prime is injective, whenever N goes to N prime is, we have only to check that when we localize at P, become injective for every P. And this just means this comes from the fact that MPs are flat over the APs. And this is pretty clear. So this, therefore, there is ways of viewing flatness. I mean, they're all checked. So let's look what happens if we have two different spaces, X and Y. Ringed spaces with a sheaf of rings OX here and OY down. And if you have a sheaf of modulus M on OX, what does it mean that M is flat with respect to Y or F flat? You have to look at flatness also for modulus on X with respect to Y. And for us, the most interesting case is the one when M is equal to OX itself. So what it means that OX is flat over OY. Well, to say that we have a morphism of ring spaces means also that we have a morphism of sheaf of rings which goes from the inverse image of the sheaf of rings OY, which would be a sheaf of rings on X, into OX. And therefore M being a sheaf of modulus over OX can be viewed as having a restricted structure of sheaf of modulus over OY. F minus 1 OY. And we will say that M is flat with respect to Y if it's flat with respect to the structure of modulo over this. Now this means also that for every point X in the capital X, the store M lower X viewed as being a module not over OX capital X, which would be the store of OX, but rather as being a module over the store of F minus 1 OY at the point X, and this module is flat. But this stock here is just the store of the structure sheaf of Y at the point small y, by definition of the inverse measure of sheaves, more or less. Stocks at corresponding points are the same. And therefore, the modulo structure which I put on my MX is the one which is deduced from the modulo structure over O capital X small x by taking its restriction of scalars to O y small y, thanks to the homomorphism that we have. Now assume that X and Y are schemes, again, and that M is quasi-coherent. And let's look what that means, that M is flat with respect to Y. Well, again, it's a local condition on X and Y, so we can assume that X and Y are affine, corresponding to rings A and B, B being an algebra over A, and M corresponds to a B module M. And then we see just as before that M is flat with respect to Y if and only if the B module M, when we restrict the scalars to A, becomes a flat A module. And now, although a number of things about flat descent into vertical properties of flat morphisms would hold true if we work with flat modules on X, I will henceforth restrict to the case in M equals OX. So if OX is flat with respect to Y, we will just say that the morphism F is flat. So a flat morphism is one for which OX is flat with respect to the basis OY. So this is a local notion on both X and Y. And when X and Y are both affine, it just means that the algebra B over A that describes X is a flat algebra over A. And now we know what a flat morphism is, and we can say that a flat morphism is generalizing, because this is both being flat and being generalizing is a local property, so we are reduced to the affine case, which we have dealt with. We can also say that F is flat if and only if, for every point X in capital X and the corresponding point Y in capital Y, the local ring of X at small x is a flat algebra over the local ring of Y at the point small y. And therefore, the spectrum of this maps surjectively to the spectrum of this, because flat means here faithfully flat, because we have a local number of local rings. Now, let's give a variant of the property that, in fact, that's equivalent to the property that F is generalizing. I guess. But let's be short in that state. Of course, a flat morphism is generalizing, and as being flat is stable under base change, quite evidently, because this is true when we take ordinary rings. Then we see that a flat morphism is universally generalized. Yeah, let's write it down here. Flat morphisms. Stable under composition on the one hand, contain of course isomorphisms also, and stable under base change. Why is this? Everything reduces to the affine case. And then about stable under composition, this comes from the fact that if B is flat over A and C flat over B, C is flat over A, because the functor of base change from modulus over A to modulus over B being exact, and so on, from B modulus to C modulus being flat, being exact to the composition must be exact. And what about, all right, and now if M, yeah, and on the other hand, if B is flat over A, and if we make any base change, then B prime is flat over A prime. Is this clear? Let's see. Okay, how does this work? More generally, this has nothing to do really with algebras. It's true. If a module M over A is flat over A, then I can that M prime over N prime is flat. So let's see. Let's take a variable module N prime over A prime, and let's look at this tensor product over A prime. Let's show that it's an exact functor with respect to A prime, N prime. But this tensor product is canonically isomorphic to M tensor over A with N prime. And therefore it's exact. Alright, so flatness is stable under base change and under composition on the level of rings and modules, and therefore the same holds true globally for schemes. And the same also for faithfully flat morphisms. But I have still to define them. So when will we say that the morphism of schemes is faithfully flat? Well, I mean, the natural thing to do is to say that these are the morphisms that are both flat and surjective, because in the affine case, this will match with the description of algebras over rings that are faithfully flat. So F faithfully flat by definition will mean that F is flat and surjective, and then as surjectivity is stable under base change under composition, just as flatness implies that faithful flatness is also stable under base change and composition. Contains isomorphism, of course. You can, as an exercise, give variants of this definition here by saying, by proving that F is faithfully flat if and only if the inverse image functor going from modulus on Y to modulus on X is exact and faithful. So if you want to reconcile the definition I have picked with a, let's say, the more conceptual definition, that would make a sense for a morphism of general Lutheranian spaces. Maybe in this case, surjectivity is on the right node, or for a morphism of ring topoi. So maybe the right node, the more reasonable notion would be that the inverse image functor is faithfully correct. Let's at least prove this, and of course we will need that if F is flat and surjective, then the functor on modulus which transforms F into inverse image of M is exact and faithful. Exact because of flatness, of course. And why faithful? So we have to prove that if this is equal to 0, then M is equal to 0. But this is equal to 0, this means that its stalks are equal to 0 at all points x. But any point, and that this is equal to 0 means that the stalks of m at all points y are equal to 0. So that's what we have to prove. But every point of y has a point x above it, because f is surjective. That's the assumption. And now what is the relation between my and the stalk of its inverse image at x? This is just my tensor over the local ring below with the local ring above. And because the local ring above is flat over the local ring below and hence faithfully flat, we have it. Therefore, as the module above is 0, the module below must be 0 too. All right. Yes, now I want to come back to flat morphisms, so I have just introduced for the time being the definition of faithfully flat morphisms. Later we will work mainly with these, but let's say some more about flat morphisms. Let x goes to y be a flat morphism. Then I claim that every irreducible component of x dominates an irreducible components of y. Dominates means that if I look at the closure of the image in y, this is an irreducible component of y. So this is the same as to say that if x in capital